Welcome to this series of lessons on C++ programming. In a series of short videos, I will be demonstrating some of the main features of the C++ programming language. C++ is an exceedingly powerful language that has been around since the early 1980s. It's still very popular despite the advent of other more modern languages such as Java and .NET. It owes its popularity to the fact that it is a portable language. There are numerous compilers available for it, including many open source compilers. It works on many platforms, from microcontrollers to mainframe computers, and under many operating systems, from real-time operating systems through Unix, Linux to Windows, Mac OS X to mainframe operating systems. It is low level in that it has functionalities to access raw memory through pointers. Yet it's also high level in supporting the big three object-oriented principles of encapsulation, inheritance and polymorphism. In fact, it arguably does this better than the modern languages mentioned previously. Finally, it's fast. Of course, it's just as easy to write inefficient code in C++ as in any other language, but it's easier to write performance code in C++ than most other languages. The objectives for this course are quite simple. At the end of this course, you'll be able to understand and use the key concepts of object orientation. You'll be able to use both fundamental and complex data types defined in the language. You'll be able to use pointers and dynamic memory. You'll also be able to use modern programming techniques such as move semantics and lambdas, but at a basic level. You'll be able to write efficient and robust code, and use generic containers and write your own templated generic functions and classes. The prerequisites of this course: you should be able to use an IDE or at least have a method of compiling and building C++ programs. You should have some knowledge of the built-in data types in C++ and be able to create and use complex data structures, albeit to a beginner's level. You should be able to use simple assignment statements, iterative and decision statements, and be able to write simple functions. You should have an understanding of the principles of object-oriented programming, even if you don't know how to implement them fully in C++. And finally, you should be aware of the standard template library and the common use containers. An in-depth knowledge is not necessarily required, as this will be taught as part of the course. The course is broken down into chapters and lessons, with each chapter subdivided into short lessons. At the end of most chapters, there's a short hands-on exercise in which you can test your knowledge of the topics that you've just learned. The Working Files folder contains examples of all the code used in this course, as well as a code skeleton you're asked to modify or enhance in the hands-on exercises. A sample solution is also available to the hands-on exercises. All code samples are given in platform-independent flat files that can be imported into most integrated development environments without any trouble. Let's have a brief look at what's in store for you on this course. We'll look at the complex data types, structures and classes. We'll look at functions and types of function parameters, including optional parameters, passing by value and by reference. We'll look at classes and class initialization, using constructors and destructors in classes. We'll also look at the more advanced class copy construction and conversion construction. We'll be looking at pointers, including their use, and also smart pointers and pointers to functions. We'll be looking at relationships between objects and how we can represent that in classes. Operator overloading covers global overloading and member function overloading. Inheritance is covered. This is the second major principle of object-oriented programming, as is polymorphism. Finally, the course covers the standard template library, or STL, and the algorithms that you can use with the STL. In this video, we'll be looking at the basic data types in C++. As you can see, I've created a program which has various different data types declared. The standard built-in data types, the integer data types, are short, unsigned short, int, unsigned int, long, unsigned long, and long, and finally unsigned long. On a Windows system, these variables take up 2 bytes, 4 bytes, 4 bytes, and 8 bytes respectively. However, the size of these variables isn't fixed, as we shall see shortly. The floating point data types are float, double, and long double, which take up 4 bytes, 8 bytes, and 8 bytes respectively. And then there are other data types, as defined on lines 23 to 25, char, for storing a 1 byte character, bool for storing true and false values, which also takes up 1 byte, and wchar_t, which is traditionally used for wide characters or Unicode characters. This is a wider version of a char and takes 2 bytes per character. The newer data types are listed below on lines 28 to 35. These are all fixed size integer data types. The size is fixed regardless of the platform or the compiler that you're using. They're all named int size_t, so int8_t is a 1 byte or 8-bit fixed integer. There are corresponding unsigned versions, uint8_t, uint16_t, and so on. As well as the standard fixed size integer data types, there are also other data types that have been introduced more recently. We can see on lines 37 to 52 of my example, an int_fast8_t. Underneath the fixed size data types, you will see a series of fast and least size data types. The fast data types are there to allow the compiler leeway in choosing a type which is fastest, but is at least the size as specified in the variable type name. So for example, an int_fast16_t will be at least 2 bytes, but on my system it actually turns out as a 4-byte integer because integers are fastest. The following least types allow again the compiler to specify a type, but it must be at least the number of bits as specified in the variable name. So an int_least32_t must be at least 32 bits, but the compiler is given the leeway to choose a larger type if necessary. Finally, there are 2 more data types, char16_t, which is a UTF-16 encoded character, and a char32_t, which is a UTF-32 encoded character, and those are 2 and 4 bytes fixed, respectively. If it's necessary for you to find out the size of a particular data type, you can use the sizeOf operator as I've done on lines 60 onwards. You can use sizeOf type, or in actual fact you can also put a variable into the sizeOf operator and say sizeOf a variable name. To use the newer data types, you must include the cstdint header file, and everything within that header file is declared within namespace std, so you will also either need a using namespace std statement, or you'll have to prefix everything that you use with std::. Everything in this file is available to you in a file called types.cpp in your working files folder. In this lesson we'll be looking at enumerations or enums. Let's consider a situation. What exactly does that statement mean? Well, assuming today is supposed to represent a day of the week, 3 could actually represent any day from Tuesday to Thursday. It all depends whether we're numbering from 0, and also which day of the week is considered the first day of the week. In some situations, some countries consider Sunday as being the first day of the week, and others consider Monday as being the first day of the week. So statements such as this are totally ambiguous. We could get around this problem by declaring a series of constants, like this, and so on. If we wanted to use our previous example, the code becomes a lot clearer to read. There is an alternative. We can declare an enum, like this. The enum weekdays declaration on line 4 of my code actually declares a series of 7, in this case, numeric constants. There are no values to these constants displayed. However, the compiler, when it sees an enum declared like this, will allocate the value 0 to the first element of the enum, as you can see from my tooltip here, and every subsequent member of the enum will be the previous member plus 1. So Monday is 1, Tuesday is 2, and so on. That's a very quick way of avoiding this necessity of declaring lots of individual constants. And my code, int today equals Monday, is still very readable, and provided I use the enum constants, it all works nicely. You might say, well, I don't want, in all cases, the compiler to provide values for me, and let's take an example of that. In the new enum on line 5, I've explicitly given 3 out of the 4 members of the enum values. I didn't need to give OK the value 0, the compiler will assume that anyway. In this case, OK is explicitly set to 0, warning is explicitly set to 5, error will implicitly take the value of warning plus 1, in other words 6, and fatal is explicitly set to 999. Let's take a look at the use of some enums. I'll declare another variable. You may have noticed that on line 10 I used an int and a member of the enum Monday. This is fine. An enum is based on an integer data type. So an assignment of an enum to an integer is an implicit conversion from an enum to an integer, and this is allowed. I could of course say tomorrow equals Tuesday, which is also fine. In this case, I'm assigning an enum member, Tuesday, to a variable of type weekdays, which is the same enum. However, if I try and assign an integer to a variable of type weekdays, as I've done on line 13, you can probably see there's a red underline under the equals, and that is telling me that that is an invalid assignment. There is no implicit conversion from an integer to an enum, even though the number 4 actually represents Thursday. Take that line out. Let's add a couple more enums to my example. There's an enum color, which has 4 data members, red, yellow, blue, green, and I'm quite happy to let the compiler implicitly allocate the values 0, 1, 2, and 3 to those enum members. I've added another enum called mood, which contains 4 members, happy, blue, excited, and indifferent. Again, I've let the compiler allocate the values 0, 1, 2, and 3 to these 4 data members, and I'll insert some code to use these enums. Have a look at this code, and I've got errors. The errors come out of the fact that I've declared blue twice in 2 different enums. Blue has effectively got 2 values. In the enum color, it's got the value 2. In the enum mood, it's got the value 1. This is not allowed. Enums and enum members are global in scope. A modification to the C++ standard, however, has ensured that this situation can now be changed. With the inclusion of the keyword class on an enum, we can sort this problem out. It's not simply a matter of specifying class, because we now have to say which enum a particular member comes from. And we do this using the : scope resolution operator. There is no implicit conversion between enum class types, so I couldn't, for example, say that is not allowed. That concludes the lesson on enums. A fully commented summary of all the code used in this example is in the file enums.cpp in the Working Files folder. This lesson is about structures. I've declared several structures in a header file in my Visual Studio project. I'm going to discuss them one at a time. We'll start off with the structure date that you can see on lines 1 to 6. This structure is a straightforward structure which contains 3 data members, dd, mm, and ccyy, all of type integer. To use struct date, I can use code like this. That declaration of a date structure called VEDay uses universal initialization to initialize dd to 8, mm to 5, and ccyy to 1945. If I want to access any of the members of my VEDay date structure, I can do it using dot notation like this. First line statement on line 9 sets the dd member of the VEDay variable to 10, and line 11 queries the ccyy value within VEDay. Let's take a look at our second structure now. In this case, I've got a structure called employee. It contains 3 members. The first one is a simple integer, but the second 2 on lines 11 and 12 are embedded date structures. It's quite acceptable to embed one structure within another. I've done it twice, the first one for date of birth and the second one for start date. If I want to access my employee structure, I can do it like this. To set the employee number, and to access my date of birth, I use 2 dots. The first dot gets me to the date of birth, and the second dot takes me to the dd member of date of birth. The employee structure me is currently declared on the stack. The employee structure could in fact be very large. My structures are very small, but in real life they're likely to be much larger than this, and declaring them on the stack is not considered good practice, because the stack is a finite resource and you can soon end up blowing the stack. To declare a structure on the heap, you use this syntax. And to use it, we need to create some memory. Once that's done, we can access the members of PU. Note that this time we're not using dot notation, we're using arrow notation. PU is a pointer to an employee, and in fact the arrow looks just like a pointer. If I want to access the DOB member of PU, then I use this syntax. But because DOB is not a pointer in its own right, I have to use dot notation. Going back to the declaration of the structures, you may have seen structures declared using the typedef keyword. This is not uncommon. So, taking my date structure, you may have seen syntax like this. As you can see, my struct date works perfectly okay embedded within my struct employee, and in fact anywhere in C++ to declare a structure of type date, I simply say date and structure name or variable name. So why do we have this definition methodology? In actual fact, it harks back to C, compatibility of structures in C++ and C. In C, to declare a structure, you must use the keyword struct. To declare a variable of type that structure, you must also again use the keyword struct. So in my code, if this were C, to declare a date, I would have to say, in C, that would be a compulsory syntax. In C++, we use the syntax date today. The typedef on the structure simply means that we don't have to use the keyword struct to declare a variable of type date in C. It's purely there for compatibility and is only necessary if you intend to use your structures cross-language between C and C++. Since I don't, I'm going to put mine back to the C++ syntax. Let's take a look at some more structures. Let's take a look at a slightly more complex structure. In this case, I've called it worker. This structure consists of 5 integers and 4 booleans. What about the size of structures? Well, I'll tell you that the size of a structure is the sum of the sizes of all its elements. But there's a caveat to that. Sometimes the compiler will insert padding. We'll deal with the way it pads later, but for now, let's just say that we have 5 integers, which is 5 times 4, which is 20 bytes, and 4 booleans, 4 times 1 byte. So the size of my structure on this platform, and remember the size of variables is platform dependent unless you're using the fixed size data types, then the size of this structure is 24 bytes in memory. That's a little excessive. I can make it a lot smaller very easily. An int can hold values in the range plus or minus 2 billion. The day of the month is in the range 1 through to 31. So at the very least, I can make this structure a lot smaller by changing it to this. It's essentially the same structure with the same members, but I've reduced the sizes of the data members. So for start day, which is in the range 1 to 31, I've used a char, which can store numbers in the range 0 to 255. Similarly for start month. The year is a little larger because I specified a 4-digit year. That won't fit into a char, but it will fit into a short. If we add up all the bytes for this structure, we've got 2 1 bytes at the top, 2 chars, plus a 2 byte short, plus 2 chars, plus 4 single byte booleans. The size of this structure in memory is 10 bytes. So we've more than halved the memory allocation for this structure. But we can go one step further still. You may have noticed that at the bottom of my screen I've got a tiny worker structure. The tiny worker structure uses a feature called bit structures, where within a structure we can actually specify how many bits each individual field takes. So start day, for example, is 5 bits. 5 bits can store numbers in the range 0 to 32. Our day of the month is in the range 1 to 31, which fits nicely. The month is in the range 1 to 12. I've used 4 bits, which can store numbers in the range 0 to 15. So I've minimized all my fields to the minimum size necessary to store the data. There are no data types associated with bit fields. They're all simply unsigned. And in fact, you can only use integer type data in a bit structure. The 4 flags at the bottom of the structure, married, driver, owns car and wears glasses, are all a single bit, because they're only designed to store true or false values, which can be represented by 1 bit. If we add up the size of this structure, it's 5 bits plus 4 bits, which is 9, plus 11, which is 20, plus 5, which is 25, plus 7, which is 32, plus the 4, which is 36. A bit structure must be a multiple of 8 bits. Mine isn't at the moment. The compiler will automatically add padding into it to make it a multiple, so the size of my tiny worker structure will become 40 bits or 5 bytes. So I've actually come down from 24 bytes down to 10 bytes by using built-in data types, and finally down to 5 bytes using bit structures. However, there is a cost of doing this. My original structure used integers. My small worker used smaller data types. Some data types can be more efficient than others, so my small worker on some platforms may suffer performance overheads because a char is not as efficient as an int. Similarly with my tiny worker, it is very inefficient to access individual bits of a byte. In this case, the compiler has to create additional code to address bits. So the tiny worker structure is substantially less efficient than my small worker and my worker. To use these structures, the code is exactly the same. Because my structure is declared on the stack, I use dot notation. I could also declare it on the heap and use pointer notation, but I'll stick with dot notation for this example. And finally, for my tiny worker, so in use there is absolutely no difference between these structures. Another drawback of bit structures is that you cannot use the address of operator to get the address of any member of that structure. With me, you, i.e. worker and small worker, they are byte-oriented variables, so I can take the address of any member of structure worker or any member of structure small worker. Tiny worker is not byte-oriented, it's bit-orientated, so you cannot take the address of any member of that structure. This lesson introduces unions. A union is very similar to a structure, and as you can see here, I've declared a structure employee and a union called memory. In a structure, each data member occupies its own area of memory, so the size of my structure employee will be 4 bytes for the employee number plus 4 bytes for the float salary. That's on my system. Remember, that could be platform dependent. Total size of my structure employee is therefore 8 bytes. In a union, the members of a union share the same area of memory. In other words, the size of any given union is the size of its largest member. Let's look how we can use our memory union. Here I've declared a union of type memory called space. I've listed the size of the employee structure and the size of the memory union. And remember, I should get 8 for the employee structure and 4 bytes for the memory union. To use it, on lines 12 to 19, I've inserted a number into the memory base.int number member of the union, set it to 99, and then I've displayed it again. Following that, I've started to use the float number member of the union, and again added a value into it and displayed the value of it. Any attempt to cross-use those members, i.e. while I'm using the float number, try and see out the int number member of the union, will result in an invalid output. We'll see that in just a moment. Before we go on to that and run this program, I'll show you a more valid use of unions. In this union, I've declared a union called bitfields. I've got 2 individual members of that union. The first one is a char, which I've called whole byte. That represents an 8-bit character. The second member of my union bitfields is called individual bits, and it is a bit structure. And I've got within my bit structure 8 individual bits, each of size 1 bit. Usage of this structure is shown here on lines 21 through to 26. I've declared a variable of type bitfields, which is the entire union. On line 23, I've then used the whole byte member to address all 8 bits within the union and set it to 0. On lines 24 and 25, I set just bit 0 and just bit 3, using the bit structure member of the union. On line 26, I've couted the whole byte member of the union. What I've done is I've managed to set individual bits using the bit structure members and printed out the whole byte using the whole byte member. Let's have a look at the output from this program. The first 2 statements were the size of the structures, and I said that my employee structure was 8, which indeed it is. The size of my union was 4 because the 2 members occupy the same area of memory, and that's true. When I went to use the memory union, I put 99 into int number and then couted it. Then I put 33.3333 into the float number member of the union and couted it. And then I performed an invalid action. I tried to cout the int number member of the union, and as you can see, I get total rubbish. The output in that case is meaningless. This means that any member of a union can only be used in isolation. You can't start to use one member, suddenly switch to another member, and back to the original member interchangeably, expecting data to be held over from one member to another. The last set of output there is the whole byte. I set bits 0 and bit 3 to 1. If you write that down and look at it in binary, the actual result that I get is 9, and that's exactly what I get from my whole byte. That concludes the lesson on unions. The code for use in this lesson is available in the working files folder for this lesson. This lesson is about data alignment and memory usage within structures. Without considering bit structures or any other efficiency measures, it's very easy to create a structure that wastes huge amounts of memory. Let's take a look at an example. In this employee structure, I've declared various fields of various different sizes, an employee reference which is a 10 char array, followed by a double salary, an int department code, and so on and so forth. This structure is quite readable. Related fields such as, for example, performance bonus and satisfactory conduct are next to each other in the structure, as you might expect. If I add up all the fields in this structure, and remember the size of a structure is the sum of the sizes of all its fields, the figure that I actually get is 49 bytes. However, if I let the compiler tell me the size of this structure in memory, the figure that I get is 72 bytes. In other words, there's some 23 bytes difference. So where's this 23 bytes gone? Well, the compiler tries to make the structure as efficient as possible in terms of CPU usage, and variables are far more efficient if they're aligned on certain boundaries. For example, an integer is usually aligned on a 4-byte boundary. A double is usually aligned on an 8-byte boundary. If the members of my structure, my employee 1 structure, follow one another directly in memory, this would not be the case. So the compiler inserts padding. The employee 2 structure here is a simulation of what the compiler might do to pad this structure. The employee reference is still 10 bytes. The double salary which immediately follows it must go on an 8-byte boundary. The nearest 8-byte boundary is 16 bytes, so it inserts a padding of 6 bytes, and so on for the rest of the structure. If I were to take the size of this structure and let the compiler tell me how many bytes it is in memory, the result would be 72, exactly the same as it was for the compiler inserted padding employee 1. So what can we do about this? Structure employee 3 takes advantage of the fact that doubles can be grouped together, so the first 3 doubles will be placed on 8-byte boundaries regardless of any packing. They won't need packing. If we group variables in this way, largest variables first, followed by smaller, followed by smallest variables, that will reduce the size of my structure considerably. In fact, in this case, the compiler will have to insert very little packing. The only packing it will have to insert is at the very end of the structure to pad it out to a round number of bytes. One disadvantage of doing this in this case is that the structure is less readable, so we've now separated different fields which are potentially related. You might ask, is there anything that we can do to prevent the compiler inserting this padding? Well, the answer to that is yes. In employee 4, I've used a series of compiler directives or preprocessor directives to control how the compiler packs this structure. On line 63, the hash pragma pack push stores the current packing onto an internal stack. Line 64 then modifies the default packing to 1-byte boundaries, and at the end of this structure on line 78, the hash pragma pack pop restores the value that was pushed on line 63. But between lines 65 and 77, the packing will be 1-byte bound. Therefore, salary will immediately follow the employee reference. If I were to take the size of this structure, the size of the structure will be 49 bytes. As the comment says on line 65, the structure is now readable, it's now very well packed, but it's potentially non-portable. Also, it is likely to be a lot less efficient than the previous employee structures. More recent compilers allow you to specify the alignment of variables using the alignAs keyword. In the case of this structure employee 5, I've specified alignAs 1 to 8. That does not affect individual members of the structure, it simply means in this case that employee 5 will be aligned on a 1 to 8 byte boundary. To affect individual members, you have to declare each member with an alignAs statement. The effect of using alignAs is effectively this. The size of the structure becomes 128, and the compiler will effectively insert a padding of 56 bytes somewhere within the structure, most likely at the end. If I go to the code and run this code, it gives the size of the employee 1, which is the readable, size of the padded employee 2, which should be the same as employee 1. It'll give the size of the less readable but packed employee 3, size of the hash pragma packed employee 4, size of the aligned employee 5, and the size of the simulated aligned employee 6. So employee 1 and employee 2 are both 72 bytes. They're packed but readable. Employee 3 is less readable but packed better. Employee 4 is packed with hash pragma 1, meaning that everything is 1 byte aligned. That makes it readable potentially but less portable. Employee 5 was the align as 128, and employee 6 was the simulated align as with packing that I inserted myself. That concludes this lesson on alignment. All the code in this lesson can be found in the working files folder. Over the last 30 years or so, C++ has been developed, changed, standardized, and improved multiple times. Rather than de-implement features, the preference has been to make language features fully backwards compatible wherever possible. This has sometimes resulted in there being several ways of doing things. One of these areas is initialization. Let's look first at some traditional ways of initializing variables. On lines 51 and 52, I've declared two integers and initialized them both to 0. Both syntaxes are valid and always have been. Next, on lines 58 to 61, I've declared 3 arrays and a variable of type date structure. Numbers1 is an integer array of 5 elements. It's a sized array, and after the declaration of the array, I've used an initializer list to initialize each element to the values 0, 1, 2, 3, 4. Numbers2 on line 59 is an unsized array. In this case, the compiler will count the number of initializers in the initializer list, in this case 5, and size the array to 5 elements, and then go on to initialize the elements to 1, 2, 3, 4, 5. Numbers3 is a sized array of 10 integers. In this case, I've used an initializer list with one initialization value. That initialization value will be assigned to the first element of numbers3, and all other elements will be initialized to the default value for the type. In the case of the structure, date, and the variable millennium, I've again used an initializer list to initialize it to dd1, mm1, ccyy 2000. Now we'll move on to classes. We've not really discussed classes much so far, so this is going to be a very brief overview of class initialization. Line 70 creates a worker1 variable of type employee, where employee is a class. The initialization here is non-existent, and in fact will call the default constructor of the employee class. On line 71, I've declared another worker, worker2, of type employee, and I've initialized it by calling an overloaded constructor with 2 arguments. Finally, on line 78, I've created a vector. The vector is a standard template library container, and in this case I've created a vector of integers called digits1, and I've initialized it using a constructor for the vector object. This particular constructor takes 2 parameters. The first parameter is the number of elements, and the second parameter is the initial value of the elements. So in this case I'll create a vector called digits1, which has 3 elements, all of them initialized to 999. That's traditional initialization. Now let's have a look how this changes with universal initialization. We'll take the fundamental data type int first of all, and on line 55 I declared an integer c. To initialize that to 0, that is the universal initializer syntax. In fact, the universal initializer uses curly braces and values on every initialization that we should look at. So for the arrays, on line 64, numbers 4, if it's going to be initialized the same as numbers 1, will be initialized like this. Numbers 5, our unsized array, will be initialized like this. As you can probably see, there's a pattern emerging here. The initialization of arrays using universal initializers is almost identical to the original initialization methods. All we're doing is missing the equals out. So for number 6 will be the initialization, and for first millennium, that will be the initialization. Moving on now to our objects, our classes. Line 74, worker 3, for default initialization, I can do that, which is exactly the same as it always has been, or using universal initialization, I can now also specify that empty curly braces. As far as constructors are concerned, to initialize worker 4, the same as worker 2, I can use this syntax. Vectors are a little different. You might think using universal initialization that the syntax to initialize digits 2 might be this. If you remember, a while ago I said that line 78 digits 1 created a vector of 3 integers each initialized to 999. Line 81 does not do that. Line 81 creates a vector of integers of 2 elements, with the first element initialized to 3 and the second element initialized to 999. In order to create a 3-element vector, all initialized to 999, the syntax would have to be, when using STL or standard template library types, you have to be very careful to distinguish between construction and initialization. Let's take a look at our class. I said I created a class employee. It's a very simple class. It has 2 public member functions, both of them constructors. On lines 15 to 19 is the default constructor, and on lines 20 to 24 is the overloaded constructor. These topics will be dealt with in more detail later in the lessons. As you can see, on lines 16 and 21, I've used round brackets to initialize the value of salary and emp number. Using the new universal initialization syntax, this could become, and for the overloaded constructor, there's one more change with modern compilers. In the past, C++ never allowed in-situ initialization of class data members. Newer compilers will allow you to initialize a data member in place. In the working files folder of this course, you'll find files called courseevent.h, global.h, person.h, and handson.cpp. You should import the CPP and header files into your chosen development environment. I'll demonstrate this using Visual Studio 2015. I'm going to start an empty project, a Win32 console application, which I'll call Hands-On. I'll set the project settings to be an empty project. The security development lifecycle is not needed. It just causes additional checks, and for an empty project we don't need it. When I click Finish, my project is created and it's an empty project. There are no source files and no header files in my project. I can now add the files from the working files folder to my project. My files are actually on my desktop in a separate folder. You can select all the files and add them all in one go. And as you can see, the header files have been added to the header file section and the CPP file has been added to the source files section. Once you've added these files, you should have a look at the files. The files contain various comments. The comments are your instructions. From these 3 files, in the course event file, you're asked to create a course event structure. The fields of the structure and the field types are given for you in the comments. The global.h file asks you to create enums, and the person.h asks you to create a person structure. Again, all the field names and field types are given for you in the comments. The CPP file gives you further instructions. You'll have to include some header files at the top. Then it asks you to declare a course variable and a pointer to a person variable, and so on. Once you've done all that, you should be able to run your project and have a successful solution. A sample solution with the same file names but with solution in the file name is also available in the working files folder so that you can check your answers. This lesson is an overview of how function parameters work, and in particular the copying mechanism for pass-by value. I've created a declaration of a function which takes 2 parameters called add. If we switch to the bottom of the screen now, that function is implemented and it simply takes the 2 numbers, declares an integer result, adds the 2 numbers into result, and then returns the value. When this function is run on line 11, the values of x and y are copied into 2 local variables, num1 and num2, within the function. This has several side effects. First of all, the copying does take a fraction of a time, although in the case of the built-in data types, the time actually taken to copy them is minimal. It also uses space on the stack, as all parameters are normally passed on the stack. When the result is returned, the value returned is also copied back to the original program. This is quite reasonable because the moment we leave the add function on line 20, the values stored in num1, num2, local to add, and result, which is also local to add, are all destroyed. So the value must be copied back to be assigned to answer on line 11. We'll return to this again shortly. We've already seen passing parameters by value and how it works for copying the parameters. But what if the parameter being passed is a large structure or object? This data will still be copied. This has several drawbacks. Firstly, the item being copied will be placed on the stack. The stack is a finite resource and it's very easy to exhaust it. This will usually manifest itself in a runtime Stack Overflow error. We could increase the size of the stack, however, this is not generally good practice. Secondly, there's the time taken to perform the copy in the first place. There has to be another solution. As a general rule of thumb, it's okay to pass the built-in primitive data types by value. These are permanently small and trivial to copy. However, the complex data types are not. The solution to our predicament lies in references. References are similar to pointers. In this example, I'll show some code that uses references and compares them to pointers to show the differences. The first part of the code, from lines 5 to 11, uses references, and 13 to 19 uses pointers. Let's look at the references first. The first thing to note on line 6 is that a reference must be initialized. It must be initialized on the declaration. Compare this with the pointer declaration on line 14. The pointer doesn't need to be initialized. Secondly, and possibly more confusing, a reference is declared using the ampersand character. So on line 6, int ampersand refx. Refx is a reference to an int, and because of the initialization, the integer it refers to is x. On line 14, the pointer is declared with an asterisk. Pint is a pointer to an int. When we initialize a pointer on line 15 or 16, we use the ampersand character to initialize pint to the address of x. The context in which these operators are used is important and determines the actual meaning of the statement. Next, a reference doesn't normally create any storage, although the C++ language specification only states how a reference should behave, not how it should be implemented. A reference in this context, that is a reference variable, will almost certainly not use any memory. A pointer, on the other hand, is a separate variable. A reference is not. A reference is an alias for a variable. It refers to a variable. On lines 10 and 11, I've used the variable x and the reference refx. Those two statements are identical in what they do. Both of them assign 10 to the variable x. On line 10, directly, and on line 11, via the reference refx. On lines 18 and 19, I repeat this process using the variable y. Line 18 assigns 20 directly to y. Line 19 assigns 20 to wherever pint is pointing to. In this case, pint was initialized to the address of y on line 16, so 20 is assigned to y via the pointer. All of these statements alter the values stored at x and y. Now that we looked at straightforward references, let's look at references with respect to function parameters. On line 3, I've declared a function called SumAVGMinMax1. That function takes two integer parameters, n1 and n2, followed by sum, which is a reference to an int. This is a reference parameter. AVG, which is a reference to a double, again a reference parameter, and two final parameters, min and max, which are both reference to ints or reference parameters. Within main, I've used this function SumAVGMinMax1. I've declared various variables. The first two, num1 and num2, are input parameters to the function, and the last four variables, total, average, smaller and larger, are results that I'm going to retrieve back from the function. Reference values, or reference parameters, can be used to return values from functions. When I call SumAVGMinMax1, I pass it num1 and num2 for the first two integer parameters, total for the sum reference to an int, average for the AVG reference to a double, and smaller and larger for the min-max reference to ints. That's used as shown on lines 18 and following. If we look at this function on lines 18 to 24, we can see there's no return statement, any values to be returned are returned via the reference parameters. So sum is assigned the result of n1 plus n2, AVG is n1 plus n2 divided by 2. For min and max, I've used the ternary conditional operator. This is effectively an if statement. And the way you read this, if you're not familiar with it, is if n1 is less than n2, question mark, then the result is n1, colon, else, the result is n2. Reference parameters are all very fine, but they do have some serious side effects. For example, within the function, if I were to pass n1 and n2 as reference parameters, I could change the values of n1 and n2 within the function, and this would change the values in the program that calls some AVG min max 1. Let's have a look at that. I'll create a function some AVG min max 2 that passes all the parameters by reference. Since I've declared it, I must also code it. Superficially, the two functions look identical. If I were to attempt to change n1 within some AVG min max 1, that's quite acceptable, but the value of n1 is only changed within the sum AVG min max 1 function. If, however, I change the value of n1 within the sum AVG min max 2 function, because n1 is a reference to the same variable in the call, let's put a call in for this function, then when I call sum AVG min max 2, n1 is changed. Because n1 is a reference to an int in the function, that will affect the value of num1 within main. After the call to sum AVG min max 2, num1 will have the value 999. So why do we have reference parameters? Well, for a start off, reference parameters stop copying. It's all very well to copy ints, floats, doubles, and any of the other built-in data types. However, if the parameter to my function was a large structure or an object, then the copying becomes non-trivial. It takes quite a lot of time to do the copy, and also the copy will use up more space. To prevent this, we always pass, or normally pass, parameters which are larger than built-in data types by reference. This, of course, as I've already said, exposes that data to alteration within the function. How can we prevent the function from modifying data unintentionally? We use the const keyword. So my sum AVG min max 2 would ideally pass n1 as a const reference to an int, and n2 as a const reference to an int. Since I've changed the function signature on the declaration, it means that I've also got to change it here on the use. And since they're const, you can now see that the compiler has said that n1 cannot be modified. The expression must be a modifiable value. Therefore, we can build a rule for reference parameters. For input-only parameters, such as n1 and n2 in our sum AVG min max 1 function, the built-in types may be passed by value. The compiler knows how to pass these types efficiently, and the space taken up by the copying is minimal. Anything larger than a built-in data type, anything which needs a header file to implement, and that can include structures and classes, should be passed by a reference. If you don't want the function to modify the values within the data structure, then you should pass it by const reference. If you want to return values from the function, these must be reference parameters, they can't be const references. In this lesson, we're going to discuss arrays as parameters to functions. Just like any other data type, an array can be passed into a function, and I've created an example here that shows an unsized integer array called Enums being passed into a function called doSomething. Within main, I create an array of 10 elements and initialize it either by using an initializer list or by using universal initialization. Then I pass that array into doSomething. Within doSomething, I change one element of the array, in this case element 7, to 9999. It looks as if the array nums is being passed by value into the function doSomething. So in theory, if I alter any element of the array within doSomething, that change should not be reflected in the numbers array in the main function. Let's run the code and see what happens. In fact, within main, the array location has been changed. Therefore, this suggests that we're not passing the array nums by value. We're in fact passing it by reference. This is not quite the case. What's actually happening behind the scenes is that nums is a pointer, and it's the pointer that's being passed in to do something, and therefore, since it's a pointer to the beginning of the array, any changes within do something are reflected in numbers in the main program. As it stands, this program has a slight problem. What if the array that I pass in to do something doesn't have at least 8 elements? In that case, I'd be trying to address a location within the array that simply doesn't exist, and the result of doing that would be undefined. It could certainly cause my program to fail. So let's look at some alternatives to passing arrays in this way into my doSomething function. In this file, I've supplied various declarations of a sum function. Sum function is designed to add up the contents of an array and return the answer. So on lines 1 to 9, I've declared and implemented a sum function that takes an array of 5 elements, 5 integers. I've passed a sized array into sum. This function would work. However, what would happen if I wanted to pass an array of 10 elements? You might think that I could write another function, sum, on lines 11 to 19, which takes a different sized array. However, this actually won't work. You can't overload an array just on size. If I then wanted to create one that used 15 elements, 20 elements, 25 elements, 30 elements, I'd end up writing lots and lots of sum functions, which just isn't practical. Having discounted those two solutions, I'll comment them out. The next solution, on lines 21 to 29, is a little better. In this case, I've passed an unsized array. However, on line 24, I want to total all elements of the array. How do I know how big the array is? Simple answer is, I don't. There's no way I can work out how many iterations I need to do within my for loop. Therefore, this solution is not a valid solution to our problems, and I'll comment it out. On lines 31 to 39, I have the most often used solution to this problem. I pass an unsized array, which will accept an array of any size, and also pass as another parameter the actual size of the array. And then within the code which does the totaling, in the function on line 34 in this case, I can use the size to work out how many iterations I have to do to total it. A better solution still would be to pass both a start point and an end point. So I still pass the unsized array, but 2 integers saying start at this point and end at this point for the totaling. This is by far the most versatile solution, and it will work. This lesson is all about returning values from functions. On the screen I've created some examples, and these initially are a review of different ways of returning values from functions that you should already know about. For example, the function on lines 4 to 9 shows a simple fundamental data type returned via a return statement. I've coded the long-handed way of doing it on lines 6 and 7 and commented out a shorthand version of doing it on line 8. Similarly, in the function on lines 11 to 14, I'm still returning a fundamental data type, an integer, but this time I'm returning it as an integer reference parameter to the function. On lines 16 to 20, I've declared a structure called SumAVGRect with 2 data members, an integer and a double, called Sum and AVG respectively. And on lines 22 to 30, I've declared and implemented a function called SumAVG, which returns a SumAVGRect structure. Code for this function again is coded in 3 ways this time. A long-handed version which creates a temporary SumAVGRect structure called temp, assigns values to the sum and the AVG members of the structure, and finally returns it. Lines 28 and 29 are shorthand versions of the same code, and note I've used the universal initialization here. Another way of returning values from a function without using a structure is to use a more modern feature called a tuple. In order to use the tuple, you must hash include the tuple header file, and to save me typing std : scoping everything to the standard namespace, I've also coded using namespace std. Let's take a look at an example of a function using the tuple. My function is coded on lines 32 to 35. The return type is tuple. It's a template function. The template can take any number of parameters. So when I declare a tuple with an int and a double, it's going to create me a tuple with 2 members, 1 int and 1 double. If I wanted more parameters, I'd simply extend the parameter list for all the return types that I want to return. The function is called SumAVGTuple, And the return statement on line 34 calls a function called makeTuple. This creates a tuple, passes it parameters. The first one is an int, the second one is a double. Again, this function can take multiple parameters, and it must have the same number of parameters as the type of the tuple. Let's look how this function can be used. I've declared the function SumABGTuple with a return type of tuple int double, and in main I've created a result variable of type tuple int double, so all my data types match up. On line 11 I've called SumABGTuple with the values 10 and 15, return the result into result, and see out of the values. As part of the tuple declaration and creation, you also get some get functions. These are also template functions, and get0 returns the first parameter, get1 returns the second parameter. So get0 will return an int, which is the first parameter to the tuple. Get1 will return a double, which is the second parameter to the tuple. If we run this, we should get the values 25 and 12.5. The functions that we've seen so far return values as copies. We should know that this copying mechanism can be bad. How do we stop copying? We use references. Let's look at some functions which return references. The first function on lines 1 to 5 returns a reference to an integer and takes two parameters which are added together. This is not allowed. Temp is a temporary variable. You can't turn a reference to a temporary variable because at the end of that function, the variable will be destroyed on the stack. Therefore, any reference to it used outside this function would be invalid. This won't cause a compiler error. It'll return a warning which tells you that you're not allowed to return a reference to a temporary or local variable. Okay, let's have a look at the function on lines 7 to 11. In this case, we have an increment function, and we return a reference to an int, and we return ++n1. Even though n1 is passed into the function, we still can't return it because n1 is passed by value, and it's therefore a copy, which is a local or temporary variable. So the function on lines 7 to 11 is invalid too. On lines 13 to 16, we have another increment function. This time, I'm passing in a reference to an int, incrementing it, and returning a reference to an int. This is fine. n1 is a reference, it's not a local variable, so the compiler thinks this is perfectly okay. Finally, on lines 18 to 21, we have another version of increment. In this function, I'm passing in a const reference to an integer, attempting to increment it and return the reference. This function won't even compile because we're trying to modify a const variable. Let's take a look at another example. In this example, I've got a simple int function, and it's used in main, and this function is perfectly okay as it stands. Newer features of C++ have introduced something called a trailing return. We can use auto, and the compiler will deduce the type of the function. So it should deduce that sum returns an integer. And it's fine. A more common way of doing this is to use something called the trailing return, which is this. This explicitly says that the return type is int. All of this seems a little bit unnecessary. Why don't we simply specify the type of the function as int in the first place? In fact, there's an extension to this syntax that we can use. We can use the keyword decltype like that. We can get the compiler to deduce the type of the sum function based on an expression. Again, this seems totally unnecessary. It's blatantly obvious in this function that the return type is an int. And in fact, normally I would never use this type of syntax in a straightforward function. However, where it does come into its own is in templates. If I turn my function sum into a template function, my function now has no types associated with it. It's a template function. In this case, the auto is almost essential. If I were to replace all this with an int, and then somebody were to pass in doubles, the return type would have to be a double, and there'd be a clash in the compiler. However, using this syntax, I can now call sum with integers, as it stands at the moment. I can also call it with other data types, like this, with a double, or even with a char. They all work because of the template function. No overloading, the template takes care of everything for you. If I run this, there are my answers, proving that it's worked with the integer, 20 plus 10 is 30. The doubles, 10.5 plus 33.3 is 43.8. And also with the chars, A plus 1 is B as a char. Quite obviously the explicit returns, wherever you can use them, are far more readable. The auto and decal type trailing return function syntax should only be used where necessary. This lesson discusses pointers as parameters to functions. Just like any other data type, a pointer can be passed into a function as a parameter. In the example shown on the screen, I've declared a structure date, and I'm passing in a pointer to a date into my isValid function, which is a very rudimentary date validation routine. It certainly doesn't take account of leap years. However, for the purposes of this demonstration, it will suffice. The value passed in is a pointer to a date called pDate. As you can see on lines 14 and 15, this allows pDate to be modified within the function. Not only can I modify the members of the structure that's passed in, as on line 14, but I can also totally corrupt or modify the pDate pointer itself. We can prevent this kind of modification by making our parameter const. Let's look at the first instance. pDate is now a pointer to a const date. Because the date that's passed in is now const, I can no longer modify members of the date structure as shown on line 14. However, I can still modify the pointer itself. The pointer itself is not const. To prevent that type of modification, I can pass in pDate is a const pointer to a const date. Now both the pointer itself, pDate, and the structure it points to, const date, are both constant and no modifications allowed at all, as shown on lines 14 and 15. The subject of this lesson is function overloading. Function overloading is the practice of having several functions, all with the same name, but with different numbers and/or types of arguments. In fact, the rules for overloading state that a function can be overloaded provided the number and/or types of the arguments differ. In this example in front of me, I've declared 7 different functions. They all have the same name, some are valid, some are not. Line 1 shows a straightforward print function with no parameters. Line 2 could not be implemented because it's only different based on the return type, and the return type is not part of the overloading criteria. Line 3 is a perfectly valid overload because it has one integer parameter. The only other print that is valid on that page above it is print with no parameters. Therefore, the number of parameters is different. It's a valid overload. The overload on line 4 is not valid. The reason it's not valid is that the name of the argument is irrelevant. It's purely the types and/or numbers of arguments that the compiler looks at. And this one is print with one integer. That clashes with the one above it, which is also print with one integer. On line 5, we have a print with 2 integer parameters. That's perfectly okay because there's no overload above it which takes 2 integer parameters. Again, on line 6, we have an invalid print function. This one has 2 integer parameters. All I've done is switch the names of the parameters round, but as I said before, the name of the parameter is totally irrelevant. It's the number and/or types of the parameters, and this clashes with the one above it. The last example on line 7 is perfectly valid because this one is print with an integer and a char array parameter. Function overloading is used frequently with class member functions and in particular with class constructors. The advantage of overloading is that it avoids unnecessary renaming of functions. All functions that do the same function, in my case here, print, can have the same name, making them more intuitive to use. And in fact, when we come to class constructors, the constructor has a fixed format name. There is no way we can actually call it constructor 1, constructor 2. Behind the scenes, overloading works by decorating the names of the function. The compiler uses a methodology called name decoration, or sometimes called name mangling. When the compiler encounters multiple functions with the same name, as in my example here, it will decorate the name of the function with additional characters that represent the function name, the class that the function is a member of, if it is, the namespace that the function belongs to if it's declared within a namespace, the types of the function parameters, the calling convention for the function, and the return type for the function, although this isn't used for the overloading system. Unfortunately, the C++ language doesn't define a standard name decoration scheme, so the way in which decoration differs from compilers to compilers. Let's take a look at another example of overloading. In this example, the first two functions are not overloaded, and they demonstrate what I would have to do if we didn't have the overloading facility. I'd have to declare an add2int function and an add2float function, but as you can see, the function actually does exactly the same thing. On lines 11 to 19, I've declared two similar functions. This time, they're both called add2numbers. The function on line 11 is the same as the function on line 1. The function on line 16 is the same as the function on line 6. The compiler will take care of differentiating between the two functions based on how you call it by mangling the name to include the parameter types. This might look to be a disadvantage. Overloading is used heavily in C++. However, as you can see, the function's code is exactly the same in all cases. If this is the case when you create your functions, you might want to consider using something called template functions as an alternative. These are discussed elsewhere in other lessons. This lesson contains optional or default parameters. There may be occasions where you find yourself repeating parameters in multiple function calls. Consider this example. I have a print function which takes two parameters, first one an integer number of pages and the second one an integer number of copies. In 4 out of the 5 cases where I call print on lines 7 to 11, the number of copies is always 1. It's only on rare occasions, i.e. line 8, that the number of copies varies from 1, in this case, to 2. In these cases, it would be nice if we can set a default, and in fact we can. If we put equals 1 on the declaration of the print function, then it's perfectly acceptable to omit the second parameter of the print function as shown. The default of 1 will be provided if I don't provide a second parameter to the print function as on line 7. The default parameter only goes on the function declaration, it doesn't go on the implementation. There are some rules associated with default or optional parameters. You can default as many of the parameters as you like, as shown on line 11. However, parameters may only be omitted from right to left. So the statement on line 11 is perfectly valid. All 3 parameters are defaulted. And in that case, you can call function 1 either function 123 with 3 parameters, or function 12 where the third parameter is omitted, or function 1 where the second and the third parameters are omitted, or indeed, as shown on line 18, with no parameters at all, in which case all 3 parameters are defaulted. Any call to function 1 with missing parameters to the left is invalid. C++ has no concept of missing function parameters. So when you're considering functions for default or optional parameters, the leftmost parameters should therefore be the ones most likely to be supplied or changed by the user. Default or optional parameters can be used alongside overloading. However, you must be aware that they can conflict with each other. On lines 5 to 9, we show some more calls to print. This time print is overloaded on line 1 with no parameters, on line 2 with 1 parameter, and on line 3 with 2 parameters in which the second parameter is defaulted. On line 7 we call print with no parameters. This is okay and will match up with the declaration on line 1. However, on line 8 we attempt to call print with a single integer parameter. The question the compiler will ask is this print declared on line 2 with an integer parameter, or is it a call to print on line 3 with an integer number of pages as 10 and a defaulted number of copies? In fact, the compiler can't resolve this situation, so it will be given an ambiguity error. The call on line 9 is perfectly okay. My personal preference is to not mix overloading with optional parameters, and to use overloading in preference to optional parameters, as I believe that this results in more readable code. All the code used in this lesson is available in the Working Files folder for this lesson. This lesson is your chance to practice your C++ skills in coding functions. In the Working Files folder of this course, you'll find files called handson.cpp, courseevents.h, global.h, person.h, handsonfuncdecal.h, and handsonfuncimpl.cpp. You should import these files into your chosen development environment. I'm going to be using Visual Studio 2015. As you can see, I've already imported these 6 files. Once you've imported them into your chosen development environment, spend a few minutes having a look at the files. They're part of a training course administration system. Hands-on.cpp contains the main program which has already been coded for you. In this program, there are currently errors. On line 14, a function called getPerson is called. This is an attempt to call a getPerson function which returns via a return statement a person which is then assigned to first. This is poor practice, but this exercise is designed to give you practice at writing different types of functions. The second call to getPerson on line 17 gets a person and returns the person as a reference parameter. The third call to getPerson on line 20 is passed a pointer to a person as a parameter, and the function getPerson modifies the person that's passed as the parameter. Finally, a function called printDelegates is called, which is passed an array of people and a count of the number of people and prints them out. The errors are that these functions are not yet implemented. Your task is to declare and implement the functions. Only two files are needed to modify in order to achieve this. The first one, hands-on-funcdecl.h, will contain the declarations of the functions. On line 5, it asks you to declare a getPerson function with no parameters that returns a person structure. On line 8, it asks you to declare an overload of the getPerson function that is void, i.e. returns nothing, but returns a reference to a person structure passed as a parameter. On line 11, it's asking you to declare another overload of getPerson that is again void, but this time returns a pointer to a person structure as a parameter. Line 14 asks you to declare a printDelegates function that is void, returns nothing, and takes an array of pointers to persons plus the integer number of persons in the array. The implementation file has function bodies within the file. However, it contains no function headers. So your task is to take the declarations that you declared in hands-on-funcdecl.h and insert them into the correct function implementations. So the comment here is a getPerson function with no parameters that returns a person struct. That will take the declaration that you've inserted on line 6, a getPerson function with no parameters that returns a person struct. Once you've declared all your functions and implemented them all, and there are only 4 functions to do, then you should go ahead and run your program. A sample solution is available for these exercises in files called handsonsolution.cpp, courseeventsolution.h, globalsolution.h, personsolution.h, hands-on-funcdecl-solution.h, and hands-on-funcimpulsolution.cpp. These files are in the working files folder so you can check your answers. I'm going to open a sample solution and show you what the output should be. That's what your sample output should look like. You don't need to enter any data yourself, that's all taken care of for you. All you need to do is implement the functions. In this lesson, I'll be starting off with a basic class definition and implementation for an employee class. Classes are normally split over 2 files in a C++ project. A header file contains the class declaration and an implementation file contains the code for the class or the implementation. This is done for several reasons. Firstly, it separates the declaration from the implementation. Secondly, any users of your class must have access to the class declaration, in other words, the header file. Finally, it could be a security or confidentiality issue. If you put code into your header file which is not forbidden, then that code will be exposed to any users of your class because they must have access to the header file. If you put confidential calculations or heaven forbid passwords into your header file, then these will be visible to the users of your class. Obviously, this isn't good practice. In my project, I've declared an employee class. The header file has been protected with 2 include guards. The #pragma_once on line 1 prevents the file from being included more than once in any compilation unit. Lines 2 and 3, the #if_endef and the #define, and also line 29, the #endif, prevent this file from being included. This is an older way of doing the #pragma_once. My class employee is then declared within the header file. I've split my class down into 6 distinct sections. I tend to use this method of declaring a class because it standardizes how a class looks. I have 1 public section for functions, 1 protected section for functions, a private section for functions, These are followed by a public section for data, and public data should be avoided wherever possible as it breaks encapsulation for the class. Protected section for data, this will only be used in class hierarchies and inheritance. And finally, a private section for data, which is the recommended place to declare all data in your class. There's nothing to stop you having more than one public section for functions, or in fact any of the other sections. And I could delete lines 16 through to 23, as I'm not currently using these sections. However, purely for documentation purposes and to illustrate best practice, I'll leave them in. In my public functions section, I've got 3 setter functions, setName, setEmpno and setExtension, and 3 getter functions, getName, getEmpno and getExtension. And these correspond to the 3 data items in the private data section at the bottom of the screen: name, employee number, and extension. In the CPP file or implementation file for this class, I've implemented each of these functions, and they've all been scoped to the employee class. That is, setName, setEmpno and setExtension and the corresponding getters all have employee : before the name. This means that they are in scope for the employee class, they are encapsulated within the employee class, and they have access to the private data members of the employee class. Classes may be inserted into a project in a number of ways. You can either insert them manually, inserting a header file and a CPP, or in Visual Studio 2015, there is a project add class, which guides you through the steps of creating the class, pops up a dialog which asks you various questions, and then creates a complete header and CPP definition for the class. My class overview.cpp file is a simple main program which is designed to test my employee class. I've created an employee called worker, called setName, called setEmpno, called setExtension, and then use cout to call getName, getEmpno and getExtension. If I run this program, this is my output. And as you can see, I setName Simon, setEmpno 12345, setExtension 9999, and that's exactly what my output gives. In this lesson, we're going to look at class modifier and query functions. Using our employee class example, we're going to add a bit of best practice to our class definition. Looking at this class, we have 3 setter functions, setName, setEmpno and setExtension, and 3 getter functions, getName, getEmpno and getExtension. It's reasonable to expect that any function that requests data from our class, which gets data or returns data, might be called a query function. But it's also reasonable to suggest these functions will not modify class data. We can therefore easily class our setter functions as modifier functions and our getters as query functions. To formalize this definition, we should declare all of our query functions, getName, getEmpno and getExtension, as const member functions. The keyword const should be applied to the header for the member function in both the declaration, as shown here, and also on the implementation, as shown here. The effect of doing that is to make a function a query-only function. This means that class data cannot be modified within a const member function, a query function, as shown on line 26. That concludes this lesson on modifier and query functions. In this lesson, we'll be taking a basic class definition for an employee class and adding initialization to it in a number of different ways. Taking our employee class as shown, that currently consists of 3 modifier functions, 3 query functions, and 3 private data items, if we try to use this class like this, by creating an employee and then using the get functions to display the data, we encounter a problem. When we run the program as shown, we get nothing for the name and 2 uninitialized values displayed for the employee number and the extension. If we'd had any pointers in our class, the results could have been much worse. Just like ordinary local variables, C++ doesn't initialize the members of a class. We have several options available to us. On modern compilers, we can use in-place initialization or in-situ initialization, and similarly for the employee and the employee number and extension. However, this is fixed. If sometime later we decide that the default extension number, rather than being 0, is for example 1234, in order to change that, we'd have to go into our class definition, change the default initialization, recompile, rebuild, and redistribute the application to all of our clients. The second alternative is slightly different. We could use a series of functions. I've called the first one initialize with a Z, and the next two are initialized overloaded functions spelt with an S. This illustrates completely the problem with using this method. Firstly, the user of my class needs to know what the function is called. It could be any name. It could be setup, startup, initialize, any name you could possibly think of. Also, and more importantly, the user of my class must remember to call this function in order to do initialization. There is a far better solution. The object-oriented model is designed to reflect real life. In real life, when a child is born, that child is given a name. It's also given various other attributes such as health service numbers. That enables that child to go on through life and to claim benefits, to get a job, to get a passport, etc. In fact, by law in many countries, this kind of initialization for a human being is compulsory. OO is designed to reflect real life. There is an OO law that says that all objects must be initialized. In the case of OO, objects are initialized through a special function called a constructor. The laws of OO state that a constructor must always be called. However, my class employee at the moment doesn't appear to have one. If you don't provide your own constructor, the compiler will provide one for you. You never see it. It's effectively defined by the compiler as an inline function with no parameters and which has no body. However, the function will be there and it will be called. We can take advantage of this automatic compulsory initialization by supplying our own default constructor. Constructors have a special format. They are the same name as the class. They take no parameters in the case of the default constructor and return nothing, not even a void. Line 8 shows a default constructor. Constructors can also be overloaded. These constructors obviously have to be implemented because they're members of the class. Here's a couple that I prepared earlier. This is the default constructor. At the moment, this default constructor illustrates the initialization of my employee class in two different ways. Lines 6 to 8 use assignment within the constructor body to initialize the data members of my employee class name, employee number, and extension. This is not normally considered best practice. The best way of initializing members in a constructor is to use something called colon initialization. Line 4 illustrates this type of initialization. Colon initialization is done by placing a colon after the constructor header, followed by initialization for each of the data members that you wish to initialize. You don't have to initialize all members. In this case, I've chosen to. Lines 10 to 16 show my overloaded constructor. This is very similar to the default constructor, except that the constructor now takes parameters for the data members I wish to initialize, and it still uses a colon initializer, but in this case I've chosen the universal initialization syntax available on modern compilers. I can call my constructors like this. Worker 1 will automatically call the default constructor. In the case of line 8, I'm constructing another worker, worker 2. This will call the constructor with 3 parameters, the first of which is a string, and the second 2 are integers. This will call the overloaded constructor that I declared earlier. Finally, we'll look at one more option. Worker 3 is very similar to worker 2. However, there are subtle differences. As it stands at the moment, both of these statements on line 8 and line 9 will compile. If I make a minor change to line 8 and compile my program, you can see that I now have a warning. The warning is on line 8, and it states that I'm trying to convert a double to an integer, and that there may be possible loss of data. Let's try the same thing with line 9. This time, I've still got warnings and errors. However, the warning that was on line 8 when I converted from a double to an int has now become an error. When constructors are called using curly braces syntax, it expressly forbids any narrowing conversions. If round brackets are used, parentheses, as shown again on line 8, that will only generate a warning. However, none of this is really very good practice, types should be as consistent and explicit as possible. This lesson introduces the default and delete keywords. Two new keywords have recently been introduced to the C++ language that are connected with constructors and other compiler-provided functions. The compiler will provide certain functions for classes such as constructors if you don't provide them yourself. In the example I've got in front of me, I'm attempting to create an employee object called worker. However, there's an error. I'm attempting to construct the worker using the default constructor, but my class has no default constructor provided. In this instance, the compiler will not provide one because I've started to provide overloaded constructors myself. The compiler will only provide a default constructor if no other constructors are defined to the class. The default keyword can be used to force the compiler to provide its own implementation for the default constructor, and it's done in this way. By declaring the default constructor and saying equals default, this will cause the compiler to generate an implementation for the default constructor, which it wouldn't otherwise do in this situation. And as you can see, my employee worker can now be constructed using the compiler provided default. There are several other functions that can be defaulted in this way. These will be discussed elsewhere in the course. Delete is the opposite of default. Coding the keyword delete on a function explicitly says, I do not want the compiler to provide this function. In this case, the delete keyword is a little bit superfluous because the compiler won't provide a default constructor anyway. But there could be instances where you don't want the compiler to generate default functionality for you. In that case, you declare the function and use the delete keyword with it. In other lessons, we've learned about overloading and class constructors. In this lesson, we'll look at a maintainable way of specifying multiple constructors. Let's look at an example. On the screen, I have a car class. I've used an enum for the colour of the car, and the car class is called class CarUnchained. The class has 4 constructors. The first constructor is the default constructor, followed by 3 constructors that initialize different data members of the class. The data members are the primary colour, the engine size, and the price of the car. The constructors are coded like this. The default constructor, on lines 3 to 9, initializes the colour to red, the engine size to 2000, and the price to 20,000. In this example, I've used universal initialization as part of a colon initializer list to do that. The second constructor initializes the colour to a colour passed into it, the engine size to a default 2000, and the price to a default of 20,000. And the last 2 constructors take the steps a little bit further by initializing colour and engine size and defaulting price, and finally initializing all 3 to the parameters that are passed into them. This is fine and it works, and until recently this was the way you had to do this type of initialization. However, note that initialization actually takes place in each of the constructors. It's now possible for a constructor to call another constructor within the same class. This can be used to simplify the code we've looked at. The class is declared in exactly the same way, with 4 constructors. However, the implementation is much simpler. If we call the default constructor on line 3, rather than initializing all the data members within the default constructor, we simply call the next constructor in the chain and pass it the default of red. That in turn calls the next constructor in the chain on line 7, passing it the red that's passed in and a default of 2000 for the engine size, and so on down the line. Actual initialization of data members only takes place in the final constructor on line 13 in the initialization list. This is a big change. The responsibility for actually doing the full initialization is delegated down the chain to the final constructor. No matter where you enter the chain, any parameters that you've supplied are automatically passed on in the chain, along with any defaults to the next constructor in the chain. Potentially this makes your code more maintainable, as initialization takes place only at one point. It all looks very sensible, if a little hard to follow. However, there are other performance implications. Instead of calling a single constructor, as in the previous example, with this example, you now call between 1 and 4 constructors in a chain. In situations where you need fast performance, this can be quite an overhead. Again, it's down to you to decide what is most important in your application. Is it performance, and to some extent better readability, or is it maintainability and code size? That concludes this lesson on constructor chaining. All of the code used in this lesson is available in the working files folder for this lesson. Having looked at class construction in some detail, this lesson will deal with what happens at the opposite end of an object's life cycle when an object is destroyed. An object can reach the end of its lifetime in various different ways. On lines 3 to 6, we have a function called doSomethingWithAPerson, which is passed a person destructor object P by value. P will go out of scope and hence get destroyed at the end of that function. On lines 8 to 12, I've created another function, createAndUsePerson, which creates a person destructor object within the function, and again P2 goes out of scope and gets destroyed at the end of the function. Another way an object can go out of scope is in the example in main on lines 14 to 21. In this function, I create a pointer to a person, and I new the person destructor object. In other words, I instantiate an instance of person destructor. I then use that object, and finally, when I finish with it on line 20, I delete the pointer. P3 then goes out of scope and gets destroyed at that point. This can cause problems. Let's take a look at my person destructor class. I've kept it very simple. Within this class, I've got one data item, which is char asterisk, called name. I've got two constructors, a default constructor and an overloaded constructor, and I have a function called usePerson. The implementation for these functions is the default constructor allocates some memory at the name pointer and copies in the name anonymous into that pointer. The overloaded constructor takes the name into the class, into the constructor, works out how much memory it requires, allocates enough memory for it, and then copies the name passed in into that memory. The usePerson object doesn't do anything in my class. So what happens at the end of the object's lifetime? Well, I've allocated memory on the heap in the constructor. There is no corresponding deallocation. My class therefore leaks memory. In order to prevent this, in fact, whenever you have any resources which must be deallocated as part of a class, we can take advantage of destructors. Just like constructors, destructors are guaranteed to be called. Let's declare a destructor in my class. Destructor, just like a constructor, has no return type. Its name is the tilde character, followed by the class name, and an empty parameter list. Unlike constructors, destructors cannot be overloaded. Because I've declared a destructor, I should implement it. It must be scoped to the class, just like the constructor, and my destructor must delete any resource allocated in the constructors, in my case, the name. That's my destructor. Now, resources are allocated in the constructor, and any resources within the class that are held entirely within the class are deleted in the destructor, and my class is memory safe. Destructors are typically used for this type of memory deallocation. They can also be used for releasing other types of resources, such as database handles and so on. Generally, if you allocate any resource in a constructor, then you will need to code a destructor. This lesson will look at inlining and the pros and cons of using various techniques. The first type of inlining we'll look at is a historic type of inlining which generally should not be used in C++, even though it does work. On line 5, I declared a macro called add2. This is a hash-defined macro which uses the preprocessor. On lines 20 through to 22, I've called the add2 macro. That macro will be expanded in line on each of the cout statements. However, as you can see here, it has a distinct disadvantage in that there is no type associated with the add2 variables. Macros coded with the hash define are not type safe. The next type of inline that we'll look at is on lines 7 to 10. In this function, I've declared the function as inline. It's a function which adds to int. I've used the inline modifier to request that the compiler inlines this function. This function is used on lines 25 to 27. This is a direct equivalent of the hash-defined macro, except that in this case the macro is totally type-safe because the inlined function has specific types on its two parameters. There's one further form of inlining, that's inlining of class members. In this file I've declined a class called personInline, and I've used two different techniques to inline functions. The first inline methodology used within the class is on lines 10 to 13. The function implicit inline usePerson is declared and coded within the class header file. When functions are coded within the header file in this way, they are implicitly inline. On lines 14 to 17, I've explicitly declared the function explicit inline usePerson as inline using the inline modifier. It's also been coded within the header file. On line 18, I've declared a function explicit inline usePerson again. This time I've again used the inline modifier, but the function is coded in the CPP file, again using the inline modifier. Those are the three ways of declaring inline functions within classes. At this point I should probably also point out that inline is not a command to the compiler. It is not imperative. When the compiler finds an inline request, either implicit or explicit, it will generally do a cost-benefit analysis on the function concerned. If it can see a benefit in inlining the function, it will do so. Certain functions cannot be inlined. Functions which cannot be inlined are functions which call themselves, or recursive functions, functions which are called via a pointer to a function, this will be explained later in the course, and finally, functions which the compiler regards as too complicated, too large, or have no benefit in inlining. This lesson will be looking at static variables, and in particular static class member variables and static class member functions. Static variables declared within a function, as in the function on lines 7 to 12, have local scope or visibility, that is, they can only be seen and used within the function in which they're declared. They also have static persistence or lifetime. Their lifetime is effectively the lifetime of the program. On lines 16 to 19, I have a for loop which calls the counter function 5 times. The first time counter is called, the count variable will already be in existence. It's created outside the function. It is also initialized by the compiler to the default for the type. So the first time I call counter, the value of count will be 0. Counter then increments count, and this count is returned. As we leave the function, the variable count is not destroyed like any local variable would be. Instead, its value is held and kept until the next time we call counter. On line 18, we see out the value. The value that was returned for the first call will be 1. We then go round the loop again, call counter again. This time counter already has the value 1 held over from the last call. We increment it to 2 and return it, and so on for all 5 iterations of the for loop. This code produces the following output. We get the values 1, 2, 3, 4, 5. Let's take a look now at another type of static. This time we're going to look at the static member of a class. I've declared a class, employee static, a very basic class, but it will serve to demonstrate static member variables. My class has 2 functions, a default constructor, and a getEmpNo function. The class has 2 member variables. The first one is int empno. This is a class member variable. It is created for every instance of the employee static class that we create. It sometimes says to have instance scope. The variable on line 9 is declared as a static int. In the case of static variables, the static keyword is a placeholder within the class to say that we're going to create a static variable for this class. It doesn't create any storage on instantiation. Whereas class member variables are instance scope, static member variables are sometimes said to be class scope. There is one instance of a class scope variable for all instances of the class. Let's have a look at how this class is implemented. The first thing to note is line 3. This is the storage for our last empno variable. As you can see, it's been scoped to an employee static class. It's of type integer, and in this instance I've initialized it to have the value 10,000. Static class member variables are initialized to their default for the type. In this case, the default initialization for last empno will be 0. My constructor on lines 5 to 8 simply sets empno to ++ last empno. In this case, I'm setting a member variable, an instance variable, to the value of a static variable and incrementing it. What this effectively does is, every time I instantiate a new employee static object, I get another incremented impno. This means that I will get unique employee numbers no matter how many classes or objects of the class employee static I create. I've also, to prove this, coded the employee static : getEmpno function, which returns the employee number, the instance variable, instance scope variable. Let's have a look at some code to take advantage of this class. In this case, I've created two employee static variables called me and you. Each time I create a new instance of employee static, it should call the constructor, which increments the static variable and stores the employee number in the class member variable, which is instance scope. I should get two different employee numbers for me and you. To prove this, I've got two couts. Let's run this code and see what happens. That's exactly what I get. The last employee number was initialized to 10,000. The first employee that we created, which was me, incremented that last empno to make it 10,001 and stored the value. The second employee that we created incremented the last empno again to make it 10,002 and stored the value in the employee number. So as you can see, static member variables can be used to create unique values such as employee number. They also have another use. In this case, I've created a class called personStatic. It has a constructor and a destructor. We would normally put other class member functions into the class. I've added one other one, a static int getNumPeople. This is a static function. Static functions can only access static data within the class, as we'll see in a minute. I've also got a static int numPeople, and if I wanted other class member data, I've put that in the private section as well. Let's take a look at the implementation for this class. First of all, on line 3, we have the numPeople static variable. No initialization this time, so it will be initialized to its default value of 0. The constructor increments numPeople. The destructor decrements numPeople. Using constructors and destructors in this way, if I can get hold of the value of numPeople, I can always have an accurate measure of the number of people that I've created. So for example, if I was creating a course administration system and the maximum number of places was 8, this would be a very simple way of keeping track of how many people I have on my course. Every time I create a delegate, I'd increment the static variable. Every time a delegate cancels, I'd decrement the static variable. And at any time, I can get hold of that data using a static member function. The static member function in my case, getNumPeople, is coded on lines 13 to 16, and it simply returns the value of the static variable. Let's see how that's used. So in this case, I'm going to use my static class for resource counting, and my resource is people. On line 32, you can see I've got a cout, which calls personStatic : getNumPeople. This may look a little odd, but this is the usual way that we call static member functions. We don't call them on an instance of the class, although you can do so. Instead, we call them on the class itself. Because I haven't created any people at this point, my getNumPeople should return the 0 value of numPeople. I then create a personStatic variable called him. This instantiates the class, the constructor is called, and the number of people is incremented within the class. On line 34, I've actually used the class instance, him, to get hold of the numPeople and call the getNumPeople function. This is just to prove that it is possible, but as I said a minute ago, it's normal to call getNumPeople, or a static member function, on the class rather than an instance. I then, on line 35, create another new person. This time it's a pointer to a person. It makes no difference. In this instance, the default constructor will be called. Again, it will increment the number of people variable. I then cout personStatic getNumPeople. I should now have 2 people. After deleting the pointer on line 37, the destructor should be called. The destructor decrements the number of people, which should take me back down to 1 person, him in my example. Just to prove that, again, I see out the number of people. Let's run this code and see what the output is. We'll have to compile it first, as usual. And we can see that the first getNumPeople returned 0, which is correct. It was before any people were created. The 1 is returned after we created him. 2 is created after creating her. We then deleted her, and 1 is the result. This hands-on lesson will give you a chance to practice what you've learned in the last few sections. The training administration system used in previous practical exercises has been updated to use classes rather than structures. You will need to import CourseEvent.h and CPP, Person.h and CPP, and Global.h, and Hands-on.cpp into your preferred development platform. A list of 4 tasks for you to complete is given in Hands-on.cpp as shown on the screen. Some of the tasks, as in Task 2 and Task 3, are expanded on in the files mentioned in the task. So for Task 2 it says see Course Event Implementation file, that's CourseEvent.cpp, and tasks are expanded there. As always, these files and a sample solution can be found called Person Solution.h and CPP, etc., and they can be found in the Working Files folder for this lesson. In this lesson, we're going to look at some issues with object construction. Let's take a look at a fairly simple example class. I've defined a class PersonConstructionIssues that has various public functions and a single private data member. The type of the data member is not important. What is important with these issues is that it's a pointer that is dynamically allocated within the class. The first function is a default constructor. The second function is an overloaded constructor, and I've also coded a destructor in this class. And finally, a query function to return the value of the name used in the char asterisk pointer. Let's look at the implementation for this class quickly. The constructor allocates some memory to store the name. In this case, I know exactly what I'm putting into it because it's a default constructor. I'm going to set it to anonymous. So I know the length of anonymous is 9 plus the null terminator for a string. So I need 10 characters. So the default constructor allocates the memory and copies the name anonymous into that memory. The overloaded constructor is very similar, except that in this case the name is passed into the constructor, so I have to determine the length of the name, allocate an additional character for the null terminator, and then copy the name that's passed in into the name stored within the class. Because I'm allocating memory in my constructors using new, I should also delete that memory in the destructor using operator delete to ensure that there is no memory leakage within my class. The destructor is defined on lines 17 to 20 and simply deletes the name memory. GetName is a query function which simply returns the name pointer. Let's look at some uses of this class. In main, I create an object from the PersonConstructionIssues class called me1 and use the overloaded constructor to set the name to Simon. If I want to create another object exactly the same, this is one way of doing it. I've created another object which again calls the overloaded constructor and is passed the same parameter Simon. I can then see out me1.getName, that should print Simon, and see out clone1.getName, that should also print Simon, which is the case. Let's look at the lines of code on lines 16 to 20. I've done something very similar here, except that on line 17, rather than calling the overloaded constructor and passing the same parameters, I've called a special constructor. In this case, I've passed the object created on line 16 into a special constructor called a copy constructor to create a new object. However, if we take a brief look at my class again, the only constructors I've got defined are the default constructor and the overloaded constructor. There is no constructor in my class which takes an object of type PersonConstructionIssues as a parameter. The answer is in the comment there. The compiler will provide a copy constructor for you if you don't define your own. Let's see what happens when I run this. Well, it sort of half works. The first 2 displays of Simon are from my first set of code, which was perfectly okay. The second 2 displays are from my new code. This suggests that 2 objects have been created. They both have Simon as their name. However, as you can see, I've got a runtime failure. In order to diagnose this, we'll look at exactly what's happening within the compiler. To avoid confusing the issue, I'll comment out this code for now. The first thing that I do is create a me2 that calls the overloaded constructor, this code here. That creates a me2, takes the name Simon into it, works out how many characters the parameter Simon takes, which is 5, adds 1 to it for the null terminator, 6, allocates some memory for that Simon, and then copies the parameter Simon into that memory. Construction of me2 is now complete. What about line 17? Well, the compiler provides the copy constructor. We can't see what the compiler's doing with this copy constructor, but let me tell you exactly what it does. It copies every member of me2 to the corresponding member in clone2. My class has one data member. It copies the pointer to the name from me2 to the pointer to the name in clone2. No new memory is allocated. When I see out me2, it's using the pointer to the Simon memory within me2. When I see out clone2, it's using the pointer to the memory held within clone2, which points to the same memory as in the me2 object. That in itself is not an error. It doesn't cause any problems. The problem occurs when we get to the end of this function and destruction starts to take place. The first object that will be destroyed is clone2. The destructor deletes the memory for name. The second object to be destroyed will be me2. The destructor is called. That again attempts to delete the memory for name. However, since both pointers were pointing to the same area of memory for name, the second delete causes the error. We'll look closer at how to resolve these issues in a later chapter. Let's take a look at another case. First, let's comment out those lines and look at the lines 22 to 26. At first sight, these look exactly the same as lines 16 to 23 except for line 16 to 20. The only difference is that rather than calling a copy constructor, as on line 17, now I'm assigning me3 to clone3. When the compiler sees this, it actually calls the copy constructor. In other words, this code has exactly the same problems as lines 16 to 20. In order to possibly resolve this situation, I've created another class. In previous lessons, we saw that there was a keyword delete, which we could use to suppress the compiler generation of certain functions. For example, if we wanted to suppress the compiler generation of a default constructor, we could say equals delete on the end of it. In this case, I've supplied a copy constructor, or at least a declaration of a copy constructor. This will be covered in more detail later in the lessons. But instead of actually coding it, I've said equals delete. This will cause the compiler not to create its default copy constructor. If I now uncommented out these lines and look at this code, I'm using the person deleted copy constructor class, me4, for Simon. That's perfectly okay, it's calling the overloaded constructor. The next line, clone4 Simon, is also calling the overloaded constructor, and that code will work perfectly okay. However, on line 34, I'm attempting to call a copy constructor to create a clone5 passing a me4 into the copy constructor. That generates a compiler error, which is basically telling me that the copy constructor has been deleted, therefore I can't reference it. That prevents copy construction. That's a possible solution, however, it can have its own drawbacks. On lines 36 to 37, I've created a vector. As far as we can see, this code simply creates a vector of 3 people and attempts to push me4 onto the end of the vector. There are no errors there as far as we can see. If I build this, or even compile it, I get an error. Without going into too many details, the vector uses the copy constructor behind the scenes. There's no indication of it doing this, therefore you need to be careful if you delete compiler-supplied routines. In this case, this code would not work, even though it looks perfectly okay at first sight. Solutions to these problems will be given in a later lesson. In previous lessons we learned that the compiler generates something called a copy constructor, which allows us to perform construction as shown on line 16. However, we've also learned that the copy constructor supplied by the compiler does a shallow copy. If the class contains pointers which are allocated to memory, on the heap in particular, the compiler provided copy constructor is not sufficient. It merely copies the value of the pointer rather than taking a copy of the memory at the pointer. This can lead to all sorts of problems. We've looked at deleting the copy constructor provided by the compiler using the equals delete method, and seen that other functions such as vectors and in fact many of the other STL classes use the copy constructor. So if we delete it, a deleted copy constructor can cause other functions to fail. In this lesson we're going to look at defining our own copy constructor. Rather than just give you the format of the copy constructor, I'm going to work it out from scratch. What we want is to define our own copy constructor. I'm going to place it on line 7. What do we know about the copy constructor? Well, initially we know that it's a constructor. All constructors must have the same name as the class. We know that it takes parameters. If we go back to our code that calls the copy constructor, we can see that the copy constructor takes a parameter of an object. The object is of type className, the same class. However, there will still be issues with this. At the moment, the person CCP is passed by value. By value causes copying. This is a copy constructor. We don't want copying to take place as we call the copy constructor. That can lead to other problems. How do we stop copying? We pass a reference. Finally, if we're taking a copy of an object, in this case me2, we wouldn't expect me2 to be changed by the process of copying. In this case, it's clone2 that will be modified. Me2 must not be modified. How do we prevent modification of references? We pass a const reference. And in fact, that is a completely correct definition of a copy constructor. It's class name and then pass as a parameter a const reference to the class. In my case, the parameter is called p. I've already coded this in the implementation file for this class. My copy constructor is on line 17 to 22. It looks very similar to the overloaded constructor, except rather than use the name passed as a parameter, it uses the name in the object passed as a parameter. In my case p, so it uses p.name. As you can see, my copy constructor now allocates new memory for the name and takes a totally separate copy of the name passed into the local name variable. Returning to my main program and using fairly straightforward code, we have two person CCs created, both by calling the overloaded constructor. That's never been an issue and should work perfectly okay. Lines 15 and 16 create two new objects. Me2 is created using the overloaded constructor, and clone2 is created as a copy of me2. This should call our newly defined copy constructor, and it should all work okay. Finally, on lines 21 to 28, we have the copy constructor called again for clone3. When the compiler sees clone3 equals me3 on a declaration, it will convert this to call the copy constructor. Since we've now defined our copy constructor, this code should work perfectly satisfactorily. Finally, we said that the vector could cause an issue if you don't have a copy constructor defined. So I've again defined a vector called people. Initially, it creates a vector of 3 people, and then finally I push back one of the people created before, in this case me3, onto the end of the vector. If I build my solution, everything's fine, there are no errors at all, and debugging my code, running it, works perfectly okay. There are no nasty errors due to copy construction. Everything works fine. So basically we can formulate a sort of rule here. If your class contains pointers which are allocated and deleted within the class, then it's highly likely that you will require a copy constructor. You may not know when you need a copy constructor. The STL in particular uses copy construction behind the scenes, and there may well be other third-party products which use copy constructors too. Therefore, if you're in any doubt, ideally you should provide one. In this lesson, we'll look at when copying occurs and how to minimize copying. To illustrate this, I've created a very basic class called copy, which contains a default constructor, a destructor, and a copy constructor. The data in the class is a pointer to some memory. It's called large memblock. Ultimately, this pointer will point to a large area of memory on the heap. There's also another variable which contains the size of the memory block that we're going to create. If we go back and look at the constructor, the default constructor allocates 1 million integers on the heap. In other words, it's allocating 4 million bytes. The memblock size variable is set to the size of the area in integers, which is 1 million integers. The destructor deletes the memory block. Thus my memory handling within my class is correct. I use some memory in a constructor and delete it in a destructor. No memory leakage will occur. My copy constructor on lines 25 to 32 takes a new memory area, copies the large memory block from the original object into the new memory block for the current object. memcopy is a C standard library routine which copies memory, and then I also move across the block size. In other words, if I take a copy of my object, what I actually end up with is one object, the source object, with 4 million bytes of integers allocated, and a copy of the object with another 4 million bytes allocated. Let's look at how we use this object and where copying occurs. On lines 59 to 61, I create 3 objects. One is a straightforward object. It will call the default constructor. It will allocate 1 million integers or 4 million bytes. 2 is a copy of 1. The copy constructor will be called. It will allocate another 4 million bytes or 1 million integers, copy the memory from 1 into 2. 3 also calls the copy constructor. This is assignment, but it's assignment on declaration, which the compiler converts to copy construction. Therefore 3 will have another 1 million integers allocated, which will be a copy of the 1 million integers in 1. On line 64 I call a function, doit1. Doit1 is defined on lines 46 to 49. Here an object is passed into doit1 by value. Passing by value causes a copy to take place. In order to do that copy, the compiler will call the copy constructor. So whilst I'm in doit1 between lines 47 and 49, the local copy, C, will have another 1 million integers allocated. Once I leave the doit1 function, the destructor for C will be called as it goes out of scope, and its memory will be deallocated. On line 65, I call a function doit2. Doit2 has no parameters, so there's no copying of parameters, but it does return a local copy x. Because when I reach line 55 x goes out of scope, it cannot return x directly, it cannot return x as a reference, therefore it has to take a copy of x and return that. As it does the return, a new temporary copy of x will be taken. It will allocate 1 million integers, or 4,000 bytes. That will get returned by doit2. Line 65 doesn't actually make any use of the returned value, so it will go out of scope and be destroyed. But a copy is definitely taken. Finally in this code, I've used 3 standard template library objects. I've used a vector, a queue, and a list. I've created vectors called V, created a queue called Q, and a list called L, and onto each of them I've used their push function. In the case of a vector and a list it's push back, in the case of a queue it's simply push, to push a new copy of something. I've used universal initialization. Because the type of the vector is of type copy, the compiler can deduce that what I'm actually pushing is a default copy. So within the parentheses for v.pushback on line 68, it will create a new version of copy and push it onto the back of the vector. This will call the copy constructor yet again. So in my example here, I've got copy construction on line 60, copy construction on line 61. When I call doit1, it will create another copy. When I call doit2, the return will create a copy. And I've got 3 STL functions, standard template library functions, which will also do copies. Within my copy constructor, I've coded a cout. This isn't good practice, but for the purpose of this exercise, it will prove that I am actually calling the copy constructor. If I now run my program, we can see that I'm calling the copy constructor 7 times. The first 2 are on creating copies of the object. The third one is on the call to doit1. The fourth one is on the return from doit2. And the last 3 are on the vector, the queue and the list respectively. My aim is to actually reduce copying as much as possible. So my benchmark is to remove as many of these 7 copies as possible. One way I can do that is to pass parameters into functions by either reference or via a pointer. So I could make this a reference to a C, or I could pass in a pointer to an object. References and pointers will not be copied. Recent modifications to the C++ language have introduced a new feature, which helps to reduce copying. Move semantics are really beyond the scope of this course. However, briefly in this situation I'll explain the move constructor. In some situations when we're taking copies, we can actually move the item rather than copy it. For example, in my vector queue and list, I create a temporary copy within the parentheses. That copy is never used again. As soon as I exit statement 68, that copy is destroyed. Therefore, it makes no sense to copy the memory within that object and then immediately delete it. It would make far more sense to simply move the memory, or in other words, take a copy of the pointer. That's what the move constructor does. If we compare the copy constructor with the move constructor, the copy constructor news a new copy of the memory and copies the memory into the area that's just been created. In the move constructor, we don't do any newing of memory and no copying of memory. Instead, we just assign the pointer from the source memory to the destination or the copy memory. In this instance, I've also set the source memory pointer to null. If I run my program now with the move constructor in place, this has to be copying. So I would expect that to still call a copy constructor. This too is definitely copying. It's definitely going to call the copy constructor by assignment. These, however, are potentially open to using the move constructor. When we code our program, we don't have to tell the compiler specifically to use the move constructor. The compiler will detect when a move constructor can be called. The STL in particular is move constructor enabled. The compiler will call the move constructor wherever possible. Remember, when I had the copy constructor, I called it 7 times. As you can see, I'm still calling the copy constructor 3 times, but now I'm using the move constructor in 4 instances. Copy constructor will be called here and here. That's the first 2. The copy constructor will also be called here. Because I'm passing 1 into do it, I may be using 1. 1 pre-exists. It's not temporary. However, when I return from do it to, X is local, it's only temporary, therefore it can move anything that was into X into the copy that's returned, because X is no longer required. That's the first instance where the move constructor will be used. In the case of the vector, the queue and the list with their push routines, I'm using a temporary object. That object is never used again. Therefore, the compiler determines that any memory that's within those objects can simply be moved and not copied. Therefore, the move constructor is called on lines 68, 71 and 74. In this lesson, we'll be looking at writing conversion constructors. Sometimes it can make sense to construct one object from a similar but not the same type of object. Constructing one object from exactly the same type is called copy construction. Here we're going to look at creating one object from another object of a similar type. This is called conversion construction. On the screen I've got 2 different classes defined. On the left is a person class, or person conversion class. It contains 3 data members: string, name, int age and char sex. On the right of the screen I've got another class, employee or employee conversion.h, which contains a very similar set of data members. It also contains a string name, int age and a gender sex. The 2 classes are not identical in that the person class contains a char sex and the employee contains a gender sex, which is of type enum gender. The employee class also contains an int employee number. These classes are sufficiently similar for me to be able to make the statement that it would make sense to be able to create a person from an employee. In doing so, we simply have to copy the name across from the employee to the person. The sex has to undergo a little bit of conversion, and we can simply ignore the employee number. If we wish to convert an employee to a person, the conversion must be done in the person class. And in this class, I've added another constructor to my class called person conversion. This particular constructor takes an employee as a parameter. Just like all other constructors in the class, the constructor is called the same as the class name. The conversion constructor takes a single parameter of an employee object. Objects should not be passed by value, they should be passed by reference, hence employee conversion reference. And also, we wouldn't expect the conversion to a person to affect the employee that's being passed in. Therefore, we pass a const reference to an employee. Let's look at the code for this function. The standard conversion constructor simply takes the three items passed in, name, age and sex, and uses universal initialization to construct a person. However, with the person conversion constructor, we need to do a little bit more work. Typically, a person conversion constructor cannot use a colon initializer list because it has to do additional work and also get information directly from the employee. You might think that line 8 would work. In other words, copy the employee's name into the person's name. However, we don't have access to the private data members of the employee. They're encapsulated with the employee, it's a totally different class, and therefore that syntax is not allowed. We could make it work. We could use a feature called friend classes. Friend classes are allowed direct access to the private data members of classes where friendship has been established. However, this totally breaks the encapsulation rules of object orientation and is very frowned upon. My employee class has actually got get members to get the name, age and sex. Therefore, I can use this methodology to copy the data across. On lines 10 and 11, I directly access the getName and getAge members to copy the name and age into the person class. As I mentioned earlier, the sex member requires some conversion. I've done this using a switch statement. So I get the sex, use a case statement for male to set the sex to M, female to F, and if it's not male and female, then I set the sex to question mark in the person class. Let's have a look at how we might use this feature. In this example, I've got a function called doSomething which takes a person as a parameter. The code within the function doesn't matter. The conversion is going to take place when we call the function. I've created an employee object called Fred, which is initialized to Fred Flintstone, age 30, gender male, and employee number 1234. I've also created a person object called Mr. Flintstone and passed it Fred as a parameter. This will directly call the conversion constructor. This is explicit conversion. Fred will be converted into a person. On line 15, I've called doSomething. doSomething takes a person as a parameter. The type of object that I've passed into doSomething is an employee. The compiler now implicitly knows that I've declared a conversion constructor which takes an employee as a parameter and returns a person. It can therefore do implicit conversion of an employee into a person, and it does it automatically when we call the function. Obviously, it wouldn't be meaningful to construct objects from totally diverse and dissimilar objects. You wouldn't, for example, want to construct a pen from a dog object. However, where the objects are sufficiently similar, this technique can be used. In this lesson, we'll look at type conversion in C++. Type conversion is also called casting. C++ has three ways of performing type conversion. The first way is illustrated on lines 37 to 41. We have a double variable d, which contains the value 99.99, and an integer x, which is uninitialized. If we attempt to assign d to x, then at the very least we'll get a compiler warning, telling us that we're performing a narrowing conversion and there will be some possible loss of data. Code should never be released containing warnings. One way of getting rid of this warning is to perform an explicit cast to tell the compiler this is what we really intend. In the cast on line 41, we're using a C cast. This type of casting is inherited from the C language. Everything that works in C still works in C++. However, C++ is far superior to C, and C casting should never be used. On lines 43 to 47, we have the second type of casting. Again, we're using a double, this time called e, with the same value 99.99. We have another integer, y, which is uninitialized. We're trying to do exactly the same, assign the double to the integer. As in the first instance, this will also generate a compiler warning, telling us that we're doing narrowing conversion and there will be a possible loss of data. As with the C-cast, we can suppress this warning by doing an explicit cast. We do this on line 47, and this time this is a C++ or sometimes called functional cast. It actually looks as if we're calling a function called int, passing it the double e, and assigning the resulting integer to the y variable. Both of these casts will work, however they're both inherently unsafe. The code following this shows this unsafe feature. On lines 49 to 52 I've got 4 variables declared. An integer a which has the value 123, a double b which has the value 99.99, a pointer to an integer, pa, which is pointing to a, it's given the address of a, and on line 52 a pointer to a double, pb, which is made to point to b by giving it its address. Line 54 is using a C-cast to convert our integer a into a pointer to an integer. This will make our pointer to an integer point to the address 123. It's totally unsafe and should never be used. In the second example, on line 55, we have a pointer to a double which we're casting into a pointer to an integer. We're changing the type of the pointer. This does nothing to reformat the memory at the end of the pointer. It purely says that the pointer to a double is now a pointer to an integer. The disadvantage of doing this is that a pointer to a double will point to 8 bytes of memory. A pointer to an integer will only point to 4 bytes. Again, it's a totally meaningless piece of code. Now we'll move on to the third type of casting. The third type of casting consists of 4 casting operators. These are static cast, dynamic cast, reinterpret cast, and const cast. First of all, we'll look at static cast. The static cast operator is illustrated on lines 57 and 58. Static cast is safer than C and C++ functional casting in that it does compiler time checks. On line 57, I am attempting to convert a double into an integer. As far as static cast is concerned, this is fine. If I, however, attempt to convert a pointer to a double to a pointer to an integer, static cast determines that this is not safe. Therefore, it generates a compiler error. If you look at the line 55 just above it, it's exactly the same conversion that was allowed by the C-cast. It's not allowed by static cast. On line 61, I've attempted to use a dynamic cast. I've attempted to cast a double to an integer. Dynamic cast does a few compile time checks. In particular, this check will return an error that dynamic cast must be used with a pointer to a class or a void pointer. It cannot be used to convert this built-in data types. Similarly, on line 63, I've used it with pointers. However, in this case, it's a pointer to a double being converted to a pointer to an int. And again, the error that I will get from this is that it must be a pointer to a class or a void pointer. Dynamic cast is primarily used in situations where you don't know the object type. This is usually when you're using polymorphism and an inheritance hierarchy. Unlike static cast, dynamic cast does most of its checking at runtime. If the cast doesn't make sense to the dynamic cast operator at runtime, then a runtime error will result. Reinterpret cast is a special case. Reinterpret cast, which isn't illustrated here, but uses exactly the same syntax as static and dynamic, does very little in the way of checking at all. It's virtually the equivalent of the C and C++ casting. It's inherently unsafe, and its use should be avoided wherever possible. It only tends to be used for unsafe casts which are also usually non-portable and in situations where you're dealing with low-level programming. The final cast is a const cast. To illustrate this, I've got a piece of code. I've created a person object. My class person has a member function growOlder. It has a getAge const member function. So growOlder is a modifier function. GetAge is a query function. In my code, I create a person as a pointer. I then call a function doSomething with that pointer. DoSomething takes as a parameter a const person pointer. P is a pointer to a const person. Therefore, within doSomething, P is a constant. Any attempt to call a modifier function such as growOlder will give an error because P is a const person. Modifier functions cannot be called on const objects. The workaround is to use the const cast. On line 25, I've created a pointer to a person called nonconst. I've then cast the const person passed in to do something, p, to a person asterisk pointer, in other words, a non-constant pointer. Line 26 effectively removes the const attribute from my parameter, and I can then call modifier functions on the non-const pointer. However, it is not a new object, it is simply a new pointer to an object which is no longer const. The object p and the object pointed to by non-const are the same object. When I modify the object via the non-const pointer, it modifies exactly the same object as pointed to by the p pointer. I've seen this situation used when the original requirement specified a const parameter to a function, and later requirements specified that the object passed into the function had to be modified within the function. Generally, this type of use indicates a possible design flaw. It should be avoided wherever possible. The 4 new casting operators, static cast, dynamic cast, reinterpret cast, and const cast, should be used in preference to both the C casting and C++ functional casting. In previous lessons, we've learned about implicit and explicit conversion and conversion constructors. Conversion using conversion constructors is usually implicit. In this example, I'm converting implicitly a Fred, which is an employee class object, to a person within the parameter of the do something. Do something requires a person, I pass it an employee. The compiler knows that I've created a conversion constructor for my person, which takes an employee as a parameter, and therefore I've implemented conversion from an employee to a person. Any code that requires a conversion, as in this example, will automatically be actioned by the compiler. However, in some situations you may want to disallow implicit conversion and only allow explicit conversion through a cast. If that's the case, you still have to implement the conversion constructor, but now you have to mark the conversion constructor as only being allowable in explicit conversions. If you apply the explicit keyword to the conversion constructor, you can see that the compiler has now given me an error on the conversion in the implicit conversion. It's suggesting that no suitable conversion constructor exists. If we force this conversion to an explicit conversion using a cast, like that, the compiler now realizes that I really want to do the conversion. I've explicitly said that I want the conversion to be performed. Because the conversion constructor exists, it can perform the conversion, and everything's okay again. The explicit keyword is only applied to the declaration of the conversion constructor in a class. Recent changes to C++ mean that the explicit keyword can also now be applied to conversion operators as well as conversion constructors. Operator overloading will be discussed later in this course. In this hands-on lesson, you'll be coding copy constructors, conversion constructors, and using vectors. This lesson contains 8 files: courseEvent.cpp and .h, person.cpp and .h, and a new class trainer.cpp and .h. It also contains global.h and hands-on.cpp. The instructions for the lesson are given in hands-on.cpp. The first task asks you to use a vector rather than the array in the course event class. You'll need to make several modifications to the classes to achieve this. You can then proceed on to task 2. Because we're using a vector, we should also code a copy constructor for the person class. Strictly speaking, this project doesn't require a copy constructor because we're not using dynamically allocated pointers within the person. However, we may wish to add some at a later date. Finally, because our training company, Acme Training Inc. is a very forward-thinking company, it cross-trains its trainers. A new class trainer has been added to the project. It contains a string name, a date of birth, and a trainer reference. This is very similar to our person class. Therefore, it makes sense that we should be able to convert a trainer into a person in order to add them onto the course. So your task is to add a conversion constructor to the person class. However, we should only allow explicit conversion from a trainer to a person. The trainer class doesn't contain an address field, so you'll need to default this to something like Acme Training Inc. There is no corresponding person field for the trainer ref field, so you may disregard this in the conversion. The code to test this has been implemented in main. As you can see, on line 34, I've coded an explicit conversion from a trainer object created on line 29 to a person object. I've added a new function, addPersonDirect, to the course event. This simply adds the person directly in rather than passing parameters as in the 3 lines above it. A sample solution with all the files called handsonsolution.cpp, etc., and all the files for this lesson are available on the working files folder. Pointers are regarded by some as one of the more difficult aspects of C++. For this reason, this lesson will be a brief review of pointers before we launch into the more advanced pointer concepts. Pointers are declared using the asterisk operator. On line 14, there is a pointer declared pint, which is of type pointer to an int. Pointers can be initialized in one of several ways. On line 18, pint has been initialized to 0. This is an old method of initialization which still works in C++. However, on modern compilers, it's been superseded by the initialization on line 19. Null putter is a new type to C++. It is specifically and explicitly a null pointer. Line 20 shows initialization of a pointer on its creation. The pointer in this case is pint2, which is also a pointer to an integer, and it's initialized using a universal initialization to null putter. On line 21, an integer x has been declared with an initial value of 999. On line 22, the pointer pint has been initialized to the address of x. On line 23, pint has been initialized to a new int. Operator new finds some memory, in this case 4 bytes for an integer, returns the address of the dynamically allocated memory, and assigns that address to pint. All of these methods of initialization may be used in your programs. However, the preference is for pointers to be initialized to null putter if they may not be immediately used. Pointers can be accessed by dereferencing the pointer using the asterisk operator. The asterisk operator is used for simple data types, or the arrow operator for complex types. This program has a structure date declared, and on line 25, a new integer created, and on line 26, a new date created. Line 28 uses the asterisk operator to dereference the integer. On line 29, the dereference operator is used to print out the integer. On lines 31 and 32, the arrow operator is shown. On line 31, dd is accessed by dereferencing the pointer to the date, and in this case is used to set its dd member to 21. Line 32 prints out the value of dd dereferenced via pdate. C++ uses strongly typed pointers. Conversion between pointer types is rare and usually restricted to inheritance hierarchies, where conversion takes place either up or down within the hierarchy. C++ can do anything that C can do, and more. C uses the concept of void pointers, or void asterisk. In C++, the use of void pointers is usually limited to casts to and from the void pointer. The void pointer is usually only used in very low-level programming, such as when writing peripheral drivers. Since C++ is a superset of C, it is conceivable that you may come across the C dynamic memory allocation routines. A brief example of these are given on lines 36 to 40. On line 36, the C allocation routine malloc is used to allocate an integer. Malloc has to be told how big the amount of memory to allocate is. So in this case, we've used size of int. Malloc always returns a void asterisk pointer, so before we can allocate it or assign it to our pint, we must cast it to int asterisk. The reverse of malloc is shown on line 37. This is free. On line 39, an array of integers is allocated. In this case, the amount of memory allocated is size of int times 10. We're allocating 10 integers. Again, malloc returns a void asterisk pointer, and it has to be cast to int asterisk. Unlike C++, which has different versions of delete for different versions of new, C only has a single deallocation routine, free. You should never use malloc on C++ objects. Also, malloc and free must never be mixed with the new and delete operators on the same pointers. That completes this lesson, which reviewed pointers. The code in this lesson is available in the working files folder. Pointers to char have always been treated as a special case in C and C++. Traditionally, in legacy programs, they've been used to represent strings. In C++, we have the new std::: data type, which is used to represent more modern strings. However, many legacy applications still use the char asterisk representation of a string to interface with libraries. For this reason, this lesson will discuss these in a little more detail. On line 8 of my program, I've allocated a 255 byte area of memory for a string. On line 9, I've copied, using a structCopy routine, which will be explained shortly, one string, Simon, into the 255 character destination string. The size of the memory allocated is 255 bytes. The length of the string is 5 bytes plus 1 byte for the null terminator. So the size of the memory does not necessarily bear any resemblance to the actual length of the string it contains. The way this is catered for in C++ is to terminate all strings with a null terminator character. Routines which use strings, such as cout on line 15, then output continually up to the null terminator. They don't need to know how many bytes there are in the string. To demonstrate some of the routines in the C standard library which deal with char asterisks, I've created 3 pointers to char. One called 10 chars, which is nude to 10 characters, 10 bytes. One called 6 chars, which is nude to 6 characters or 6 bytes. And finally one called big chars, which is nude to 255 characters or bytes. The first routine we'll look at is copying strings. More modern standards have introduced newer versions of the existing older routines. In my examples on the screen, the first routine is generally the older copy of the routine, and the second example is a newer version of the routine. However, you should note that the newer versions of the routines are implemented in a part of the standards which is optional. These routines are specified in Annex K of the standards, and Annex K is totally optional. It's up to compiler writers whether they actually implement these routines. Microsoft have done so, other compiler writers may not. So the versions of the routines we're seeing here are the Microsoft versions of the enhanced routines. The _s on the end of the newer routines stands for safe or secure, and this generally refers to the fact that they take an additional parameter over the existing routines, which is the length of the destination buffer. Any attempt to exceed the destination buffer in the newer routines will generate some sort of error. On line 22 we have a routine called structCopy. StruCopy is used to copy one string to another. The first parameter is the destination area, and the second parameter is the source. So structCopy 6 chars, Simon copies Simon into 6 chars, and in this case it will exactly fill the 6 chars buffer because the null terminator is copied too. The newer version of this is on line 23. Again, it copies Simon plus the null terminator into 6 chars. The length of 6 chars is 6. Any attempt to exceed that will generate an error. On lines 25 and 26 I have a similar example, but this time I'm copying 6 chars into 10 chars. 6 chars currently contains Simon plus a null. 10 chars is 10 bytes long. This means that we've actually filled 10 chars but have 4 chars remaining. The same is true of line 26. In this case we're copying 6 chars to 10 chars. I've specified that the buffer size of 10 chars is 10 bytes. That function is perfectly okay, no errors will be generated. The next two lines, on lines 28 and 29, concatenate two buffers. On line 28 we're attempting to concatenate 6 chars onto the end of 10 chars. The result of this is undefined. The compiler will not generate any sort of error. However, our 10 chars currently only has 4 bytes spare. If we remove the null terminator from 10 chars and then copy the new 6 chars onto the end of it, we're overflowing our 10 chars buffer by 1 char. What we're actually overwriting is anybody's guess. It all depends what's in memory, where these two variables are declared in memory, and if there's any memory following them. If you're very lucky, you might cause some sort of critical error, and your program might crash. Why is that lucky? Well, if you're unlucky, then the error will not overwrite anything critical. You don't know what it's overwriting. The data that's been overwritten could get written to a file, a database, anywhere in fact. It could compound the error every time we run the program, and your data could become totally corrupted and may be undetected. Line 29 shows the safe version of strucat. Again, it has an _s on the end. This time, however, an error will be generated because attempting to do it will exceed the destination buffer. Lines 31 onwards copy and concatenate a number of characters from one string to another. Struct nCopy takes a third parameter. It copies 3 characters from 6 chars to big chars. The _s version does the same, but this time the second parameter is the size of the destination buffer. And again, if you exceed the destination buffer while doing this type of copy, you'll get an error. Lines 35 and 36 are exactly the same but for concatenation. Struct ncat concatenates a number of characters from one string onto the end of another. In this case, we're concatenating 3 characters from 6 chars onto the end of big chars. And on line 36, the secure or safe version of the same thing. Lines 38 and 39 are comparison. On line 38, we're comparing 6 chars with 10 chars. It compares the entire string 6 chars with 10 chars and returns an integer result which determines which string is greater or whether the 2 strings are equal. Line 39 does the same thing, but only compares the first 3 characters. The result of the comparisons is given on lines 40 to 43. If the first parameter is less than the second parameter, then the integer result is -1. If the 2 strings are equal, the result is 0. If the first parameter is greater than the second parameter, the result is 1. Lines 46 gets the number of characters in a string. It's not the length of the memory, it's the number of characters in the string up to but not including the null terminator. I said earlier that the std::: string is a more modern string. Strictly speaking, the two are not completely compatible. However, the char star is the basis of the std string behind the scenes, and in order to allow compatibility of the two types, the char asterisk and the std::: string, there is a data member of the std::: string which returns the string stored within it in char asterisk format. This allows us to use an std::: string, in my case here name, with the existing string handling routines from the C library. Microsoft have chosen to deprecate or de-implement the older versions of the routines, and in fact if I compile this code, I get all sorts of warnings about unsafe routines. In fact, wherever I've chosen to use the existing older versions of the routines, I get a warning saying that it's unsafe and is being deprecated or de-implemented. All of these routines are in the C standard library. In order to use string handling routines, you have to hash include the string.h header file. Because they work in C, they also work in C++. However, if performance and portability and compatibility isn't an issue, you should use the std::: string data type instead of char asterisks, as it has all of this functionality built into it, and in fact more. It also has the added benefit of being totally memory safe. On a couple of occasions, I've carried out what may seem like odd calculations using pointers. This lesson explains those calculations and more generally pointer arithmetic. Pointers, just like any data type, can undergo arithmetic operations. On line 7, I've declared a pointer to an integer and newed it to 1000 integers. On lines 9 and 10, I've declared 2 temporary pointers. These will be used shortly. Lines 12 and 13 perform addition and subtraction on the pointers. Lines 14 to 16 show that we can't use all of the arithmetic operators in pointer arithmetic. You can only use the additive or subtractive operators as shown on lines 12 and 13. For that reason, I'm commenting out those 3 lines. I can, however, use the ++ operator and also the -- operator. Lines 18 to 21 show the ++ operator in use on the temp pointer. You can use both the prefix and postfix versions of ++ and -- as shown. On lines 23 to 32, I've shown an example of using pointer arithmetic with arrays. I have an integer array called numbers, and I've used universal initialization to initialize it to the numbers 0 through to 9. My array is therefore 10 elements long. I've got a pointer to an integer called pnumbers, and initially on line 27 I set pnumbers to the address of numbers 0. In other words, pnumbers now points to the start of the array. If I see out *p-numbers, I will get the contents of the first element of the array, in other words 0. On line 29 I then increment p-numbers. That adds 1 integer to p-numbers, and makes it point to the second location of numbers, i.e. numbers, open brackets, 1, close square brackets. That contains the value 1. If I cout *p numbers, it'll print 1. Finally, on line 31, I do p numbers plus equals 5. It should now be pointing at the 7th element of the array, which contains the value 6. If I cout *p numbers, I should therefore get 6 printed. The last example is again using arrays. However, it's a variation on the previous example. It uses a pointer as an array iterator. Initially, I set p numbers to point to the start of the array. This time I haven't used address of numbers 0, I simply used the name of the array. The name of an array in C++ is actually a pointer to its first element. So p numbers points to the first element of numbers after line 35. I then got a while loop, while p numbers is less than or equal to numbers plus 9. Within the loop, I cout *p numbers and then increment p numbers. This loop should therefore output all elements of the numbers array starting at 0 and going through to the 10th element. The new operator is usually used to allocate a piece of memory from the free store or the heap. The piece of memory is allocated at an arbitrary address decided upon by the operating system, and that address is returned to you as a result of using new. In this lesson, we're going to look at a version of the new operator which allows you to specify a particular address for allocating objects. First of all, I've created a class CHAR. I've coded this class in line for simplicity's purposes. The constructor takes a make, a model and a registration number, and the body of the constructor, just for purely debugging purposes, contains a cout telling me that I've constructed a car and the address that the car is constructed at. That's done using the this keyword, which is this is a pointer to the current object, therefore it is the value of the address of the current object. On line 14, I've got the destructor for the car. In my case, I don't specifically need a destructor for the object, since the object contains no dynamic pointers. However, I wanted to insert another cout stating that the car was being deleted. The car contains 3 private data members, make, model and registration number, all as strings. I can't just pass an address to the new operator. Instead, what I have to do is allocate a large area of memory and then allocate my cars within that area of memory. I allocate the large area of memory, the pool if you like, on line 33. I'm using malloc, which is a C memory allocation routine. As you can see on line 31, I've stated that I can't use new because new calls constructors and creates objects. Malloc will not create objects, it just allocates raw memory as void asterisk, which I've then converted by casting to car asterisk and assigned to my pool pointer of type car asterisk. On line 35, I declared a car pointer called pool car, which will be used later in this code for access to temporary pointers. On lines 38 to 40, I've called operator new to allocate 3 new cars. Normally, new does not take any parameters, we just say new car. However, in this case, I've passed it a pointer as a parameter. The parameter is the address that we wish to allocate the car at. So on line 38, I allocate a car of make, Fiat, model Punto and registration number Italian, and it will be allocated at the address of pool pointer. In other words, right at the start of my pool memory. On line 39, I allocate the second car, a BMW M6 convertible with a registration number of German, and I allocate it an address of pool pointer plus 1. From previous lessons you should know that this is pointer arithmetic, and the address it's actually allocating the car at is pool pointer plus 1 car. In other words, it's allocating the BMW at an address which immediately follows the first car, the Fiat Punto. On line 40 I do a similar allocation, this time a Renault Twizy with a registration number of French, at pool pointer plus 2. What I should end up with after line 40 is a pool of memory pointed to by a pool pointer, which contains a car Fiat at the very start, followed by a car BMW and then a car Renault. I then use my pool car pointer. I set it to point to pool pointer plus 1. In other words, it's pointing at my BMW. On line 45 I've done something which is a little strange and should never normally be used. However, in this situation it's quite acceptable. I've called the destructor of the car pointed to by pool car. In other words, I've called the BMW's destructor. The destructor sets the make, model and registration number back to empty. In other words, it reinitializes the car to empty. This effectively leaves a hole in my pool. I've got my first car, then the deleted BMW car, and finally my third car, the Renault. Line 48 replaces the car that was at position pool pointer +1, the deleted BMW, with a new car, a Dodge Viper with a registration number American. And it also adds a fourth car onto the end, a Rolls-Royce Wraith with a registration number of British. Lines 52 to 56 cycle through my pool, deleting each car in turn. Finally, on line 59, I free my entire pool memory. You should note that there is a placement new, however there is no real placement delete. The only way we can actually delete cars from our pool is to call the destructor as shown on line 45. Okay, so that's how it works. You have a pool of memory, you allocate objects within that pool, you have to keep track of the objects within that pool. To delete an object from the pool, you don't call the delete operator, you call the destructor. But why might you want to use it? At first sight it looks like a lot of hard work. You've got to manage everything yourself within the pool. One advantage of using this methodology is that it's memory safe. If you're using the compiler provided new operator just to create objects and delete them with destructors elsewhere, you can get memory allocation errors. Using this methodology, the memory is allocated up front, you know you've got enough memory, so you won't get any such errors. It's also much faster. Memory allocation of individual objects is fairly slow. Memory allocation in this way is simply formatting a pre-existing piece of memory to a car and calling its constructor. Another use of placement new is in the area of memory mapped hardware, although this is beyond the scope of this course. In this lesson, we'll be expanding further on pointers by introducing pointers to functions. We'll start by taking a quick look at a very simple class that represents a car. In the car header file, I've declared my class, which contains a constructor, which takes 3 parameters, make, model and colour. I've also got 3 query functions, getMake, getModel and getColor, and 3 private data members, make, model and colour. The 3 query functions return the values stored in the private data members, and the constructor initializes the data members. In my code, I've used universal initializers to initialize the 3 data members, make, model and colour from the parameters, and as I said, the 3 query functions simply return the values stored in the 3 data members. Now let's look at a simple main function which can utilize this car class. I've started to code this main function by declaring a couple of vectors. The selected vector will come into use shortly. The main vector that I'll be using is the carpool vector, which is a vector of pointers to the car objects. On lines 74 to 85, I've created a few cars and pushed them into the vector. The cars are an assortment of makes, models and colours. Now let's assume we want to make some selections on our carpool vector. For example, I'm going to use a couple of different selections. I'm going to say I want to select all blue cars. Or as a second example, I want to select all Ford cars. We could do this by creating functions which iterate through our carpool vector, placing the selected items into a new vector selected. Let's have a look at those functions. Lines 7 to 18 contain the select blue cars function. I pass as a parameter my carpool vector, and I return a new vector which is the selected items. Within the function I create a temporary vector, again called selected. I then go iterate through the carpool vector from 0 to pool size. If the colour is blue, then I add it to the selected vector. Finally, when I leave the for loop, I return all blue cars in the vector. Similarly, the Ford selection routine is very similar. In fact, the code is totally identical apart from the code on lines 12 and 25. The code on line 12 does getColor equals blue, the code on line 25 does getMake equals Ford. Obviously, this is not particularly good practice. It would be nice if we could do the following. Create a function which is capable of selecting any criteria and pass our select statement, make equals forward, colour equals blue, etc., in as a parameter. And then within the function, as shown on line 38, simply select statement and return the vector according to the cars that have been selected. However, if we try to call our function by saying this, select any and pass it the carpool vector and piece of code which says get colour equals blue, this will not work. Returning to our function for a moment, we simply cannot pass a string containing a piece of code and then on line 38 simply test that string expecting it to be treated as a piece of code. That approach therefore will not work. We can, however, rather than passing a string, create a function which merely contains the single line get colour equals blue, get make equals forward, etc. Then we can write a generic select function and we can pass it a pointer to one of those functions. A function, just like anything else, lives in memory, it's code. It has an address. So if I can take the address of that function, pass that address into the select function, and then call that function to do my selection, I can pass literally any function which does a selection into this select any, making select any a totally generic function. This is exactly what I'm doing here. My function prototype, my pointer to function, reads as, this is a pointer to a function which takes one parameter, in my case a car pointer, and returns a boolean. I can therefore pass any function which matches that signature into this select function. And if we look at my two select functions, they both take a car function pointer as a parameter, and they both return booleans. Line 61 is where I call that function. My function pointer is called anySelect. I call anySelect, pass it each individual car in turn from my pool. It returns a boolean. Depending on which one I call, it may return true or false depending on whether the colour is blue or whether the make is forward. This code will not change regardless of how many functions I pass it to select. Let's have a look how we call that. Well, the first two examples are selecting the cars using the distinct select functions. That code will not work because it's attempting to pass a code as a string into the function. We've removed that. The last two bits of code both call select any. Remember, select any is my generic function. The first parameter is the vector of cars. The second parameter is the name of my selection function. The name of any function is actually its address in memory. Therefore, I'm passing a pointer to an address which is the start of my select blue function on line 110 or select forward function on line 121. That cycles through the pool of cars, applying the select function to each member. The select function returns boolean true or false, depending on whether it's selected or not. If it is selected, the select any function adds it to the output vector, which is then returned when we exit select any as selected in my code on lines 110 and 121. The last bit of code simply outputs what I've actually got in my selected at the end of those two functions. If I run this code, what we should end up with is a call to the distinct function, select all blue cars, followed by a call to the function which selects all forwards, followed by two calls to my select any generic function. The first one is past the select blue car, the second one is past the select forward function. If we have a look at the output, the first function I called was to select the blue cars using the select function which was hard-coded. That selected a blue Ford Fiesta and a blue Renault Clio. The second function I called was select all Fords using the hard-coded selection criteria. That's returned 5 Fords, a blue Fiesta, a green Fiesta, a black Focus, a yellow Fiesta and a green Galaxy. The next two lots of output are my functions which use the generic select any function. And if you remember the output from the previous functions, you can see that the outputs are identical. Cases where pointers to functions can be used are fairly rare. However, when they can be used, there is a trade-off between readability and maintainability and performance. The code tends to be a little bit less readable. If it's less readable, then it can also be regarded as slightly less maintainable. Pointers to functions are actually quite an advanced concept. However, rather than having to use multiple select statements, multiple switch statements and so on, the simplicity of the pointers to functions generally makes it more efficient. In this lesson, we'll be reviewing pointers to functions and introducing a new feature to C++, lambdas. We've already seen how pointers to functions can lead to more generic and smaller code. We'll use the same pointers to function examples that we've used before to demonstrate lambda expressions. I've declared a class, CHAR lambda, which has a constructor, 3 query functions, and 3 private data members. The implementations for these functions simply stores the make, model and color passed into the CHAR constructor into the member variables, and the query functions retrieve those member variables. When we looked at pointers to functions, we created a selectAny function which took a vector of CHARs and a pointer to a function that contained the selection criteria. In our main function, we populated our main vector, CHAR pool, and then called selectAny, passing it a pointer to the function. And the example on line 49, it was a select blue cars function, and on line 58, a select forward function. These were simple utility functions which returned a boolean, took an individual car as a parameter, and applied selection criteria, returning true or false depending on whether those criteria were true or false. Now we'll look at lambdas. The code for the lambda looks very similar to the code for pointers to functions. In fact, if I can get both of them on the screen at once. Lines 58 to 64 select based on a function, pointer to a function, in this case select forward, and then it prints the selected criteria. The equivalent of this using lambdas is lines 67 to 73. Rather than calling a function as the second parameter, I call selectAny, but instead pass it a lambda expression. The selectAny function doesn't change in any way whatsoever. This suggests that a lambda is actually behind the scenes a pointer to a function. Let's take a closer look at the lambda expression. In particular, I'm looking at line 67. I call selectAny with my CHAR pool, but in place of the pointer to a function, I have this expression. In some respects, this looks like a function anyway, because it has a body and a parameter. However, unlike my function, it has no return type. In this expression, the square brackets at the start indicate that this is a lambda expression. The compiler can deduce the return type of the lambda expression by looking at it and evaluating it. Because I'm returning the result of a comparison, the compiler can deduce that I am returning a boolean, therefore I don't need to put the keyword bool anywhere into this lambda expression. When I call selectAny, this lambda expression actually gets converted into a pointer to a function. It's an anonymous function rather than a named function in the previous examples. On line 76, I have similar code. I still pass a CHAR pool into selectAny, and I pass a different lambda. This lambda compares mates for forward. Again, the selectAny function hasn't changed at all. This lambda will be converted to a pointer to a function. At first sight, there doesn't appear to be any advantage in lambdas. In fact, some would suggest that it is a disadvantage because I've hard-coded the blue and the forward into the two lambda expressions. However, this is only a very basic introduction to lambdas. Lambdas are a lot more complex than this. Let's take a look at a slightly more complex lambda expression. This time, rather than calling selectAny, I've used an algorithm in the standard namespace called forEach. This algorithm takes a container, in this case my CHAR pool. I pass it a begin and an end iterator to my container, telling the forEach algorithm where to start and finish. And then I pass it a lambda. In this case, the lambda extends from here through to here. This lambda expression isn't quite the same as the last lambda expression. The last lambda expression returned a boolean. In this case, I'm doing away with my selected vector completely and instead couting all the members of the pool that match the criteria. Similarly, with the forwards, my lambda extends across those lines. As I said, this is a very basic introduction to lambdas. Lambdas themselves contain lots more useful features. However, it's quite an advanced feature and it's beyond the scope of this lesson. If I run this code, what we should end up with is, first of all blue cars using selectAny, then all forwards using selectAny, then all blue cars using a lambda and using selectAny, then all forwards using a lambda and selectAny, and finally blue cars using a forEach algorithm and forward cars using a forEach algorithm. Let's have a quick look at the output. Blue cars using the function pointer, we've got Ford Fiesta blue, Renault Clio blue. Fords using the function pointer, we've got 5 Fords, blue, green, black, yellow and green. Switching to a lambda, we've got blue Ford Fiesta, blue Renault Clio and the same 5 Fords. Using for each, again we've got our 2 cars, a blue Ford Fiesta and a blue Renault Clio, and finally our 5 Fords. All methodologies produce the same output. In previous lessons, we've looked at pointers to integers, pointers to structures, pointers to objects, pointers to char, and even pointers to functions. This lesson takes a brief look at pointers to pointers. A pointer can point to any item in memory. A pointer is itself a variable in memory. It therefore stands to reason that we should be able to point one pointer at another pointer. Let's take a look at a few examples of using pointers to pointers. On line 6, I've declared an integer and given it the value 99. On line 7, I've declared a pointer to that integer. The pointer to the integer pint is initialized by taking the address of x. Pint now points to an integer x. On line 8, I've declared a pointer to an int and called it ppint. Ppint is initialized with the address of pint, which is a pointer in itself. So ppint is a pointer which points to pint, which points to x. The cout statements on lines 10 to 12 show how we can access data at the pointers. Line 10 is a straightforward cout of x. 11 dereferences the pint pointer, goes to where it points to. Since pint is pointing to x, that's the value that's printed. On line 12, we use the pointer to an int. Note how on line 8 the pointer to the pointer is declared using asterisk asterisk, and on line 12 it's dereferenced using asterisk asterisk. We can look at the addresses of pointers by printing them out. The hex modifier on the cout prints the address contained in a variable in hexadecimal format. Before we run the program, we'll look at a few more examples. The next example starts on line 19. I've got an array of pointers to integers. On lines 21 to 25, I initialize the array. I allocate a new integer on every pointer within the array. I then initialize the address pointed to by that pointer to the x which is used in the for loop. I should therefore end up with an array of 10 pointers to integers, each one pointing to an integer which contain the value 0, 1, 2 through to 9. We already know that an array is itself a pointer. If I declare a pointer to an int pp numbers, I can initialize that with the name of the array. Remember, my array is an array of pointers to integers. P numbers therefore is a pointer to an integer. It's a pointer to the first item in the array. In the for loop on line 29, I am initializing pp numbers to point to the first item in the array. I'm looping until I reach the end of the array and iterating through the array with pp numbers. Every time I increment pp numbers, I will be adding one pointer to pp numbers. In other words, it will be iterating along the array one pointer at a time. My cout therefore should print the first location in the array, 0, then the second location, dereferencing the pointers as it goes along. I should get the values 0 through to 9 printed with a tab between them, and finally on line 33, a new line. Let's have a look what this code produces. The first cout on line 10 prints x. X was initialized to 99. The second line is the output from line 11, asterisk pint. Pint was a pointer to the integer x, therefore dereferencing it will produce 99. The third line output is asterisk asterisk ppint. Ppint was a pointer to pint, which was a pointer to an integer, x. Again, when I dereference it, therefore, I should get x, which is 99. Line 14 prints out the address of x. X is stored, in this case, at 00B8FC38. If pint is a pointer to an integer, x, it should contain the address of x. So the next line of output is the contents of pint, and as you can see, it is the same as the address of x. I then print out the address of pint, 00B8FC2C in this case. Pint contains the address of x, pint points to x. I then print out the contents of ppint. As you can see, the contents of ppint are the address of pint. ppint points to pint, pint points to x. ppint is a pointer to an integer. The last section of my code was used to print out the contents of an array which was iterated through using a pointer to a pointer. And exactly as I said, we've got the values contained in the array, 0 through to 9, and then a new line. Pointers are one of the most common causes for failure in C++. When used correctly, they're a powerful programming tool. However, if used carelessly or improperly, they can lead to memory leaks, corruption, and program failure. This lesson is more about best practice than syntax. In it, I'll show you some ways in which you can make your program more resilient to problems. Of course, this usually comes at a cost, and that cost is performance. Let's first take a look at some examples of poor programming practice. On lines 4 to 18, I've declared a class. My class is called Big Class. In the constructor for the class, it allocates some memory, 1,000 times size of a double. In my case, on this platform, that equates to 8,000 bytes. I've got no destructor, so automatic cleanup for this class won't happen. I have, however, got a tidy up routine in there, which has the delete for the p double pointer. I then got a structure declared called BigMem. Within the structure, it has a pointer to an integer and an array of 500 doubles. I've got a function called doIt, which takes a big class object as a parameter. Within the function, I create a pointer to a BigMem structure, and I knew it to create an instance of the BigMem structure. On the next line, line 30, I knew the integer pointer within the BigMem structure to be 1,000 integers, or 4,000 bytes. Finally, in main, I have a pointer to an integer, and I see out the contents of the pointer to an integer. Then on line 43, I create a new integer at that pointer and delete it again. I then try to see out the dereferenced pointer. On line 47, I create a pointer to my BigMem structure and create an array of them. So I've got 10 pointers to BigMem. Within a for loop, I then create a BigMem at each of the pointers and knew the integer to 100 integers. So I've got 10 pointers to BigMem. Each pointer to the BigMem contains a pointer to an integer new to 100 integers, or 400 bytes. This is followed by another loop on lines 54 to 58, which is designed to delete the huge mem memory. And finally, I've got a delete for pint. You've probably noticed there are comments throughout this code. Let's have a look at the comments briefly. First of all, on line 15, my big class has no destructor. In my doIt function, my BigMem structure goes out of scope. I knew it, but I don't delete it. As far as the operating system is concerned, I still have, within my BigMem, 500 doubles and my 1,000 integers. These are still allocated in use, however, because I've lost the pointer to the BigMem because it's gone out of scope, I can no longer access it. This is termed memory leakage. There's also another problem with this doIt function. Big class is passed into my function by value. Passing by value is in itself a problem. It'll cause copying, I haven't got a copy constructor declared, and so on. However, in this case, we're not even calling a tidy up routine for the copy. So, no destructors declared, so when the copy BC goes out of scope, no tidying up will be done, and we'll end up with more memory leakage. In main, we're dereferencing an uninitialized pointer. Line 41 attempts to dereference pint. Pint hasn't been initialized to any memory. On line 45, we deleted pint and we're trying to reference it again. Deleting a pointer does not change the pointer in any way. It doesn't invalidate it. On line 45, pint will still contain the same address as it was allocated to in line 43. On line 57, I've deleted the huge mem structure. However, the structure contained 100 integers. I haven't deleted that memory. Deleting a structure will not delete all the memory it contains. It will delete the structure itself, but as far as the system is concerned, I still have 100 integers allocated. All I've done is lost that pointer to those 100 integers. Again, I'm leaking 400 bytes of memory. And finally, on line 61, I delete pint. Pint was deleted previously on line 44. Deleting a piece of memory twice has undefined results. this is going to cause an error. Let's just try compiling this code to see what happens. Well, the compiler succeeded according to the compiler. I have got a warning. The warning is that I'm using pint before it's been initialized. And this particular warning refers to line 41. In other words, I potentially got all these memory errors in my program, but the compiler isn't picking up in any of them. A lot of them may seem very silly, but believe me, I've seen these sort of errors in code that people have written. So let's have a look how we can fix them. The first error was that big class had no destructor. In the destructor for big class, I want to delete the p double pointer that was allocated on line 9. This actually exposes another error. In my tidy up, I delete p double, that will delete one double. I've allocated 1,000 doubles. The delete on line 13 should be delete with square brackets, as should the delete in my destructor. That's fixed one problem. My big main structure is still okay, it's purely a declaration of a structure. Let's go into do it and see what we need to change there. First of all, error 1 in this function says that p local big mem goes out of scope, but memory is still allocated. Therefore, we need to delete that memory. That's deleted the integers that are pointed to there. Next, we need to delete the structure. Those two deletes correspond to the two news on lines 33 and 34. As for error 2, big class is called by value. Well, we've now implemented a destructor in our class, therefore big class is memory correct. It won't cause any further problems. Let's turn to all our problems of our pointers in the main function now. Dereferencing an initialized pointer. There is no way we can tell whether a pointer has been initialized or not, unless we forcibly initialize it. Now my pint is initialized. I can add code around my dereference of the pointer to check whether the pointer is initialized. Now, pint will only be dereferenced if it is not null pointer. The next problem is on this line. I delete pint. I said that deleting a variable does not alter its value. Therefore, what we should do every time we delete a pointer is reinitialize it to null pointer. Then whenever we try and use it, we can check whether it's null pointer or not. The next problem occurs on line 68. We delete the structure, huge mem, but we don't delete the individual item pointed to within the structure. We don't delete the memory at pint. Again, we now have symmetrical memory management for our huge mem structure, huge mem array. We have new with square brackets, delete with square brackets, new without square brackets, delete without square brackets. So my memory management is symmetrical. Finally, we're deleting pint again just to be sure. Although this is bad practice, we now know how we can easily protect it. We can protect it by checking to see if it's null pointer. If it's not, then it will get deleted and we set it to null pointer. As I said, all of this takes time. However, if you use these methodologies, you can protect your program against failure through bad pointers. We've seen some of the problems associated with the use of pointers. This lesson puts forward another possible solution to some of these problems. Recent changes to C++ have reinvented the concept of scoped pointers. The now deprecated auto putter has been replaced by the 3 new pointer types. These were previously available in third-party Boost libraries. 3 new pointer types have been added to the STD or standard namespace. These are unique putter, shared putter, and weak putter. In fact, these types are not simple pointers. They're small template classes that will contain and manage a pointer. We'll look briefly at each of these in turn. First, let's look at a very simple unique putter example to see how it works and what benefits it can give us. The code on the screen shows a very simple class person with a constructor, a destructor, and a single member function called usePerson. I've also got a function called doIt, which takes a reference to a person as a parameter and does a simple cout. The code to use the unique pointer follows those two declarations. Line 20 shows the declaration of a unique putter variable. It's a template class, so we have to tell it what type of pointer it's going to contain. In my case, it's a pointer to a person class, so I tell it it's going to contain a person. The unique pointer's name is P1. I've supplied a constructor to my P1 object and created a new person. At that point, the person constructor should be called. If you note, I've not got any reference to any pointers to a person in my project. All the pointers are contained within the P1 unique pointer object. I can then use my unique pointer object as if it was a standard pointer. I check if P1 is valid. If it is, then I call usePerson. The block of code that follows is not part of the if statement. The if statement ends on line 21. It's just a block of code to demonstrate another unique pointer, P2 in this case, declared and initialized within a block of code. I create a pointer P2 and I move the pointer within the P1 object, the person that I created on line 20, into pointer P2. P2 now owns the pointer to the person that was previously in P1. If I call doIt with asterisk P2, the person that is in P2 is the person created on line 20. That calls doIt. It will cout in doIt. I then move the pointer that was in P2 back into P1. On line 26, I reach the end of my block of code, and on line 27, P2, the unique pointer that I declared on line 23, goes out of scope. However, it doesn't own any pointers now. The pointer that it did own has been moved back into P1, therefore no person destructors will be called. Since I moved my person back into P1, I can now call usePerson on P1, and when I reach the end of my function on line 32, the person instance owned by P1 is automatically destroyed when P1 goes out of scope. I don't need to take care of deleting the person myself. If I run this code, let's have a look at the output versus the code. Person constructor was called on line 20. I then called usePerson, which calls the usingPerson output. I passed my person as a reference into doIt as P2. doIt outputted in doIt. I then couted P2 going out of scope. Note no person destructor was called. Then back into my main function again, I called usePerson on P1, which output usingPerson. And finally, even though I haven't called a destructor explicitly or deleted the person object explicitly, as P1 goes out of scope, the person destructor is called for me. The second type of pointer that we'll look at is a shared pointer. Whereas the unique pointer held exclusive ownership of a pointer, the shared pointer allows sharing of a pointer. Again, I'm using my person object. The code for the shared pointer is a little longer. Let's have a look at it briefly. On line 15, I declare a shared pointer, which is uninitialized. It owns no persons. The shared pointer has a useCount member, which can be used to tell how many people are sharing the pointer currently. Initially, that should be 0. I then set another shared pointer, P2, to null, or null putter, and look at P2 useCount. P2 useCount should also be 0. I create another shared putter, P3, and this time I new it to a person. Because my P3 actually contains a pointer to a person now, the useCount for P3 will be 1. I then create another shared putter, P4, and initialize it with P3. P3 and P4 are both now sharing the person created on line 19. As a result, if I do P3 and P4 useCount, they both show a value of 2. I can use the person via P3 or P4. They both share the same person pointer and therefore will produce exactly the same output. Next, I've created yet another shared pointer, P5. This time I've moved the P4 shared pointer created on line 21, which is a copy of P3. I've taken that pointer and moved it into P5. We haven't altered P3. P4 now does not share the pointer at all because it was moved into P5. P5 is a share of my pointer. Therefore, the use counts are 2 for P3, 0 for P4 because we've moved it into P5, and 2 for P5. The next bit of code calls the reset function. I've called reset on P3. Reset deletes a pointer from the share, but doesn't call its destructor. P3 held a person. That person is also held by P5. If I reset it in P3, P3 no longer holds a pointer to a person, so its use count is 0. P4 was moved into P5 earlier, so it doesn't hold a person, so its use count is 0. P5 is now the only pointer, the only shared putter, which holds a person. Therefore its use count is 1. When I call P5 reset, it deletes the last remaining share. When a shared pointer detects that there are no outstanding shares, it calls the destructor for the shared object that it holds. The destructor for the person created on line 10 will be called on line 34, and all the use counts are now 0. The final type of pointer we're going to look at is the weak pointer. The weak pointer answers a question. Let's take a look at a simple piece of code. I've created a pointer to an integer and set it to a new integer. I've created another pointer called ref and set its value to pint. I then use the pointers. They both point to the same integer. If I delete pint, how can we tell if ref is valid or not? The simple answer is that we can't using this code alone. The weak pointer is the answer to that question. Again, I've used a person class. Let's look at some code for a weak pointer. I've recreated the code that we just looked at, this time using a person. Person P1 equals new person. Person ref is P1. They both point to the person. If we delete P1, how can we tell if ref is still a valid pointer? I said that we couldn't. However, if we use weak pointers, we can do so. Weak pointers are never used on their own. They're used with shared pointers. In this case, I've got a shared putter, SP1, which refers to a person, or contains a pointer for the person. I've got an empty or uninitialized SP2, which is also a shared pointer, and an uninitialized weak pointer, WP1. At that point in the code, SP1 use count is 1. It contains a shared person. SP2 use count is 0. WP1 use count is also 0. If I set WP1 to SP1, then my pointer is now shared with SP1 and WP1. SP1's use count is 1. SP2 is still uninitialized. Its use count is therefore 0. WP1 is a weak pointer to SP1. Its use count is 1. I then call the lock statement on WP1. If WP1 is valid, the lock statement will return a pointer to a person. In this case, WP1 is a valid pointer, therefore it will return a pointer to the person that it holds. That's assigned to SP2, which gives us this situation. SP1 use count is now 2 because the person pointer is shared by SP1 and SP2. SP2's use count is 2, and the pointer contained in WP1, the weak pointer, is also use count 2. If I reset SP1, then SP1's use count is now 0 because it's been reset and the pointer within the shared pointer 1 has been removed. However, SP2 also has a share on that pointer, so its use count is 1, and WP1 also has a weak reference to that pointer, so its use count is 1. I then set SP1 to WP1.lock. WP1 is a valid pointer, therefore SP1 will get a reference to that pointer and will be reinitialized with it, and all the use counts go back up to 2. I can call my used person member of my person from either SP1 or SP2. However, I cannot call it from a weak pointer object. I then reset SP1. Remember, at the moment, SP1, SP2 and WP1 all contain references to the pointer. If I reset SP1, WP1 still has a weak reference to the pointer in the SP2 object. Therefore, the expired member will return false. The expired member of a weak pointer returns true if there are no valid references to the pointer, and false if the pointer is still valid. So in this case, I will get WP1 lives. If I then reset the last remaining shared pointer to my person object, there are no valid references to the pointer within SP1 or SP2. WP1 will therefore return that it is expired, and that's the output I should get. To show you how they work, I've provided you with function calls in a main program to call each of the functions in turn to show you how they work. All of these smart pointer types actually contain many other functions for creating, accessing, managing and deleting pointers. This lesson is just an overview of smart pointers. This hands-on lesson is your chance to test your understanding of pointers. In the working files folder for this lesson, you will find a file called handson.cpp. I've imported this into Visual Studio. The CPP file contains various functions defined and a main function. The main function is split down into various small parts, each part containing a piece of code. The small portions of code contain various pointer manipulations and a question. For example, on lines 46 to 52, I have asked what is the value of b at the end of that section of code. I've not provided a solution for this exercise. What I suggest is that you either write your answers on a separate piece of paper or add comments after the code with your answers. You can then run this code to check your answers. There's one section of code at the very end which is optional. If your compiler doesn't support the null putter type, then this question should be commented out and you can ignore it. If it does support null putter, then you can attempt the question on lines 141 to 150. This lesson is about the theory of object relationships. In this lesson, we'll be looking at kinds of relationships, the lifetime of an object, when is it created and deleted, who creates and deletes the object, and who, if anybody, owns the object. In particular in this lesson, we're talking about the interaction between objects rather than single standalone objects. Composition or aggregation describes a whole-part relationship between objects. The diagram on the right of this section shows the UML notation for describing a whole-part relationship. Association represents a usage or acquaintance relationship between objects. One object knows about another. Multiplicity defines the numbers of objects that may be involved in composition or association. And navigation defines how a relationship occurs. Is it unidirectional, object A knows about object B, or bidirectional, object A knows about object B and object B knows about object A? For our first example, we'll look at the relationship between an employee and a pool car. Can these two objects exist in isolation? Can we have an employee who does not have a pool car allocated? Can we have an unallocated pool car? The answer to all of these questions is yes, of course we can. Can we have an employee object with a longer lifetime than a pool car? Pool cars are usually replaced when they reach a certain mileage, say 50,000 miles, or a certain age, say 3 years. Yes, of course we can have an employee with a longer lifetime than a car, and vice versa. The two objects, in this case, are entirely independent of each other. A relationship between the two objects is formed when Mr. or Ms. Worker applies for and receives a pool car. Once the current task is complete, the relationship may end and the car return to the pool. On the other hand, Mr. Worker may be a particularly heavy car user and the car that he's associated with may break down or exceed its lifetime. In that case, a relationship will end and very likely a new relationship with a new pool car will be established. This kind of associative relationship is usually implemented using pointers. Mr. Worker has a pointer to the pool car that he's currently using. When no relationship exists, then the pointers can be set to null, or in C++ terms, null putter. This particular example shows a bidirectional relationship. The employee has a pool car, and the pool car has an employee driver. This is termed association without custody. Who is responsible for creating the employee and the pool car objects? In this case, it's probably the HR department for the employee and the transport department for the car. For our next example, we'll look at the relationship between a car and its engine. Again, I'll ask some questions. Can these objects exist in isolation? Can we have a useful car without an engine? Can we have an engine that can be driven? The answer is certainly not outside the factory. Can we have a car object with a longer lifetime than its engine? We're considering the car as a whole here, not individual parts of the car that may be recycled or refitted. The answer is no. The car will be manufactured with a petrol or diesel engine, but it keeps that engine for life. The two objects cannot exist independently of each other. A relationship between the objects is formed when Mr. Moneybags walks into the showroom, orders a car, and it's manufactured to his specification. If Mr. Moneybags is unfortunate enough to have an accident and his car is wrecked, then both the car and its engine are scrapped together. This is termed association with custody. The car is created and the engine created in the car at the same time. In some cases, a constant association may be required. In this example, we have a course that has an instructor. Ajax Sprockets Inc. have an office in Hawaii, and they want the training to take place at their company site. This is fixed. However, Acme Training Inc. can supply one of a number of instructors for the course, and can change the instructor at any time. The instructor is a variable association, and is usually implemented with a pointer. The location is a fixed or constant association. This is usually implemented by using a reference that must be initialized when the course is created, but cannot be changed thereafter. In this lesson, we'll take a look at a simple implementation of association with and without custody, and also an example of a constant association. In order to demonstrate these concepts, I'm going to use a training company with a trainer, a course delegate, and a location. The trainer will be a variable association, the delegate will be a variable association with custody, and the location will be a constant or fixed association. Let's take a look at the individual classes first. The location class is very simple. It contains two variables, a center ID and a room number, and all I've got is a constructor for the location. The course delegate is also simple. I have a name and address variable and a constructor. The trainer is also very simple. Two variables, a name and a trainer ID. As you can see, I've tried to keep this example as simple as possible. I could have added lots more fields, but this will suffice to demonstrate the association. Finally, in the course class, I have a constructor. The constructor takes as a parameter a course location object. The destructor is a little more complex. It deletes all delegates currently on the course. I have a setTrainer method, which takes as a parameter a trainer object and stores it in the class. The trainer object will be created externally. Therefore, the trainer is without custody. Delegates are added into the course object using an addDelegate method. This creates a new delegate object within the method and adds them into a container. The course class is therefore responsible for creation and, as we've already seen in the destructor, deletion of delegates. The course delegate has custody over the delegates. However, since I can both add and remove delegates, this is a variable association. For convenience of this demonstration, I've also put a listDelegates method in the class. Normally it would be bad practice to use cout within a class. However, it's used for demonstration purposes only here. The data members in my course are a container, and I've used an std::map, part of the standard template library. The map, very briefly, is a container which stores objects using an index and a value. In my case, I've used the name of the delegate as an index, which is a string, and a delegate object as the item. Delegates are added and removed from this map by the two routines we've already seen. The trainer is a pointer to a trainer association object. Trainers can be put into the course, again by using the methods shown earlier. This is a without custody variable association. The location is held as a reference to a location association object. References normally must be initialized where they're declared. In a class, the rule is that references must be initialized in a constructor. Because this reference cannot be changed later, this is a constant association. And because the location object is created and deleted externally to this course object, it is a without custody association. Let's just go back again and look at the constructor. Here the location is passed in, and within the constructor, using a colon initializer, the location is initialized. The code to use these objects is in a separate CPP file. First of all, I create a location. This is an external object. It's without custody. My location is set to Moscow and room 99. Next, in my main function, I create a couple of trainers. A Fred Flintstone trainer with a trainer ID of 123 and a Simon Bailey trainer with a trainer ID of 456. On line 15, I then create a course. Since I must pass the location into the course constructor, I pass in the location created on line 8. That establishes my constant association with the location. On line 18, I set the trainer to trainer 1, who happens to be Fred Flintstone. Further down the code, on line 28, I change the trainer to trainer 2. Trainer is a variable association. The trainers are created externally to the course, therefore it is without custody. On lines 20 to 24, I add 4 delegates to the course. There are no delegate objects in this code at all. The delegates are created internally to the course. The course has custody of the delegate objects. However, on line 31, I can remove delegates. Therefore, the association is a variable association. On lines 35 and 36, I add 2 more delegates to the course, and finally list the delegates. The destructors concerned in all the objects should take care of deleting any memory which has been allocated. In fact, this has only happened in the course, where we add delegates to the course, we create delegates in the add delegate function, and they're all deleted in the course destructor. If I run this code, we'll see how it works. So in the first instance, I add Batman, Popeye, Superman, and Yogi Bear to my course. The map is an ordered container, so they will be sorted. There's the add of the 4 delegates in code, and here's the display: Batman, Popeye, Superman, and Yogi Bear. The next bit of code removes Batman, and I list the delegates again. I end up with Popeye, Superman, and Yogi Bear. I then add 2 more delegates, Robin and Cinderella, and again in order, I get Cinderella, Popeye, Robin, Superman, and Yogi Bear. Previously, we've looked at implementing association. This lesson looks at implementing aggregation. Aggregation can be implemented using a couple of different techniques. We could, for example, use inheritance. We haven't discussed inheritance on this course yet. However, I've implemented a simple example to demonstrate aggregation using inheritance. The example I'm going to use is a PC. A PC contains or is made up of a disk drive, a printer, and a screen. To that end, I've created a disk class, which simply has a constructor, a default destructor, a display method, and a single private data member, which is the size of the disk. Again, as I usually do in my examples, I've tried to keep the classes very simple. We could, of course, add other disk attributes, such as the manufacturer, the rotation speed, etc. However, this would suffice to demonstrate aggregation. The display class is very similar. It has a single integer data member, which is the screen diagonal size in inches. I have a constructor to set the size, a default destructor, and a display function to display the screen attributes. In my classes, I don't need a destructor because I'm not allocating any resources within the destructor. If I had other resources, then I could implement a destructor as well. My printer is slightly more complex. My printer has 3 data members: a boolean to indicate whether the printer is also a scanner, a boolean to indicate whether the printer is also a fax machine, and a boolean to indicate whether the printer prints in colour or monochrome. The constructor therefore takes 3 arguments: bool scan, bool fax, and bool colour, and these are initialised via an initializer list. The destructor is again default, we don't really need to implement one, and my display displays the printer attributes. So if the scanner variable is set, then it prints scans. If the fax machine variable is true, it prints out faxes. And depending on the setting of the colour variable, it either prints in colour or prints in monochrome. All of these 3 types of object, printer, disk and display, can be used to create a PC. Here's my PC object. You should also note that all of my classes are implemented inline in a header file. This is not normally recommended practice, however in this case it allows me to demonstrate the code and the declaration all in a single file. On line 9, I've declared a new class, PC Inheritance. Line 10 is Inheritance in operation. Lines 9 and 10 effectively say class PC Inheritance is derived from or inherits from class Disk Aggregation, class Display Aggregation, and class Printer Aggregation. The public is a special keyword that will be looked at when we deal with inheritance. I have public member functions in my class. The PC Inheritance constructor takes parameters which initialize the disk, the display, and the printer. These parameters are passed down to the constructors for the appropriate classes. So for example, disk GB is the size of the disk in gigabytes. That's passed down to the disk aggregation object for construction. Again, I've got no destructor other than the default destructor, and my display delegates display to the objects concerned. Because my PC object is composed of a disk, a display, and a printer, it can call the appropriate displays in the relevant classes. This methodology works fine. It uses recognized OO techniques of inheritance. However, it does have a number of drawbacks. The PC is constructed using multiple inheritance. Multiple inheritance is not supported by many languages. In fact, none of the .NET languages will support multiple inheritance, and Java will not support multiple inheritance from classes. Another disadvantage is that whenever we create a PC object, we always get one disk, one screen, and one printer. Many PCs don't have printers attached. However, using this methodology, we're forced to have one. Another disadvantage is, what if we want multiple disk drives? Using this methodology, we can't implement that. We have a single disk, a single display, and a single printer. Therefore, for this type of operation, multiple inheritance would not really be recommended. Let's look at an alternative. I'm going to use the same printer, disk, and display classes, as I've used for the inheritance example, but instead I'm going to use composition. Here's my PC class with composition. As you can see on line 10, there is no inheritance involved at all. My constructor is vastly simplified. I've put a constraint on my constructor and said that a PC must have at least one disk. So the constructor takes the size of the initial disk as a parameter and then does something with it. Let's take a look at the data starting on line 80. Rather than having a single disk, a single display and a single printer, I've decided to use a vector. A vector is totally dynamic. It can contain 0 through to n disks. My constructor places the first disk in the vector. It does nothing with displays or printers. These are optional. We can have 0 through to n displays and 0 through to n printers. The destructor from my PC class goes through each of the vectors, deleting the items in the vector. I've created a new disk aggregation object in the constructor, and in various other parts of the code I also create new displays and new printers. These should be deleted in the destructor. I have an add disk function. If I want to add more than one disk to my configuration, I can call add disk, tell it the size of the disk, it will add that new disk to the disk's vector. Similarly with displays. I can tell it the screen size I want for the display, and it will add that onto the end of the displays vector, and again for PCs. And as the comment on line 56 and 57 says, we could or should add routines to remove disks, screens and printers. Most PCs these days are plug and play. We should, strictly speaking, implement that methodology in our class. It's simple to do and I've left it out for brevity. The display function now displays more than one disk, more than one display and more than one printer. It simply goes down the vector, delegating the display down to the appropriate object. So it'll go down the disk's vector, calling display disk on the disk object stored in the vector, similarly with the displays and the printers. Let's look at the code to run these two methodologies. With inheritance, I create a PC inheritance object called myPC, and I pass it the parameters to construct a 1024 GB disk, a 28-inch screen, and a printer that scans, does not fax, and prints in monochrome. I have to pass my PC inheritance constructor all the information required to create the objects that it's going to inherit from. I can then call display on my PC to display those attributes. With composition, the code is a little bit longer. I create a PC composition object called myPC2. The constructor for myPC2 must take the size of the compulsory disk. So I say I'm creating a PC initially with a 1024 GB disk. I can then proceed to add extra peripherals to my PC, and if I had the capability I could remove them as well. In my case I've added an initial disk of 2048 GB and two displays of 28 inches diagonal. I then call the display. Although the code is a little more complex for composition, it is by far more versatile and is the recommended way of implementing aggregation. This hands-on lesson is designed to test your knowledge of relationships. In the Working Files folder for this lesson, you'll find various files. These files should be imported into your chosen development environment. The files are course-event-relationships.h and .cpp, events-location-relationships.h and .cpp, global-relationships.h, person-relationships.h and .cpp, trainer-relationships.h and .cpp, and finally hands-on-relationships.cpp. Hands-on-relationships.cpp is the main program for this exercise, and it contains a set of instructions in comments at the top of the file. Your task is to remove all references to the enum for the course event class and add a fixed without custody reference to the new event location class within the course event class. This will involve a reference member variable, changes to the constructors to initialize the reference, and code in the main program to create a location object before you create the course events object. For the second task, we already have a trainer class. Your task is to add a without custody variable association relationship to the course event class. This will involve adding a pointer variable for the trainer and an addTrainer method to set the trainer. You'll also need to add code in main to create a trainer to test your code. You should note that additional modifications may also be required to display the location in trainer. A sample solution is available in the working files folder with files suffixed with the solution. This lesson introduces operator overloading. We've seen that you can perform arithmetic and comparisons on numbers and even on pointers. However, as things stand, we can't perform arithmetic on objects. We can perform simple comparisons on objects to determine whether two references or pointers refer to the same object, but we cannot compare the contents of objects directly using the standard comparison operators. Let's have a look at where this might be useful. I've created a simple class, Employee Overview, which contains a default constructor and an overloaded constructor. The overloaded constructor initializes three data members: name, which is of type string, salary, which is of type double, and day's holiday, which is of type int. The destructor has been defaulted. I've also got three member functions to return the name, salary, and day's holiday. These are query functions, so in keeping with usual practice, I've made them const member functions. This code uses these classes in a slightly different way to what we're used to. I've created 5 employees. The first two are the same, Fred Flintstone with a salary of $10,000.99 and 5 days holiday. And then 2 additional employees, Batman and Popeye, with 2 different salaries and 1 and 30 days holiday respectively. Last employee is a default constructed employee. It would be nice and intuitive if we could simply add employees together. In this case, I'm giving the plus the meaning that it adds the salary of 2 employees. So if I add employee 1, employee 3 and employee 4 together, what I'm expecting to get out of it is a new employee, employee 5, which contains the sum of the salaries of employee 1, 3 and 4. Using this intuitive syntax, I should be able to get the salary from the new employee 5, divide it by 3 to work out the average salary for my company. In addition, I've added 2 other operators. I've added the plus plus operator both in prefix and postfix form. The meaning I'm going to give this is that it will give Fred an extra day's holiday. Secondly, I've introduced the asterisk equals operator. The meaning I've given this is that it will give Popeye a 10% pay rise. Employee 4 refers to Popeye, asterisk equals 0.1 will multiply the salary by 0.1 or 10% and stick the result back into employee 4. Finally, on line 28, I've used the equals operator to compare 2 employees. I'm not trying to compare 2 references to employees here. What I'm trying to say is the contents of employee 1 and the contents of employee 2 the same. In the case of my program, they should be. Employee 1 and employee 2 are identical. As you can probably see at the moment, none of these operators will work. I've got an error on the plus saying no operator plus matches the operands to employees. I've got another error on the plus plus operator, a similar error on the asterisk equals operator, and finally, same error again on the equals operator. The compiler can't generate code to compare 2 employees. What should it compare? What if the 2 names are similar but not the same? What if we have Fred F. Flintstone for one of the employees? Is that the same employee as Fred Flintstone? Perhaps in your situation it might be, so you can implement some sort of fuzzy matching. However, the compiler cannot do anything like this, so it doesn't bother. One way of implementing, for example, a comparison would be to put a compare routine into my employee class. However, that means that I've got to call emp1.compare and pass it emp2, for example. Should I call the function compare? Should I call the function check? It's not at all intuitive. It's far better to use operator overloading in such cases. Once the compiler determines that an overload is available for an operator, then we'll use that overload wherever it needs to. There are 2 methods of overloading operators, and each has their own merits. The 2 methods are global operators and class member operators. These are explained more in future lessons. This lesson demonstrates techniques for coding some global operators. Let's take a look at some code that we're going to use with our global operators. I've used an employee class, employee global operators, to create 5 employees. Employee 1 and employee 2 are effectively the same employee, they contain the same data. Employee 3, employee 4 are different employees, and employee 5 is a default constructed employee. On line 14, I add employee 1, employee 3 and employee 4 together. The result is assigned to employee 5. The meaning I'm giving this is that if I add an employee to another employee, it adds their salary together. So employee 5 should contain the sum of employee 1's salary, employee 3's salary and employee 4's salary. I should then be able to get the salary from employee 5, the total, divide it by 3 to get an average salary. On line 21, I multiply an employee by 0.1. The meaning I'm giving this is that when I multiply a salary by a figure, it gives that employee a pay rise. In this case, 0.1 represents a 10% pay rise. To check that this works, I've done an employee4.getSalary and printed it out. On lines 26 to 38, I've used a comparison operator. If employee 1 equals employee 2, then print out duplicate employee. Employee 1 and employee 2 are both Fred Flintstone, they are effectively the same employee. I then said if employee 1 equals employee 3, see out duplicate employee, else see out different employees. As we've already seen, without operator overloading, this code will not work. My employee class contains all the code necessary to construct an object, destruct an object, and get the data members from the class. However, in this module, I've also declared extra functions. These functions on lines 41 to 58 are not members of the class. They contain no scope resolution operator, they're not scoped to the class, they are global functions. I've broken best practice here by putting code into a header file. However, for the purpose of this demonstration, this method will work, but functions are normally coded in CPP files. Let's have a look at the first operator on lines 41 to 45. This is the plus operator, which overloads operator plus. Operator functions are all called operator and then the operator they're overloading. So on line 41 I have operator plus, on line 47 I have operator asterisk equals, and on line 53 I have operator equals equals. Operators always return a value. In the case of adding 2 employees together, I want to return a new employee. The operator plus function is a binary operator. There is a left-hand side of the plus and a right-hand side of the plus. When I add 2 employees together, the compiler converts the plus into a call to operator plus, passing the left-hand side as the first parameter and the right-hand side as the second parameter. As you can see, I've also adhered to convention by passing const references to employees. The code within the operator plus creates a new employee, called temp in my case, and creates it using a constructor. The constructor passes a name of result into my temp, a salary of left-hand side.getSalary plus right-hand side.getSalary, and a day's holiday of 0. I have to use accessor routines in this operator function because it's not a member of the class and therefore has no access to the private data members of the employee class. Once I've created my new temporary object, I can return it. Let's have a look now at a slightly different case, operator asterisk equals. In the case of this operator, it appears that I've declared the operator within the class. That's not quite true. What I've said is the operator asterisk equals function with this signature is a friend of this class. Friend functions are generally frowned upon. If I say that this function is a friend of this class, it means that that function has unlimited access to the private data members of the class. On lines 47 to 51 you can see that rather than using accessor functions to get hold of the salary, I've accessed it directly. This is only possible as a result of the friend keyword. Many people frown on the use of the friend keyword because they say it breaks the major OO principle of encapsulation. It allows unlimited, unprotected access to the private data members of a class. That's the downside. The upside is that it's marginally more efficient because rather than having to use accessor functions, I can access the data members directly, thus avoiding the overhead of function calls. My personal preference is not to use friends, as I feel that the OO principle of encapsulation far outweighs any performance advantage. The last operator function that I've implemented is operator equals equals. This function returns a Boolean and again takes 2 employees as parameters. Again, to adhere with convention, I've used const employee reference, and since this function is not a member of the class, nor is it a friend of the class, then I have to use the accessor functions to get the name, get the salary, and get the day's holiday. And I compare the left-hand side with the right-hand side and return true if they're all equal. Returning to my code to use these functions now, I'll run this code, but let's have a look at what we're expecting. On line 16, I calculate the average salary. That will be the average of 10,000.99, 50,000.55, and 9,999.99, and I see out the average for all employees. Popeye currently has a salary of 9,999.99. I then give him a 10% pay rise and see out the new salary. Finally, in this code, I compare employee 1 with employee 2, and if they are equal, which they are, I output duplicate employee. And then compare employee 1 with employee 3. I compare Fred Flintstone with Batman. If they're equal, I output duplicate employee. They're not equal. Else, I output different employees. And here's my output. The average salary for all employees is 23,333.84. Popeye's salary was 9,999.99. It is now 10,999.99. Employee 1 does equal employee 2, so I get duplicate employee. Employee 1 does not equal employee 3, so I get different employees. In previous lessons, we've looked at overloading operators. It's all very well being able to add 2 classes together. However, sometimes we might want to add an integer or another basic data type to an object of a class. For example, if we had an employee class and an employee object, a worker object, we might want to add 10,000 to that object to increase the employee's salary by £10,000. Let's look at an example where we're holding the stock of an item in the store. We have a class called stock item. The constructor, the default constructor for the stock item, sets the item name to unknown and the stock level to a default value of 0. I've also coded an overloaded constructor on lines 16 to 20, which initializes the item name to a string that's passed into the constructor and the stock level to an integer stock that's passed into the constructor. In this example, I've defaulted the destructor. I've also added a display function to my class. This is purely for convenience so that I can display the current item name and stock level. Within this class, I've overloaded operator plus as a friend function twice. If you look more closely at these 2 friend declarations on lines 29 and 30, you'll see that they're almost identical, except that in the first one on line 29, the stock item, the class itself, comes first and the integer second. In the second example on line 30, the integer is first and the stock item is second. This is so that we can do 1 plus stock item or stock item plus 1. The 2 private data members are item name and stock level. The 2 operator plus functions are almost identical too. We create a temporary stock item to return and we use left-hand side item name and left-hand side .stock level where the stock item is the first parameter, and where the stock item is the second parameter we use right-hand side .item name and right-hand side .stock level. Because we're using friend functions, this code's fine. If I hadn't used a friend function, then I would have had to have used get and set accessor routines to do this. Let's look at the code to use this class. I've created a stock item called sprockets, which is initialized to a quantity of 1,000 sprockets, and another stock item called widgets, which is initialized to 200 widgets. I then got 2 uninitialized or default initialized stock items, new stock 1, new stock 2. I then tested the 2 friend operator plus functions. The one on line 10 calls the overload that has the class first and the quantity second. The one on line 11 calls the overloaded operator plus that has the quantity first and the class second. Let's run this code. Adding 1,000 to sprockets doesn't change sprockets or widgets. However, the new stock shows that the name has been transferred across and the stock level is now 2,000. And in the case of new stock 2, the widget's name has been passed across and we have a new stock level of 700. We've already established that we can write operator functions as global operators. This lesson shows that you can make them symmetrical operators, so that we can do sprockets plus 1500 plus widgets. Membered operators will be discussed in another lesson. However, it does pose the question, which operators are best overloaded as global operators? In fact, there are several answers to this question. Operators that are required to be symmetrical, in the fashion that I've illustrated here, can only be overloaded as global operators. Operators that you wish to subject to accessor limitations, i.e. public, private and protected within the class, must be member operators. Operators which only modify the left-hand operand may be declared as member operators. So if I only wanted to do calculations as in line 10 in this example, I could have used that as a member operator. However, the fact that I wanted to do it in the reverse on line 11 means that it must be a global operator. Certain functions can only be overloaded as member functions. For example, operator equals. Member function operator overloading may also be preferable if the data that you wish to access in your operator is complex or not easily accessible, or even secure. Certain operators can only be overloaded as global operators. For example, the insertion and extraction input and output operators. My personal preference is to follow the OO rules of encapsulation and wherever possible use member operators. We've seen in several earlier lessons that we can overload operators. In this lesson, we'll look at two operators that are only overloaded as global operators: the insertion and extraction operators, the input and output operators. So far in this course, I've usually used the display class member function wherever I want to demonstrate a class and its state. It's not possible simply to see out or see in an object, as the compiler just wouldn't be able to create code to do it. How do you want the output? Do you want it comma separated? Do you want it tab separated? Do you want each data item on a new line? And so on. It just cannot do it. In this example, however, it looks as if I'm actually seeing and see outing objects. I've got two objects of type stock item, a sprockets and a widgets, and I've used the see-in operator to read data into those items. And then on line 13, I've used the see-out operator to display them. If we look at the class definition, we'll see how this is implemented. My stock item class has a default constructor with an item name of unknown and a stock level of 0. It also has an overloaded constructor, which in this example I don't use. The destructor is defaulted, and I've added class member functions to get the item name and get the stock level. These are both query functions, so they're both set as const member functions. These two functions simply return the two data members. I've implemented the input operator as a friend function. The input operator, since it's a friend function, has direct access to the class private data members. This is the implementation of the iStream input operator. iStream is the file which is used for see-in. In most cases, it's the keyboard on the PC. This operator must return a reference to the stream. If we look at the code on line 43, we can see that the first thing that will happen is that I input an item name. That must then return a reference to the input stream so that I can use that reference to input the second item. Finally, at the end of that function, I return the reference to the input stream. There's no reference in this code to see in or see out. It's simply a file. If we look at the output operator is not defined as a friend in the class. Therefore, it has no access to the private data members of the class. So I have to use the get functions, getName and getStockLevel within this function. Other than that, it's virtually identical to the input operator. If we run this code, it's asking me for an item and a quantity, and it's asking me for a second item and quantity, and that is the result of my cout. Item colon, get item name, sprockets in my case, stock level, and then the value. One advantage of using accessor functions rather than friend functions is that friend functions have direct access to the class data members. This can be faster. However, it allows me to enter any value I like directly into the class. This really breaks the rules of encapsulation. One of the main reasons for encapsulation is to ensure that you can't access the data without going through any checks necessary first. These are implemented in the getSet functions, which are usually public. In this chapter, we've looked at global operators. The types that we've used with the global operators have been the classes on which the operator is performed and the simple data types. This hands-on exercise is an extension of what we've already covered. The files for this hands-on exercise are located in the Working Files folder. The files contain a transaction class, declared in transaction.h and implemented in transaction.cpp. Your task is to implement an insertion and extraction operator for this class. The input operator should input the transaction type as D for deposit, W for withdrawal, followed by the transaction amount. The operator should write out the transaction ID, the type, and the amount. The account class contains a vector of transactions on line 16. Your task is to implement an output operator to produce a statement of all transactions. You should already have coded an output operator for the transaction class. It makes no sense to duplicate this code, so after outputting the account details, you can delegate displaying of transaction details to the transaction class. Finally, add a plus equals operator to the account class that adds a transaction object to the vector. See the code in the main procedure for the implementation. A full set of instructions is given at the top of the main function in hands-on.cpp, and code to test this hands-on is shown. As usual, a sample solution is provided in the Working Files folder, with all solution files have the suffix solution in their file name. In previous lessons, we've looked at global operators. In this lesson, we'll be looking at class member operators. If you've been following the previous lessons on this course and completing the hands-on exercises, you should be familiar with the code that I've got in front of me. In this code, which previously used global operators, I've stripped out most of the global operators, only leaving the input and output operators within the two classes. That's the transaction and the account class. Let's have a look at some of the operators that I've put into these classes. The account class now has 4 member operators. Line 14 is the declaration of a member operator plus equals. Line 15, the declaration of a member operator plus. Line 16, a Boolean operator equals equals. And line 17 is an overloaded subscript operator. We'll look at how these work in a moment. In the transaction class, I've overloaded operator not equals and left the OStream operator output. Since most of the operators are in the account class and operator not equals is just a reverse of operator equals equals, we'll skip looking at the transaction class and go straight to the account class implementation file. The first function in the implementation file, apart from the constructor, is an operator plus equals. Operator plus equals adds a value to the current object. In this case, I've chosen to add a transaction into the account. So the parameter to operator plus equals is not a number, not an account, it's a transaction in my case. The code for this operator function takes the transaction that's passed as a parameter and stores it into the vector of transactions using the mplaceBack routine. In order to maintain copy safety, etc., the transaction that's passed in is a const reference to a transaction. This will prevent any copy constructors being called and also avoid the transaction being altered within the operator plus equals function. Because I'm adding the transaction to myself, and this is a member operator, the this keyword can be used to represent the current object. This is a pointer to the current object, so asterisk this is the current object. I return a reference to an account, which is the left-hand side, or this account object. And the line 11 shows that I return asterisk this, which is a reference which is safe because the current object already exists. Operator plus, on lines 14 to 30, shows a slightly different variation. In operator plus, I've coded it so that I can add 2 accounts together. The result of adding 2 accounts is the balance of the 2 accounts added together. First thing I do is declare a balance variable, then I have to go through all the transactions in the 2 account classes, that's this account object and the right hand side account object, adding the transactions, depending on whether they're a deposit or withdrawal, into the balance. After line 24, I should have, within the balance variable, the sum of all the transactions in both the left hand side and the right hand side. The right hand side on lines 17 to 20 and the current object or the left hand side on lines 21 to 24. Then I create a new transaction object, temporary transaction. I've set it as a D, a deposit, and I've created it with the overloaded constructor for a deposit with the balance. On line 26, I create an account called TempAcc with a name of grand total balance, and then on line 27 I add my temporary transaction created on lines 25 into the temporary account, and it's this account which is returned by the return statement on line 28. Using this mechanism, effectively I've added the two balances together, the two account balances. I've created a new account with a single transaction that contains the sum of all the balances. On lines 32 to 52, I've overloaded the equals operator. In this context, I've said that two accounts are the same account if the name is the same, if the number of transactions is the same, and if the individual transactions themselves are the same. I set up a Boolean variable on line 34 and set it initially to true. If the account name is not equal to the right-hand side of the account name, remember I'm using a binary operator here, A equals B, where B is the right-hand side. If the two account names are not equal, then I return false straight away. I then check the transactions vector in both the current object, the left-hand side, and the right-hand side transactions vector. If the two sizes are not equal, then the number of transactions differs between the two accounts, so I can immediately return false. If I get to line 43, the name and the number of transactions are both equal. I then go through the transactions vector, comparing them with each other. This is where the not equals operator in the transaction object is called. As soon as I find one that isn't the same, I set same to false, break out of the loop, and return same. If same has become false due to a transaction which isn't the same, then it will return false. If, however, the name, account name, the number of transactions and all the transactions are equal, the Boolean variable same will still be true, so I return true. Operator square brackets allows my class to act like an array, or a container. It's overloading the square brackets operator. We'll see how this is used shortly. The operator square brackets is passed an index, which is an index into the array. My transactions is effectively an array. It's actually a vector, but they're, to all intents and purposes, they're the same, because a vector can be accessed via square brackets. So if I pass in the index into my operator square brackets, it will return a reference to that transaction. Once I have a reference to the transaction, it can be replaced or it can be queried. Finally, in the account class, I've got the overloaded output operator that we've seen before. This is not a member operator, so I won't go through it here. Looking at the code for this class, I create two accounts, Bill Gates and Laureen Powell Jobs, who was Steve Jobs' wife. I create 6 transactions, 3 deposits, 3 withdrawals, and I assign transaction 1, 2 and 3 into Bill Gates. This is using the plus equals member operator. That operator took a transaction as a parameter. As far as the compiler is concerned, it sees line 15 as this: Bill Gates.operator plus equals T1. In other words, it calls operator plus equals on the class and passes it transaction T1 as the parameter. If we go briefly back to the account class and look at operator plus equals, Bill Gates is this, the left-hand side. That's the object I'm working on, and the transaction T1 is passed in as the right-hand side of the operator. This dot operator plus equals T1. Similarly with Laureen Powell Jobs, I have added T4, T5 and T6 into the account. I can still see out an object because I have left in the global operator for outputting. Next I'm going to look at operator plus. If you remember, I said that operator plus added 2 accounts together and returned a new account object with a single transaction, which was the sum of all the transactions in the left-hand side and the right-hand side. To that end, I create a total balance account. I add together Bill Gates and Laureen Powell Jobs. Operator plus will go through Bill Gates, getting the current balance for Bill Gates, through Laureen Powell Jobs, getting the balance for that account, create a new account with a single transaction, which is the total balance, and return it. That gets assigned to total balance, and we can see what the total balance is by couting it. Next, the equals operator. All the Boolean operators, comparison operators, return a Boolean. Initially I'm testing Bill Gates against Bill Gates. Obviously they're both the same account, so I should get out of that, cout Bill Gates equals Bill Gates. When I compare Bill Gates with Lorraine Powell jobs, the name of the account is different, the number of transactions is the same, but the transactions are different. In my case, the equals equals operator will short circuit straight away because the name of the account is different, it should return false. And in that case, Bill Gates is not equal to Lorraine Powell jobs. Let's run this code and just check that it does as we expect. Those are the three transactions, ID 0, 1 and 2, that I added to Bill Gates. There is a deposit of 5,000, a deposit of 5,000 making a total of 10,000, and a withdrawal of 1,000. The balance there for Bill Gates will be 9,050. For Lorraine jobs, we've withdrawn 1,000, withdrawn another 1,000, and deposited 10,099. The balance for Lorraine jobs therefore will be 8,099. Adding those together, the total balance for the two accounts is 17,149. Finally, the test against Bill Gates determines that they are equal, and Bill Gates is not equal to Lorraine Powell jobs. We've already established that we can write operator functions as global operators or member operators. Global operators were discussed in an early lesson. However, that still poses the question, which way should we use? Which operators are best overloaded as member operators? And in fact there are several answers. Operators that are required to be binary symmetrical operators can only be overloaded as global operators. Binary member operators take a single parameter, which is always the right-hand side of the operator. So only the left-hand side may be modified. Further, this must be a modifiable item, it can't be a const item. Operators that you wish to subject to accessor limitations, i.e. public, private and protected, must be member operators. Global operators have no concept of public, private and protected. Certain functions can only be overloaded as member functions. For example, and we haven't looked at this operator yet, but we'll do shortly, operator equals can only be a member operator. Member function operator overloading may be preferable if the data that the operator requires access to is complex, not easily accessible, or needs to be secure. Only member operators are encapsulated within the class. For this reason, my personal preference is to follow the OO rules of encapsulation and wherever possible use member operator functions. Previously in this chapter, we've looked at overloading binary operators as member functions. This lesson looks at overloading unary operators as member functions, and in particular we're going to concentrate on overloading the more complex plus plus operator. The minus minus operator follows the same methodology. The plus plus and minus minus operators come in two different forms, prefix and postfix, and examples of using them are in the example code on the screen. Plus plus T1 is a prefix increment of T1. T2 plus plus is a postfix increment of T2. When used as part of an expression, as on lines 68 and 71, the prefix and postfix have decidedly different results. This poses a bit of a problem for us, because the operator we're going to overload is operator plus plus. The function that overloads operator plus plus is called operator plus plus. Therefore, we need some way of distinguishing whether we're doing a prefix or postfix operation. How can we distinguish that? The simple answer is that we can't. The longer answer is that the compiler performs a fiddle for us that enables us to overload the operator correctly. The prototype and the implementations for the operators is shown in the time class. Let's have a look at it. The first couple of functions in the time class are constructors. First one, a default constructor, which initializes hours to 0 and minutes to 0. The next constructor, starting on line 12, initializes hours and minutes to two values passed into the overloaded constructor. Then on lines 17 to 20, we've got a simple display time function, which displays the values in hours and minutes. This is followed by our two operators. Let's look at the prefix operator first. Lines 22 to 31 are the prefix version of operator plus plus. We're working on the current object here. We're incrementing minutes. If minutes is greater than or equal to 60, then we subtract 1 from it and increment hours. Operator plus plus must return a value. It returns the current object. Because of that, we can return asterisk this, and the time that we return can be a reference, because the current object obviously exists prior to calling operator plus plus. The postfix operator, however, is a different matter. The postfix operator is on lines 33 to 46. The strange thing about this operator is that it takes a parameter. In calling the operator, we don't pass any parameter at all. However, when the compiler sees a postfix version of plus plus in a piece of code, it converts it into operator plus plus and passes a dummy parameter into it. It's this that allows us to overload operator plus plus slightly differently for postfix. It follows the rules of overloading. Operator plus plus prefix has no parameters. Operator plus plus postfix takes an integer parameter. We never need to know what the value of this parameter is. It's just a dummy parameter passed into the function. Postfix must return the object in the state it was before the operator was called. Therefore, we have to take a copy of the current object. To do this in this case, I've created a time t and used the overloaded constructor to pass it the hours and minutes from the current object. T is therefore a temporary copy of this object. Subject to copy constructor rules, you could use a copy constructor to take a copy of the current object and pass it asterisk this. Next, we increment this object in the same way as we did for the prefix operator. Increment minutes if minutes is greater than or equal to 60, add 1 to hours and subtract 60 off minutes. The current object is now incremented. We must return something which is the same as the object before it was incremented. This has been saved in T, so we return T. Because T is a temporary object, a local object within this function, we can't turn a reference. If we go back down to our code again, T1 starts off as 11:59. When we increment it, it should go to 12 o'clock. Increment it again, it should go to 12:01. Standalone ++T1 and T2++ have exactly the same effect. We're disregarding any return from the postfix. In the case of T2, it starts off at 10:40. Adding 1 to it will make it 10:41. Adding another 1 to it will make it 10:42. Finally, I've got a few lines of code which test the return value from the postfix operator and the prefix operator. Line 63 takes T1, which is now 12:01, adds 1 to it to make it 12:02. That value is returned. T3 should also be 12:02. And I display T1 and T3, they should both be 12:02. In the case of the postfix operator, I increment T1, which is currently 12:02. T1 will end up as 12:03. However, the value before it was incremented is returned. Therefore, T1 will be 12:03, T3 should be 12:02, and I display them. This time I'm going to run it. After the first increment, we have 12 o'clock, and then we have 12:01 for T1. For T2, we started at 10:40. After the first increment, we go to 10:41, and after the second increment, we go to 10:42. For T3, T3 equals plus T1. T1 started at 12:01. This time I'm going to run it. 02. T1 is 12:02. T3 is 12:02. With the postfix form of the operator, we increment T1. It was 12:02. T1 becomes 12:03, but the value that's returned is T1 prior to the increment 12:02. Sometimes people are told that the ++x operator, the prefix form, is more efficient than x++, the postfix form. If you look at the code in my program, you can see why this is the case. Postfix has to create a temporary object. On the built-in data types, prefix and postfix are generally roughly the same speed. This is because modern optimizing compilers can generate code which is very efficient and makes the two more or less the same. However, for overloading within your own data types, within classes, prefix is always more efficient. In fact, we can make a statement that for user-defined data types, ++x should usually be faster and never slower than x++. In an earlier lesson, we learned of the need for a copy constructor. Let's have a brief review of the code and the reasons why this was needed. We said that a copy constructor might be required if a class was responsible for managing resources wholly within the class. In my case, in this example in front of you, I have allocated a pointer char asterisk name. Within the constructors, I allocate memory for the name. In the case of the default constructor, it's a new char 10. In the case of the overloaded constructor, it news the memory to the size that's required to store the parameter. In the destructor, I delete the name. In other words, the management of the name pointer is entirely withheld within the class. The need for the copy constructor is because when we allow default copying of an object from one object to another, it does a shallow copy. Only the pointer is copied, not the memory at the pointer. We therefore end up with two pointers pointing to the same area of memory. If we simply try and delete the memory in the destructors for both of those objects, the first destructor will indeed do the delete. However, any subsequent destructor which points to the same memory will fail. To get round that, we code our own copy constructor, and a sample copy constructor is on lines 17 to 22. Looking at some code, lines 9 and 10 create two separate objects. Lines 15 and 16 create two objects. However, in this case, me2 is created using the overloaded constructor, and line 16, clone 2, uses a copy constructor. Because I've implemented a copy constructor in my class, this code will work. Lines 21 and 22 illustrate another use of the copy constructor. Line 21 creates an object me3 using the overloaded constructor. Line 22 looks as if it's assigning. When the compiler sees assignment on initialization, it converts this to a call to the copy constructor. We also said that certain STL functions, and in particular vector was the example I gave, use copy construction in functions such as pushback. If you intend to use the STL, the standard template library, and you have dynamically allocated pointers within your class, then it could well be advisable for you to create a copy constructor to overload it within your class. We'll now take a look at an example which won't work. I've got two persons again. The first person, him1, is created using an overloaded constructor. It creates an object him1 with Fred Flintstone as the parameter to the constructor. This is OK. Person CC him2 is a default construction. Further down the code, in my case on line 34, I do assignment. This is not the same as on line 22. Line 22 calls the copy constructor because the compiler detects that this is assignment on initialization. However, line 34 could occur anywhere in the code. I could have used him2 for various other purposes in the meantime, and now I'm just copying him1 to him2. If I run this code, you can see that it fails. The reason that it fails is for exactly the same reason as the copy constructor. When I copy him1 to him2, it's a shallow copy. In fact, this copy, the assignment, is an even worse case, because the pointer for the memory in him1 is assigned to the pointer for the memory him2. This overwrites the pointer him2. We've immediately lost access to any memory allocated within him2. So not only have we got an error on deletion of these objects, we've also got memory leakage in the meantime. The fact is that if you need to create a copy constructor, then you usually also need to create an assignment operator too. The compiler will provide you with a default one. However, it's a shallow copy. If you want the deep copy, you need to overload operator equals. This will be covered shortly in another lesson. This lesson looks at the implementation of an assignment operator, or operator equals. For convenience, I've created an example from the copy constructor code used previously in this course. Let's have a look at the header file containing the declaration of the person class. As you can see, I've got a char asterisk name variable declared private in this class. This is what causes operator equals and copy construction, when performed in the default manner, to fail. In order to make assignment of person objects work, we have to declare our own operator equals and implement it. The compiler will provide one for us, as we've already said, but it will be a shallow copy and will cause problems with pointers. Line 13 is the statement that will cause the problem. Because I've coded my operator equals, it will actually work at the moment. However, rather than just showing you the prototype for the operator equals function, we're going to try and deduce it based on what we already know. When the compiler sees a statement of the form him2 equals him1, it will actually convert it into the following. So given that, let's deduce the prototype for our operator equals function. I'll do it in line here, and then we'll look at it in the header file. One thing we do know is that an operator must return some sort of value. Since I'm working on a person CC object, the return type must be person CC. The next question is, can we return a reference? We'll hang on to that thought for now until we actually get to look at the code for this procedure. The function itself is called operator equals. It's passed a parameter of the right hand side. him1 is of type person CC. Almost there, except that we're passing a person by value. Objects should always be passed by reference. Furthermore, if we're assigning him1 to him2, we wouldn't expect him1 to be changed as a result of that assignment. Therefore, the parameter must be a const reference. Okay, now back to the issue of the return type. What are we going to return from our operator equals? Well, let's have a look at another statement. A equals B equals C. We can chain assignments together. The first assignment that will be done is B equals C. That will return B. By tradition, we return the left-hand side of any operator. Since we're actually working on the left-hand side in our operator equals function, we're returning this object. This object is referenced by asterisk this. Since this object already exists, we can return a reference. That should be the prototype for our operator equals. Let's remove those lines and go and look at our header file. We return a reference. The function is called operator equals, and we pass in a parameter of a const person ampersand, a const reference to a person. In actual fact, it's almost identical to the copy constructor, except that a constructor never returns a value, whereas operator equals must return a value. And the code is very similar too. There's the code for the copy constructor. It calculates the length of the name in the right-hand side, or the object that's being constructed from, uses some memory, and then copies the name from the parameter person into the person being constructed. Operator equals is very similar, but has a couple of extra steps. Lines 39 to 41 are almost exactly the same as the steps for the copy constructor. Line 43 is the return statement. Line 38 is necessary. Why? Well, we're working on an object which has already been constructed. If it's already been constructed, memory at the name pointer will already have been allocated. We can't just copy the right-hand side name into that memory, because the right-hand side name may be much larger. Therefore, we have to delete the existing name, create a new name, memory, and copy the data in. The only other consideration in this function is line 36. Why are we checking whether this equals the right-hand side? Again, let's look at a bit of code. If I said him2 equals him2, that will take us into operator equals with that code. The left-hand side and the right-hand side are the same. Without that code, it will delete the name in the left-hand side. Unfortunately, the left-hand side is also the right-hand side. So we'll be deleting the name in both objects, which are really the same object. Therefore, when we try to do the string copy from the right-hand side to the left-hand side, we're trying to copy from a deleted name. So in operator equals, we must check that we don't have the same object on both sides of the operator. If I return this code to a runnable form and run it, we'll see that what we end up with is code that actually works, and we end up with two objects, him1 and him2, both with the same name. In an earlier lesson, we looked at conversion constructors. These allowed us to construct one object from an object of a different type. Conversion operators allow us to do something similar, but are post-construction. They allow us to convert one type into another. Just like conversion constructors, conversion operators on more recent compilers can also be declared explicit to force explicit casting. Just like other operators that we've overloaded in previous lessons, the name of the member function is operator followed by the type that they're converting to. Let's take a look at a simple example. On the screen I've got a class, convertFromOperators. That class contains a single data member, a double d-value. I've initialized this variable in place. This will only work on modern compilers. I've also defaulted the constructor and destructor. The rest of the class consists of a series of operator functions. The first one, on lines 13 to 16, converts my class into a double variable. The code in it simply returns the value within the class, the double value. Note that just like conversion constructors, conversion operators don't have any return value. This is because the compiler can deduce the return type from the name of the operator function. On lines 18 to 21, I declared another operator function, this time operator int, and I declared this function as explicit. The code for this function takes the double value stored in the class, performs a static cast on it to convert it to an integer, and returns the integer. Lines 23 to 26 are another operator function. This time the type is convertFromOperators, which is this class, asterisk. In other words, it converts this class as an object to a pointer to an object. Since this is a pointer to the current object, I can simply return this. Lines 28 to 31 are another operator function. This time I've chosen to use a char asterisk as my operator. In fact, it's a const char asterisk, and the return value is the name of the class. This is similar to how the two string operators work in .NET. They return the name of the object, or the type of the object. Let's look at how this code is used. I create a convertFromOperators called convertFrom. That will initialize my double. Then I declare some variables, double d, int I, convertFromOperators asterisk, or pointer to convertFromOperators, called pconvertFrom, and finally a char asterisk string, which I've newed to 255 characters. Line 13 takes my object convertFrom and assigns it to the double. This will work because I've coded an operator double. It will perform an implicit conversion to a double. On line 15 I've coded an implicit conversion from my object to an int. The comment says implicit conversion to an int gives an error. However, in my case, no error is given. This is because of an unfortunate side effect of the way I've coded my class. It can't do an implicit conversion to an integer. However, it can do an implicit conversion to a double and then assign that to the integer, which will give a warning when I try and compile this code. Normally, if that side effect wasn't present, line 15 would give a compilation error. If you encounter that type of error, then line 17 is the solution. If you can't perform an implicit cast because the conversion operator has been declared explicit, then you must do a cast to convert the types. Line 19 is an implicit conversion. pconvertFrom is a pointer to a convertFrom. I'm assigning a convertFrom object. This will call the implicit conversion to convertFromOperators asterisk operator. And just to prove it works, I've called the display function via the pointer. Line 22 is another interesting side effect. I cout convertFrom. Which operator is this going to call? Well, you might expect it to call the char asterisk conversion, so that I get the class convertFrom message. It doesn't. It calls the double conversion. So what I'll actually get out of that cout is the double held within the class. Line 25 and 26 are the implicit conversion to char asterisk. String copy, or strcopy underscore s, takes as its second parameter a const char asterisk type variable. Therefore, implicit conversion will be performed from my object to a const char asterisk that will be used in the string copy to copy it into the char star string, and that's what will be couted on line 26. Conversion operators are fine, but as I've mentioned a couple of times in this lesson already, you have to be aware of the side effects. My situation is a little unusual in that I do have a lot of conversion operators within the same class. This lesson gives a few guidelines and a few pitfalls to watch out for when using copying and conversion. If a class manages resources within the class and these resources are pointers, then that's an indication that you'll probably need copy constructors and operator equals. Operators should be overloaded in pairs. For example, if you overload operator equals equals, then it makes sense that perhaps you should also overload operator not equals. This is not enforced by the compiler, as it is in some languages such as .NET. However, it can be more intuitive if you do so. If you are going to overload opposites, it should only be done if it's meaningful. In C++, we can't create new operators. For example, in C++ there is no raised to the power of operator. It can be tempted to overload other operators to provide this sort of functionality. However, you should never change the meaning of an existing operator. If operator plus is adding two items together, it should not do anything different. If you do vary slightly on the meaning of an operator, For example, if you use operator equals equals to provide some sort of fuzzy comparison logic, then this should be commented. Some pitfalls: remember, the compiler will provide an operator equals and a copy constructor. However, the compiler provided ones are shallow copies. If you need to do copying and assignment of objects and your object manages resources with pointers, then you should create your own. You could of course mark them as deleted or declare them as private. That is effectively disabling copying. Remember, however, that this can have unfortunate side effects, especially if you use things like the standard template library, which in many respects require or rely on copying of objects. Overloading is a powerful feature and makes code very intuitive to use. Used wrongly, it can lead to unreadable, unmaintainable, or inefficient code. You should overload for a reason, not simply for convenience. Beware side effects. We've seen some side effects of conversion operators in previous lessons. The compiler will do its best to resolve any issues, but don't expect too much of it. It doesn't have your intelligence. Where there are any side effects, these should be commented and documented thoroughly. This lesson is your chance to put into practice what you've learned in this chapter. The files that you need for this lesson are accountop.h and .cpp, transactionop.h and .cpp, and handson.cpp. The first task is, wherever possible, convert the global operator functions that are currently in the account and transaction classes into member operator functions. Remember, not all operators can be member operators, so you need to take care here. The next task is to add an explicit conversion operator to the account class that returns the balance of the account as a double. Currently, the code in main has an error, as shown on line 27. Once you've completed all these tasks, all the errors should disappear. The initial files to this lesson are available in the Working Files folder, and there is also a sample solution with the same file names but with the solution suffix. In previous lessons, we've looked at inheritance. We've also noted that there is a keyword, public, private, or protected, which determines how a class can be inherited. This lesson takes a closer look at these three keywords and how they affect inheritance. Let's look at a simple example to illustrate these three different levels of inheritance. Here we have a base class, class A, with a public, a protected, and a private data member. Class B is inherited from class A. Within this class, I have a public function, and I try to access the variable x in the base class. This is actually bad practice because x as a variable should never be declared public. However, it also applies to functions. This illustrates that anything which is public in the base class is also public in the derived class when we use public inheritance. The protected variable y is also accessible from within the derived class. Y is protected in the derived class and is protected in the base class. Any attempt to access the variable z is not allowed. Z is private in the base class and is therefore not accessible from the derived class. Now let's try a different keyword for inheritance. Using the same base class, we've now inherited from A using protected inheritance. Protected inheritance starts to close down the access to the base class. In my function within the derived class, I can still access x, however x is protected. This means that x is no longer accessible from outside class C, the derived class. Y, which was protected in the base class, is also now protected. The variable z, which was private in the base class, is still not accessible from the derived class C. Taking this to the last level of inheritance, private inheritance, class D is inherited private from the base class A. In this case, x and y, x was public in the base class, y was protected in the base class. They've both become private in the derived class. Why might we use this methodology? Well, protected bases are sometimes useful in class hierarchies in which further derivation is needed. Private bases are sometimes useful when defining a class by restricting the interface to the base class so that a stronger guarantee can be provided. Private inheritance can be used to implement an implemented in terms of relationship. In other words, where the external interface of the inheriting class has no visible relationship to the inherited class, but it used internally to implement its functionality. A use of this is hiding low-level functionality from the class user. For example, in class A, our base class, we might provide low-level I/O routines. We wouldn't want to expose those to the user, so we could derive from our low-level base class A, private, and in the high-level class, D in my case, provide high-level routines for the user to use. The low-level routines would not be visible to the user of class D, the high-level class. However, class D could still call them. In this lesson, we'll briefly review polymorphism. Polymorphism is the act of presenting the same interface for differing underlying object types. The classic example of polymorphism uses a shape class and all the classes that can derive from it, for example rectangle, ellipse, triangle and so on. With polymorphism, derived objects will have some common data items such as colour, pen width, position, etc. However, they will also have some unique data items. A rectangle needs two coordinate points to draw it, top left and bottom right, whereas an ellipse might need a top left and the sizes of the major and minor diameters to specify the same shape. Let's have a look at an example. In this example, I've set up the classic shape system. I've got a couple of data items prior to the shape class. They're purely utility and we'll ignore them for now. Shape class contains common data. In this case, the colour of the pen and the width of the pen. All shapes that are drawn will be drawn with a pen. Therefore, this data need not be repeated in all the subclasses. Following the shape class, we have a series of other classes derived from shape using public inheritance. The rectangle class contains its specific data in the private section. In this case, as I've just mentioned, a top left and a bottom right coordinate using the point structure. It also contains a virtual draw function. This is overriding any function in the base class, and strictly speaking, I guess I should have the override keyword on my draw to make sure that it's exactly the same signature. Similarly with the ellipse, it's also derived from shape. It also has a virtual draw function. The data for the ellipse is a point structure and two integers, major and minor diameter. Finally, the triangle class also has its own data. It has a top point, a bottom left and a bottom right, all of type point structure. This example shows that the draw function does not have to be specified virtual in all the derived classes. It inherits virtual from the base class. However, it's much clearer if we include the keyword virtual in all the derived classes too. The shape.cpp file merely implements the functions in the classes defined in shapes.h. The code in polymorphism.cpp uses these shape classes. In this case, I've used a list from the standard template library to store my drawing shapes, or more accurately, to store pointers to shape objects. I use shape asterisk because a pointer to a base class can be used to store a pointer to any of its derived classes. Lines 10 to 14 add some shapes to the drawing, and lines 17 to 20 are the polymorphism in action. It doesn't matter what kind of shape I'm looking at with the shape asterisk S in the for loop. No matter what the kind of shape, the real object underneath the shape, if I call draw, the system will take care of drawing the correct shape, whether it be triangle, rectangle or ellipse. This code is by no means perfect at the moment. As I said, I haven't included override keywords. Also, I'm not taking care of my memory in this example. I've got nothing to delete the shapes at the end of the code. However, the specific issues revolving around the destruction of the objects are going to be addressed in a future lesson. In a previous lesson, I raised the issue of class destructors in polymorphic hierarchies. This lesson looks at this issue in more detail. I'll use a shape example that I've used in previous lessons. This time I've added destructors to all the shape classes. In a normal inheritance hierarchy, when you delete an object of type derived class, destructors are called for the derived class and then the base class, or base classes. In my main program, I have reduced the code to a bare minimum. It creates a new shape and a new rectangle. Both are allocated to base class pointers. I then delete both the shape and the rectangle. If I run this code, we'll see what destructors are called. Even though I've created a shape and a rectangle, and the rectangle contains a destructor for the rectangle, only the destructor for the base class is called. This is quite expected since the pointer that I'm using to access the rectangle is a pointer to a shape. The solution to this is fairly simple. We should declare our destructor in the base class as virtual. That one simple change, if I now run my code again, fixes the problem. It calls destructors for the shape, the base class, and the rectangle, the derived class. This can lead to a rule. If you're using derived classes via a base class pointer or polymorphically, then the destructor in the base class should always be declared as virtual. In previous lessons, we've looked at virtual functions and polymorphism. In this lesson, we'll be looking at pure virtual functions. We've already seen that functions are to take part in polymorphism must be declared as virtual in the base class. Virtual functions may have their behaviour overridden in derived classes. Pure virtual functions, on the other hand, must be overridden in derived classes. Let's use the shape example that we've used before to demonstrate pure virtual functions. In this example, I've commented out the draw function in the rectangle class on line 27. I've also commented out in the implementation file. I've made the draw function in the base class pure virtual on line 16. It's the equals 0 that specifies that this function is a pure virtual function. Note, however, that I've still got a default implementation of the shape draw function in the implementation file. If I compile this code, I get various errors. Let's look at the first one. The first error refers to my main function where I try and instantiate an instance of the rectangle class. It's telling me that I can't instantiate an abstract class. Any class with a pure virtual function in it is abstract. Some languages make use of an abstract keyword. C++ doesn't have this formality. It uses pure virtual functions instead. If I now go back and uncomment out the implementation in the rectangle class, so that it has got an implementation and also in the implementation file, and rebuild my application again, it builds perfectly okay. So any function that is declared as pure virtual in a base class must be overridden in the derived class. That completes this lesson on pure virtual functions. In an earlier lesson, we saw how a pure virtual function was also known as an abstract function. In this lesson, we'll take the concept a little further and look at abstract classes and interface classes. Again, I'm going to use the shape class as an example in this lesson. OO reflects real life. You can't draw a shape in real life because it's an abstract concept. You can draw rectangles, triangles, etc. These are all kinds of shapes. Just like real life, where an abstract concept can't exist, in C++ you shouldn't be able to instantiate an abstract class, and in fact the compiler prevents you from doing so. Shape is an abstract class because it contains a virtual void draw, which is a pure virtual function defined on line 24. Any class with at least one pure virtual function cannot be instantiated. You can also create an abstract class by declaring its constructors as protected. This prevents the base class from being instantiated, but allows it to be instantiated via a derived class, because the derived class has access to the protected constructors of the base class. We can take the concept of an abstract class a bit further. Some languages, notably Java and .NET, have interfaces. Interfaces are the ultimate in abstraction. They specify a set of operations that a class or hierarchy must implement, but not how it's implemented. An interface generally has function declarations and no code or member variables in it. C++ doesn't have a formal interface type. There is no interface keyword. However, C++ can implement interfaces by using an interface class. An interface class, usually called I-something, is one that only contains pure virtual functions and no state or data. Some languages don't need to use the access specifier on line 13 in my class. However, C++ does. I've created the interface class iShape with 3 pure virtual functions and derived my shape class from iShape. The effect of doing this is that any class which derives from iShape must at some stage in its inheritance hierarchy implement all of the pure virtual functions in the interface. This doesn't have to be at the shape level. In my case, I've not implemented draw at the shape level. I've implemented it lower down at the rectangle and ellipse levels. If you don't implement a function, and remember I've got 3, draw, erase shape and move shape, then when you try and instantiate the class, you get an error. And my error in this case is the object of type rectangle is not allowed because I've not implemented erase shape or move shape. So pure virtual functions and interfaces can be used to specify what a class must implement, but leaving the implementation to the class itself, which derives from the interface class. In previous lessons, we've learned about overriding functions and using virtual functions. This chapter will look at the override and final keywords. Override is a keyword that enforces a check by the compiler. Let's take a look at an example. In this case, I've deliberately made a mistake. In the base class, I've declared a virtual function foo as const. In the derived class, I've declared it as virtual again, but without const. If I compile this code, it compiles perfectly okay. However, clearly, I am expecting my foo in the derived class to override the function of the same name in the base class. To try to avoid such situations, more recent compilers have introduced the override keyword. Any function which is declared as override forces the compiler to do a check. It searches the base class for a function of exactly the same name with exactly the same signature. Clearly in this case, mine isn't, and I get an error stating that the member function declared with override does not override a base class member. Now we'll look at the final keyword. Final is more about stopping virtual function overriding. Here's an example again. In this case, I've got my base class with a virtual function called foo. In the derived class, I've used the override keyword to force the compiler to check that my foo declared on line 13 overrides the foo on line 4 in the base class. I've also put the final keyword on the end of the foo declaration on line 13. Any attempt to further override the foo function results in an error. Final prevents further overriding of the foo function in any further derived classes. And the error I get is that I can't override a final function, and it even tells me that it's declared on line 13 in this compiler. In previous lessons, we've looked at inheritance. This lesson looks at the subject of multiple inheritance, its implementation, and its pros and cons. All the previous examples of inheritance that we've used so far in this course have been single inheritance, that is, a single base class. Multiple inheritance involves two or more base classes. Over the years I've worked with many organisations and they all have different views on multiple inheritance. Some forbid it entirely, others frown on it, and others use it freely. We'll be looking at several examples of multiple inheritance to demonstrate the advantages and disadvantages of its use. Firstly, let's take a look at the syntax. In this case, I've created a class stopwatch, a class clock, and a class chronometer. Chronometer is inheriting from both the clock and the stopwatch class, and the general idea is that the clock measures time in hours and minutes, and the stopwatch measures more accurately in seconds, tenths, and hundredths of seconds. This is fine, except that there is an error. As you can see, the getTime function is underlined in red. The error in this case is that both the clock and the stopwatch class both contain a getTime function. Furthermore, both the getTime functions have the same signature. The only difference is the return type. Functions cannot be overloaded purely on the return type, therefore the call to getTime in chronometer is ambiguous. If the classes that you're deriving from are, as in my case, similar, then it's quite possible that you will end up with this situation. The solution is to use the scope resolution operator, : operator, to resolve the conflicts and call clock : getTime or stopwatch : getTime as appropriate. This raises another interesting question. Should we be inheriting from multiple classes? Well, we've already said that OO reflects real life and everything in real life is built up from smaller building blocks. Our chronometer example makes perfect sense. The chronometer is built up of a less accurate clock and a more accurate stopwatch. So would it be reasonable to inherit from different objects? The answer is yes, sometimes. Multiple inheritance combines the functionality of all the base classes into a derived class. In cases where the classes are substantially different, it's far less likely that we'll get name clashes. We could, for example, inherit from a motherboard, a disk drive, a floppy disk drive, a keyboard, a mouse, and a screen to make a PC. These are entirely different types of object. In fact, let's take a look at exactly that example. Here I've created classes for motherboard, disk drive, floppy disk, keyboard, mouse, screen, and PC. My class PC inherits from all of the base classes. This example will work in C++. However, it has severe drawbacks. Firstly, C++ is one of the very few languages that actually supports multiple inheritance from concrete base classes. Let's look at how it could be improved by using composition. I've still got my classes defined, motherboard, disk drive, floppy disk, etc. This time, my class PC doesn't inherit directly from the classes. Instead, it has private data members for each of the types. This is called containment rather than inheritance. The downside of this is that we'd either have to use friends or member functions of the contained classes to get at their data. However, have you spotted the biggest drawback of the previous two examples yet? We will always get exactly one motherboard, one disk drive, one floppy disk, one keyboard, one mouse, and one screen. Floppy disk drives are generally obsolete. It's highly unlikely that we would want one. Also, many PCs have multiple disk drives and multiple screens. Our example as it stands allows only a single instance of these types. A far better way of implementing the PC will be to use aggregation as shown in this example. Again, I've got my base classes, but this time I'm using a vector, you can use any container, to allow multiplicity of the disk drives and the screens. I've also set the floppy disk to nullputter, indicating that we may not have a floppy disk on this computer. One situation where multiple inheritance is fine is when inheriting from interface classes. Most OO languages, including Java and .NET, support this type of inheritance, even if they don't support inheritance from multiple concrete base classes. In this case, I've created an interface iControllable, which has one public virtual pure function, control. I also have another interface iInsurable, which also has one virtual pure function, pay premium. I've created a base class animal on lines 11 to 14. Then on line 15, I've created a class dog, which is derived public from the base class animal and public from iControllable and iInsurable. Dog would therefore have to implement all the functions, virtual functions, in the iControllable and iInsurable interface. The cat class is derived from the base class animal and just iInsurable, so cat would only have to implement the iInsurable functions. In the working files folder of this course, you'll find files called pchandson.h and handson.cpp. These contain class definitions and a main program. In this hands-on tutorial, you'll be practicing interface classes and inheritance. You should first familiarize yourself with the pchandson.h file. It contains various classes, enums, and interface classes. Currently, there's very little inheritance specified in these classes whatsoever. The only inheritance is on the PC class, which inherits publicly from all the disk drive, screen, motherboard, keyboard, and mouse base classes. The handson.cpp contains a set of instructions, 2 tasks for you to complete. These mainly need modifications in the pchandson.h file. Once you've completed all the modifications, the code in main should compile. As usual, in the working files folder, you'll find a sample solution to this exercise in files called pchandsonsolution.h and handsonsolution.cpp. That completes this hands-on lesson. The standard template library is big. In fact, it's growing all the time. It's far too big to cover the entire standard template library, or STL, in a single chapter. Fortunately, we don't have to. The implementation of the standard template library has been done so that it's largely consistent. For example, most containers have push functions to add data to a container. Where this can be done at the front or back of the container, the routines are called push_front and push_back. The naming convention is consistent across all containers. Once you can use one container, you have a handle on them all. This lesson will be a general overview of the standard template library using a single container type, the list. The standard library provides various type-safe containers for storing collections of related objects. The containers are class templates. When you declare a container variable, you specify the type of the elements that the container will hold. This can be a simple built-in type, such as an integer or a double, or a user-defined data type. You iterate over the elements in a container and access the individual elements using iterators. You can use iterators explicitly by using their member functions and operators, as well as global functions. You can also use them implicitly, for example by using a range for loop. Generally, the iterators for the STL containers have a common interface. but each container defines its own specialized iterators. Containers can be divided into three categories: sequence containers, associative containers, and container adapters. Before we take a look at specific containers, let's have a look at a simple example to get a feel for how they work. As I've said, the container we're going to use is a list. It's not the simplest container, but it's one that has a multitude of facilities. In this demonstration, I've created a user-defined data type, a class called shopping item. It has the appropriate constructors and accessor routines to insert and get at items in the class. In main, line 29 is a declaration of my list. It is a list that contains shopping item objects. The list is called shopping. In this case, I've created an empty list which uses a default constructor. There are other overloaded constructors available. For example, on line 35, I constructed a list from an array. On line 37, I've constructed a list from a vector, and there are others available too. On line 41, I've created a shopping item which is bread and a quantity of 1. On lines 43 to 49, I've used 6 different methods of storing items into my shopping list. Line 43 uses pushback to push a new shopping item, which is beer 24 cans, onto the end of the list. The same on line 44, only this item it's 1 carton of milk. Line 45 still uses the pushback function, but this time it passes a previously created item and adds it to the list. Line 46 is a little bit different. When using lines 43 to 45 pushback, the item is copied into place in the list. This can cause problems. For example, if you don't have a copy constructor defined, then you can run into severe problems if your class contains pointers. mPlaceback is an attempt to resolve this problem. Rather than constructing an item as a copy of the original item, mPlaceback constructs the item in place and adds it to the end of the list. Line 48 pushes an item onto the front of the list, again copying the item. Line 49 uses mPlaceFront to place an item in place onto the front of the list. In this example, I then used a for loop on lines 52 to 56 to retrieve each item in the list in turn. This for loop displays the quantity and the item name. Earlier, I mentioned iterators. Line 58 declares an iterator. The iterator is specific to the list class and therefore is a member of the list class. Iterators are used to traverse the list. On line 60, I set the iterator to the beginning of the list. Shopping.begin returns an iterator, which is the beginning of the list. Lines 62 to 64 increment the iterator. Plus plus operator is overloaded for the iterator, just like a smart pointer, and that points me to the 4th item in the list. Line 66 uses the erase function. The erase function deletes an item from the list and returns an iterator which points to the next item after the erased item. If the erased item is the last item in the list, the iterator returned is a pointer to the end of the list. Line 71 uses the insert method. The insert method takes 2 parameters, an iterator and an item. In this case, I'm using the iterator that was returned from line 66, the erase function, and inserting a new item, coffee, before that iterator. In effect, I'm replacing milk with coffee. Finally, on lines 73 to 78, I'm using an iterator to iterate through the list. Lines 73 to 78 use an iterator to iterate through the list. The iterator is set up at the beginning of the list on line 73, and then I use a while loop while the iterator is not equal to shopping.end. The end iterator actually points to beyond the end of the list. My while loop will therefore print the quantity and the item for each item in the list, stopping when I go past the end of the list. Line 80 calls the clear function on the list. The clear function removes all items from the list. You should remember though that if you're using pointers in your list, you'd have to delete each individual pointer in turn before clearing the list. Many of these functions will be used and explained in future lessons. This lesson looks at the STL String class. We've been using the string data type in various examples throughout this course. Strictly speaking, it's not a standard template library container, however it is a member of this std namespace, and Microsoft calls it an STL String, so it therefore makes sense to include it here. The STL String class is a standard representation for a text string. This class alleviates many of the problems introduced by the C-style char asterisk strings by putting the onus of memory ownership on the string class rather than on the programmer. The class provides some typical string operations such as comparison, concatenation, find, replace, and a function for obtaining substrings. It can be constructed from a C-style string, and a C-style string can be obtained from it. The C++ strings library includes support for two general types of strings. The templated class basic_string generalizes how sequences of characters are manipulated and stored. String creation, manipulation, and destruction are all handled by a convenient set of class methods and related functions. Several specializations of the basic_string are provided for commonly used types. std::string, std::w string, which represents wide strings, std::u16 string, and std::u32 string for 16 and 32-bit UTF encoded strings. Null-terminated strings are arrays of characters that are terminated by a null character. C++ provides functions to create, inspect, and modify null-terminated strings. There are three types of null-terminated strings: null-terminated byte strings, null-terminated multi-byte strings, and null-terminated wide strings. Let's take a look at an example that uses a string class. On line 7, I've declared a string called myString. I could have taken out the using namespace and used std::string. You can also specify initial value for the string in a constructor, as shown on line 12. The string is overloaded for the cin and cout operators, and so you can cin directly into a string object and cout a string object. If you need to read an entire line at a time, you can use the getLine function. Strings can be concatenated and assigned to each other using the standard operators. So in this case, I've got string 1 which contains a string, string 2 contains is this. If I add string 1 and string 2 together, I end up with a string is this in string 3. The plus equals operator is also defined. String concatenation works provided one of the arguments is a C++ string. The other one can be either a static string, a const char asterisk, or simply a char asterisk. One of the confusing things about C strings is using comparisons. You have to use a tricky routine strucmp that returns different values depending on whether one string is greater than, equal to, or less than another string. The string class gets around this problem. It overloads the equals and the other comparison operators too. Strings are merely containers for chars. We can obtain the length of the string by using the length function. This returns the number of characters in a string. We can also access our string using the subscripts. The subscript operator is overloaded for the string class. Not only can we read the string, but we can also write to it using subscripts. So we can change any individual character in the string. Strings are actually sequences just like any other standard template library container. So you can use iterators to iterate over the contents of the string. This is shown on lines 73 to 77. Once again, the iterator is a member of the string class because it's specific to this class. The string class provides simple searching and substring retrieval using functions find, rfind, and substr. Find does a forward search through the string. Rfind does a reverse search through the string. Substr returns a portion of the string. The code on lines 96 to 105 demonstrate this. The substring is demonstrated on lines 116 to 118. I start off with a string which contains A to P, and then I use substr to extract the first 10 elements, or the first 10 letters of the alphabet. Just like the list class that we looked at earlier, the string also has an erase function and an insert function. The iterator in these cases is a simple integer. On lines 155 and 156, I demonstrate the fact that a string can be created from a char asterisk, a const char asterisk in this place, and I can use a standard C library function, strlen, which takes a char asterisk as a parameter to get the length of my string 4. C_str returns a char asterisk version of the string. The return char asterisk is a const value. You can't modify the string using it. If you need to modify the string in myString4, you should create a second string and use the strcopy function to duplicate the result of calling C_str. The string class also contains a data member which returns a char asterisk. This is inherited from the basic string class. However, the return type for data may not be a valid C string because no null character gets appended. The null character is used as a special character in a C string to mark the end of the string, but has no special meaning in the string object. In fact, the string object can contain any number of nulls. The null is treated just like any other character. Although the string class itself is useful, very useful, it might not suit your needs for internationalization. In particular, if you need to support different character sets or wide characters, you may want something a bit different. For this, you can take advantage of the basic string template from which the string class itself is defined. You can then use the basic string to define your own string encoding. In this lesson, we'll be looking at the standard template library Sequence Containers. Sequence containers maintain the ordering of inserted elements that you specify. The sequence containers are vector, array, DQ or double-ended queue, list and forward list. Let's take a look at some simple code for these types. I've created a main program which calls 5 functions, one for each of the types. The functions have been split into separate CPP files. The first one we'll look at is the vector. We've used the vector several times throughout this course already. The vector is like a dynamic array. In this example, I've defined a class person, and I'm going to use that later in the demo example. The first vector we'll look at is a vector of integers. The vector supports the pushback function to add items to the end of the vector. It also supports, as shown on line 28, subscripting to get hold of items within the vector. The empty function on line 31 returns true if the vector has no elements in it. On line 33, if the vector isn't empty, I use the clear function to clear out all the items currently in the vector. Line 36 defines another vector, and I push back the number 10 onto that vector. Vectors support operator equals equals to test for equality. Finally, I create a vector of person classes, or person objects, called people. I create a person, me, and initialize it with Simon21 male, and then push that person back onto the vector. I can also construct a person within the parameters to push back, which is shown on line 52. mPlaceBack is a construct in place function which constructs a person in place and reduces copying. On line 56, I create another vector of integers called v1. This vector uses a constructor to construct a vector of 10 elements, all initialized to the value 99. We then have some additional functions. Reserve reserves enough space within the vector for 100 elements. However, it doesn't actually construct those 100 elements. The current size after line 56 was 10 elements. After line 58, the size will be 10, but the capacity will be 100. On line 59, I call resize. That resizes the current 10 element vector to a 100 element vector. The second parameter is the initialization value. Elements 0 through to 9 will still have the value 99. Elements 10 through to 99 will have the values 999. I then resize the vector to 200. I then resize the vector to 200 elements. The last 100 elements are uninitialized or have the value 0. Line 63 reserves enough space for 1000 elements in the vector. At this point, my size is 200, but I have enough space to store 1000 elements. If you ever end up with unnecessary space in your vector, to save memory, you can call the shrink to fit function, and that shrinks the capacity down to the size. In the case of the cout on lines 65 and 66, I will get the figure's capacity of 200 and size of 200. The next container type we'll look at is the array. The array STL type is very similar to the standard built-in C++ array. The main difference is that the STL array does support container operations. So for example, on line 17, I've used a sorter algorithm to sort the STL array, and I've passed it an iterator to the beginning of the array, a1.begin, and an iterator to the end of the array, a1.end. The ranged for loop is also supported for the STL array. The next type we'll look at is a double-ended queue, or DQ. On lines 7 to 16, I've overloaded the output operator for a double-ended queue. I should be using cout with a double-ended queue fairly often in this code, so I've overloaded it to provide one single point of outputting. On line 22, I create a double-ended queue. The double-ended queue words1 is initialized using a universal initializer. It will contain 5 elements: the, frogget, is, also, and cursed. If I see out that double-ended queue, that's exactly what I should get. Next, on line 26, I created another double-ended queue of strings. This one is constructed from words1. I passed 2 iterators into the constructor for words2, and because I'm using begin and end, then words2 should be exactly the same as words1. I could use different iterators. For example, I could create an iterator, iterators are discussed in a later chapter, which points to only the third element of the list, and initialize words2 from the first 3 elements of words1. On line 30, words3 is a copy of words1. This is a copy constructor for a double-ended queue. It's effectively the equivalent of line 26. On line 34, I create another double-ended queue called words4. I construct it with 5 elements and provide an initializer. All 5 elements are initialized to mo. Then we have some code to demonstrate the functions available with a dequeue. I create a dequeue of integers called numbers and use the pushback and pushFront functions to store values at both the back end and the front end of the queue. Lines 47 to 56 also demonstrate further functions used with a double-ended queue. Numbers.front returns the item at the front of the queue. It doesn't actually remove it, it just returns the value of it. The following line, line 48, pops the item from the front of the queue, i.e. removes it. Lines 49 and 50 do exactly the same for the back end of the queue. The remaining lines just print out what's in the queue. The next type we'll look at is a list. This code was used in a previous lesson, so we'll only go through it very briefly. It's a list of shopping items, and lines 42 onwards push various items onto the list. They emplace items onto the list. Note the list also has a pushFront and an emplaceFront function. Then I use a range-based for loop to iterate through the list. I also use an iterator, shop item, : iterator, to iterate through the list. Iterators can be incremented. The ++ operator is overloaded for a list iterator. I can use the erase function and the insert function. And finally, I clear the list. Remember, if you're using pointers in the list, clear will not call destructors on all the pointers. The final item we'll look at is a forward list. Again, I'm using the shopping item. The forward list only supports pushFront operations. It doesn't support any back operations that the previous list did. Other than that, it's almost identical. It has an iterator, you can increment the iterator, but you can only move one way through the list. The forward list is effectively a lightweight or lighter weight list. It's only a singly linked list. Older compilers may not support this type. It supports fast insertion and removal of elements from anywhere in the container. Fast random access isn't supported because it's implemented as a singly linked list. Compared to the list STL type, the forward list supports more space-efficient storage. In this lesson, we'll be looking at another category of STL container. This time it's STL Container Adaptors. A container adapter is a variation of a sequence or associative container. However, it restricts the interface of the base container for simplicity and clarity. Container adapters don't support iterators. Because they don't support iterators, they can't be used with the STL algorithms that are discussed in a later lesson. The container adapters are stack, queue, and priority queue. Let's take a look at some sample code for these types. The working files folder for this lesson contains 4 files. One is a main program which is used to test the 3 container types. The first container type we'll look at is the queue. Queues are a type of container adapter specifically designed to operate in a first in, first out or FIFO context, where elements are inserted onto one end of the container and extracted from the other. Essentially, it's a cut-down version of a double-ended queue. Queues are implemented as container adapters, which are classes that use an encapsulated object of a specific container class as its underlying container. They provide a set of specific member functions to access the elements. Elements are pushed onto the back of the specific container and popped from its front. The underlying container may be one of the standard container class templates or some other specifically designed container class. The underlying container must support at least empty, size, front, back, pushback and pop front operations. The standard container classes double-ended queue and list fulfill these requirements. By default, if you don't specify an underlying container class, the standard container used is double-ended queue. On line 9, I create a queue. Lines 14 to 18 push values onto the queue, reading them from the keyboard. The empty operation is demonstrated on line 21, as is the pop operation. The priority queue is a variation on the queue. It's specifically designed such that its first element is always the greatest of the elements it contains. Again, I've created a function to print a queue. This simply goes all the way through the queue, counting the top item on the queue. In the simplest situation, I've created a priority queue of integers called q on line 20. Lines 22 to 25 push the values 1, 8, 5, 6, 3, 4, 0, 9, 3 and 2 onto the priority queue. The greatest value will be at the head of the queue, 9, 8, 6, 5 and so on. Line 35 creates a priority queue which is based on a vector of integers. The third argument to the priority queue on line 35 is a comparison routine. The standard library contains various predicate routines. Less is the default routine used in this case, which sorts them into descending order. If we use the greater comparison routine for an integer, it will store them in reverse priority order. We can also create priority queues which store strings or any other data type. Line 44 creates a priority queue of strings called PQ, and we push the strings the quick fox jumped over the lazy dog onto this queue. They're stored in this case in lexicographic order. The first one will be fox, then jumped over, then lazy dog, and then the quick. The lowest priority string is fox, and the highest priority string is the quick. And lines 56 to 62 print this out. The final adapter container we'll look at is the stack. The stack is just like a stack in a computer. It is a LIFO or last in first out stack, where elements are inserted and extracted only from one end of the container. Just like the priority queue and the queue before it, the stack can also be implemented on other containers. The underlying container may be any of the standard container class templates or specifically designed container class, so long as it supports the empty, size, back, pushback and popback functions. Vector and dequeue and list fulfill these requirements. By default, if no container class is specified for the stack class, the standard container double-ended queue is used. The code here pushes the numbers 0 through to 4 onto the stack and then pops them out while the stack is not empty. That completes this lesson on sequence STL container adapters. In this lesson, we'll be looking at the last category of STL containers, the associative containers. In associative containers, elements are inserted in a predefined order. For example, a sorted, ascending, unordered associative containers are also available. The associative containers can be grouped into two subsets, maps and sets. A map, sometimes referred to as a dictionary, consists of a key-value pair. The key is used to order the sequence, and the value is associated with that key. For example, a single map might contain keys that represent every unique word in a text, and corresponding values that represent the number of times that each word appears in the text. Unordered version of the map is unordered map. Here's an example of a map. The map declaration on line 10 takes two parameters. The first parameter to the template is the key type. The second parameter is the value type. And in this case, I've created a map of employees. I can use array-like index notation to assign values into a map. On line 13, my key will be 5234 and my value will be Mike C. I can also use the index to access any member directly, where the subscript is the index or key of the item I wish to access. I said that the map uses a key-value pair. The key-value pair is actually, behind the scenes, a structure, and the structure contains two elements. First, which is the key, and second, which is the value. This is illustrated on line 24. I can also use other types as the key. For example, on line 27, I've used the string as the key and the int as the value. In fact, I've reversed the previous example. Line 34 shows the insertion of an employee into my map. The key value pair is of type std::pair. This is a templated type which has two members, one for the key, one for the value. Line 38 shows another kind of insert using a type. In this case, it's a type which is embedded within the map object. The insert function first parameter is map string int : value type. We've come across this notation before when we looked briefly at iterators. The iterator is embedded within the STL class, and so is the value type. Line 41 uses another function to create a pair from two parameters. The next type we'll look at very briefly is the multimap. With a map, all keys must be unique. With a multimap, we're allowed to have duplicate keys. That's shown in this example, where I've got 3 keys all equal to B, and in fact 2 other keys equal to A. The only unique key in this example is C. I can use the count function within the multimap to count the number of items with a given key. So in my case here on lines 23 to 25, I should get number of items with key A is 2, number of items with key B is 3, number of elements with key C is 1. The rest of this section shows some more operations that we can do on a multi-map. The next item we'll look at is the set. In this case, my set is going to store big objects. Within the big object, I've overloaded operator less than, and I've also overloaded operator less than as global member functions too. The two global overloads are binary symmetrical. The first global operator less than has parameters string big object. The second overloaded global less than operator has these parameters reversed. With a straightforward set, if I add hello and world to the set twice, then the insert will fail. Sets, like maps, must have unique keys. If it fails, then the return value is a pair, the second of which is a Boolean value which determines whether the insertion was successful or not. My output on lines 50 to 56 should say that the set contains hello and world. The second hello and world insertions will fail. I stated that I'd overloaded operator less than in order to compare items. This was done in this case so that I could do lookups by simply passing in a small string that can be compared to the object. This type of operation may not be supported by older compilers. Let's take a brief look at the code. I create an object B1 with the string 42F, an object B2 52F, and a big object B3 62F. I then create a set of big objects. The second parameter to the big object set is a predicate function less. We've seen this a couple of times before. This is the std::less function. That function will compare two objects. I insert B1, B2 and B3 into the set and then create an iterator. I use the find function to find a string 62F in the set. However, the set is of type big object, but because I've overloaded the less than functions, the comparison will work. And in this case, I'm searching for an element which exists in my set, 62F, so I should get a found message. The multiset is very similar to the set, except that in this case, with a multiset, we can have duplicate keys. In this example, I've created a series of multisets in different ways using different constructors. The first multiset created on line 20 is an empty multiset of ints called first. The second example on line 23 is using pointers as iterators. The third example on line 25 is using the copy constructor to the multiset. Line 27 uses two iterators to construct fourth from second.begin to second.end. This is effectively the equivalent of the copy constructor on line 25. And finally on line 29, I've created a multiset of integers, but passed it a class as a compare. ClassComp is a structure which has an overloaded function which compares a left-hand side and a right-hand side object. Using a class as a compare was covered in the lesson on object functors. The last example uses a function pointer as a compare. I defined a function called fncomp, which takes a left-hand side and a right-hand side int as a parameter and returns a Boolean. It returns true if the left-hand side is less than the right-hand side. On line 31, I create a pointer to that function called fncomp, and when I create my multiset on line 32, I tell it that I'm going to pass it as the second parameter to the multiset this type of function. When I call the constructor on the end of line 32, I pass it the fn_pt pointer to the function. The code files for this section also contain unordered set testing code, unordered multiset testing code, unordered map testing code, and unordered multimap testing code. By and large, this is very similar to the map, multimap, set and multiset that we've already covered. This code is available for you to do your own experimentation on. We've already spoken about and used iterators in some of the previous lessons. This lesson takes a brief look at the types of iterator available in different containers and the differences between them. The internal structure of the STL types is different between each container. Consequently, traversal through the container is also different. Some containers only allow forward traversal, such as the forward list, while others allow bidirectional traversal. Some allow random access, such as the vector, access through subscripts, while others do not. The list doesn't have a subscript. The design methodology for the STL came up with a standard way of traversing containers, that is, iterators. Iterators abstract the idea of a position within an underlying container and also abstract the method of moving around that container. Let's take a look at what iterators are defined for each of the STL container types that we've encountered. The string contains a const iterator and a const reverse iterator, and also non-const versions. Access through a const iterator only allows reading the underlying collection. If you wish to change it, i.e. have read-write access, you have to use the iterator and reverse iterator. The vector has the same four iterators defined. However, in this case, the iterators are specific to the vector class. Similarly with the array also defines const and non-const iterators, both forward and backwards iterators, as does the double-ended queue. The list also defines the same four iterators. The forward list only defines forward iterators, a const forward iterator and a forward iterator. Traversal in reverse from a forward list is not allowed. The adapter container types queue, priority queue and stack do not provide any iterators at all. The map and multimap are again back to providing the four iterators, the const forward and reverse iterators and the non-const forward and reverse iterators, as do the set and multiset. The unordered containers, unordered set, unordered multiset, unordered map and unordered multimap only provide forward iterators, a const forward iterator and a non-const forward iterator. Once you've declared an iterator, the iterator can be generated by various STL container member functions. For example, the begin and end functions of a container return an iterator which points to the beginning of the list and one which points beyond the end of the list. The remainder of this section is further reading for you. It talks about input iterators with an example, output iterators, insert iterators, and the routines that are used to create insertion iterators. You can also use OStream and iStream iterators to do direct I/O onto containers. In the code on lines 188 to 194, we've created an iterator for the output stream, which takes an integer as its type. The iterator is called outItter. The file we're using with it is cout, and the second parameter to the outItter constructor is a delimiter which is used when outputting the items. We've previously said in other lessons that there's no way that we can output an array directly. In fact, I made the statement in that lesson that the compiler wouldn't know how to separate the array items. It wouldn't know whether to put commas between them, new lines between them, spaces between them, tabs between them. Using this iterator, we're actually specifying that delimiter as the second parameter. So when I push back 10, 5 and 99 onto my integer vector, and then use the copy algorithm function between the beginning and the end of the vector, it copies all items between begin and end to the output iterator. The output iterator points to cout, therefore individual items are all copied to cout, and because I've specified the space as the delimiter, they're separated by spaces. We can also have input iterators for cin, we can have forward iterators, bidirectional iterators, random access iterators. Rather than create examples for all of these types of iterator, I have merely included comments in this file, which is available in the Working Files folder. You can then investigate further. However, they're all iterators, they all work in a similar way. In previous lessons, we've looked at the STL containers and iterators. This lesson will look at a set of STL algorithms that can be used with containers. The STL algorithms are a set of functions written independently of container type. An algorithm requires only that the iterators it operates on conform to a minimum category. For example, to be able to reverse the sequence, different parts forward and back of the sequence must be revisited, and so a forward iterator will not meet the requirements, but a bidirectional iterator will. The majority of the algorithms are specified in terms of iterators. Given that most containers seem to support begin and end, why are the algorithms not templated on containers? There are many reasons. For example, it's not necessarily the whole container that needs to be operated on. Iterators can be used to specify a start and end position for the operation. Also, not all iterator sequences are necessarily from containers. For example, we could be searching an iStream iterator range. An iStream iterator does not come from a container. In some cases, it may appear that the STL provides duplication between a container member function and an algorithm. Remember though that algorithms are non-intrusive to containers, or in other words, they have no knowledge of the container in which the data being manipulated resides, or even if the data is in a container at all. In view of this, member functions are to be preferred, since they were written with precise knowledge of the implementation details of the container. Let's take a look at a few of the algorithms. The first one we'll look at is the sort algorithm. For simplicity, it will be demonstrated with a vector of integers. On line 41, we've declared a vector of integers and used universal initialization to initialize it. On line 43, we use a sort algorithm. The sort algorithm takes two parameters, numbers.begin and numbers.end. These don't have to be the beginning and the end of the container. We can sort between any two positions in the vector by supplying different iterators. On line 46, we redeclared the vector as numbers2. We declared two iterators, start and finish. And on line 51, we've incremented the begin, the start, by 1. On line 52, we've set the finish iterator to be the number 8. This is one item away from the end of the vector. In other words, we're sorting the numbers 6, 4, 3, 2, 5, 9 and 8. The sort, on line 54, takes the two new iterators and sorts between these items. The next example uses a vector of books. The book class is declared in line at the top of this function. We have a vector of books called library, and we place 5 books into the vector. Lines 64 and 67 use a for each algorithm to carry out an operation on this vector. On line 64, for each calls displayBook on each member of the vector. DisplayBook is another function at the top of the main, which takes a book as a parameter, or more accurately, a const reference to a book. The display function is called on that book. For each on line 64 ensures that the displayBook function is called, and each time it's called, for each element of the vector, the book is passed as a parameter to the displayBook function. Line 67 is a variation on this. Rather than having a separate displayBook function, the mem_fn function is used to pass a reference to the display function directly to the for each algorithm. In this case, the book display function is called directly and we don't need the displayBook function. As I've already pointed out, there are many algorithms. This lesson's looked at a very small selection. In previous lessons we've looked at the C++ standard template library containers. In this lesson we'll consider the performance of the STL. It's very easy to write inefficient code in C++. It's even easier to use the STL in an inefficient way. However, a few hints and tips can help you be more efficient. First, choose the correct container. Contiguous containers such as the vector are best for random access. Vectors in particular achieve random access by having an overloaded subscript operator. They are efficient, subject to a caveat, for adding new elements onto the end. The caveat is that there must be capacity available to do so. If not, then a potentially costly resize operation will take place. Node-based containers such as the list have no random access. They're good for forward and reverse traversal using iterators. They're also efficient for adding new elements anywhere in the list. Inserting elements into a list is simply a matter of adjusting pointers between nodes. The container of choice should be the vector, as it's one of the simplest and most lightweight. The second choice should be the list. The adapter containers, queue, stack, etc. should, as far as practicable, be based on a vector, although previous lessons have shown how this can be altered if required. The map, multimap, set and multiset are more complex containers and should only be used when the features of these containers are required. Performance of the contiguous containers can be enhanced by reserving capacity up front. This reduces resizing. Also consider constructing the container with a number of elements initially if this is applicable. Constructors are usually provided for this purpose along with a resize function. If you're concerned about the memory usage of your container and believe that space may be wasted as a result of automatic resizing, you can call the shrink to fit member. This reduces the capacity back down to the size. It should only be done once the container has been fully populated, as any additions to the container after that point will cause another resize. Using pointers to objects is preferable to using objects in containers. However, you should remember that you will need to manage the objects yourself, calling delete on them where appropriate. When adding items to a container and when resizing, copy construction is often used. If your class contains dynamic memory, then you should provide copy constructors. Deleting the copy constructors is not usually an option. Also, when adding objects to the container, consider using one of the mplace functions rather than the push functions. Mplace constructs items in place in the container. This is more efficient than copying. If you're using algorithms with your containers, wherever possible, use member function algorithms. Member algorithms are aware of and can take advantage of the container structure. The global algorithms are not and will usually be much less efficient. If you can implement the algorithm yourself, this should also be considered. It's not usually good practice to reinvent existing code. However, on tests I've performed on the for each algorithm, writing my own range-based for loop was very substantially more efficient and faster than using the provided algorithm. In the working files folder of this course, you will find files called handson.cpp, handsonbook.h and handsonbook.cpp. You should look at these files and familiarise yourself with them. They're a skeleton program with a series of commented sections in the handson.cpp files. The handsonbook.h and handsonbook.cpp files contain a skeleton class declaration and implementation. The hands-on.cpp file is a skeleton program with a series of commented sections. These comments are your instructions for this hands-on session. Your task is to replace the asterisks in the skeleton program with either the entire missing statement or part of a statement as guided by the comments. As usual, a sample solution with files suffixed with the solution can be found in the working files folder for this lesson. Let's have a brief review of the objectives that we set at the start of the course. We set out to understand and use the key concepts of object orientation. We also set out to use both fundamental and complex data types, and use pointers and dynamic memory. We also set out to use modern programming techniques such as move semantics and lambdas, albeit at a basic level, and to write efficient and robust code. Finally, to use generic containers and to enable you to write your own templated generic functions and classes. Throughout this course, these objectives have been met in one way or another through a mixture of teaching and hands-on exercises. We've covered complex data types, structures and classes, functions and function parameters including optional parameters and passing by value and reference. We've covered classes and class initialization, that is declaring and defining classes and writing constructors. We've looked at the need for copy constructors and conversions. We've looked at pointers, including the use of smart pointers. We've looked at relationships between objects and how these can be implemented within classes, global and member function operator overloading, and the two major OO principles of inheritance and polymorphism. Finally, we looked at the standard template library, or STL, and the algorithms that you can use with this library. From this point, you can go on and study some further topics. Suggested topics might include concurrency and multi-threading, DLLs or libraries, move semantics which were mentioned in this course, design patterns, advanced templates, lambdas, and more. There is always more to learn. The C++ language is very, very powerful and it's continuously evolving. It's taken me over 20 years to build my knowledge of the subject and I'm still learning. Resources available to you include additional courses. There are loads of books available on C++ programming. The internet has a vast wealth of resources, and don't forget your colleagues. That concludes this final lesson.